Good morning. Welcome to day 4 of the Advanced Sensors and Instrumentation annual review webinar for fiscal year 21. I appreciate you attending to the last day. Today's presentations will be on the topic of digital technologies. That's session 4. The moderator for this session will be Craig Primer from Idaho National Laboratory, and he will also be our first presenter of the day. Craig, turn it over to you.
Hi, thank you very much. So I just was going to briefly review what I heard Pattrick share at the beginning on Monday, Monday, I think it was Monday. It's a long time ago. But just an overview of the digital technologies. And so hopefully this will advance. All right. So what I've got is just an overview of today's session and then a quick touch base on what we're planning on doing to develop the digital technologies for advanced reactors, INC systems. So I'll be going over those topics. So as you can see, we've got quite a few presentations planned to share work in the area of digital technologies, mainly focused on the advanced controls and the AI machine learning or applications around that control systems, autonomous and semi-autonomous controls, and also applications that are useful for managing processes and programs within the reactor logistics or maintenance activities and things like that. So you can see here, I won't read the complete list of each person presenting, but you can see the folks that'll be presenting. First session will go through to 12:15 Eastern. We'll take a break for about 15 minutes, and then we'll come back with the second set and go on through till 2:30. Take, I guess, afternoon break or lunch if you're in the mountain time for a half an hour, and then finish up the set with a panel session, allowing everybody who's joined us to pose questions. We'd encourage the presenters to stay through that or be available for the panel session. If there's a specific question to one of the presenters that isn't available during the panel session, we'll definitely make sure that that's sent to that person and get that back to you. So in your interface for the webinar, there's a questions panel. You can pose the questions to us. We'll see those and we'll capture those into and talk through them in that panel session. So again, thank you. Dan mentioned day 4. This is quite a bit of information, several sessions. So appreciate everybody who's come to each of these. I think in each of the sessions, there's been a lot of useful and interesting information shared, and I'm sure today will be similar. So thank you for joining us today. Moving on now into just kind of put this back in perspective of what we're talking about today. So we're continuing on into the controls and the machine learning, artificial intelligence, the applications that inform and help those controls be, whether they're semi-autonomous or autonomous, those types of applications will be hugely important for those to be rolled out into different applications. The microreactor obviously is one of the ones that we're looking at coming out of the gate for the advanced reactors and using autonomous controls. So specifically, the neat ASI research in the digital technologies area is looking at integrating the advanced sensors and INC technologies so that they can be adopted by the nuclear industry. Now on to the digital technologies program objectives. We've got 3 main areas in that space. We're looking at how to have the elements established and developed into research objectives. And specifically what we're looking at is the ability to integrate advanced instrumentation and control technologies with digital twins for modern industrial applications. And so as we're doing that, it's very important that we look and integrate the digital controls with artificial intelligence and machine learning to capitalize on the advancements in what you've seen over the last few days in the areas of sensors and communication technologies. Integrating those with advanced condition monitoring and analytics is the key. And so what we're looking at is using these sensing technologies that have real-time or faster than real-time capability. They're able to provide dramatic increase in the volume and quality of process variable data in the digital INC systems, enabling higher degree of automation. And that's what we're looking for, is that autonomous control. And it's really the path forward in attaining that. So optical fibers, acoustic-based interrogation systems are examples of data collection that allow unprecedented ability to attain data, transfer information back and forth. So we want to leverage that. Multi-point, multi-mode analog sensors, we can use those and integrate those for higher data availability and digitize those into use for the digital twin and modeling inputs and things like that. So you can see here, we hit 3 main points in what we're trying to achieve, and I've talked around those, but just to be specific, the condition monitoring is, and you've got this picture here of some of that monitoring and the different types of algorithms and approaches that are useful in that monitoring. So you have the reinforcement learning, the supervisory algorithms for automated controls, and just can read around the different approaches that might be useful in that space. And then the key point here is in the second bullet. All of this is being pulled together to support a nuclear digital twin with hardware in the loop simulation. And then that'll allow us to demonstrate the performance of these algorithms and prove autonomous operation. And that's the key goal there. All of this, again, is leveraging and using modeling and simulation tools that talk about the communication and the sensors in a very new and advanced way. So now the last part of my intro, and before we move on into the today's presentations. So this year, we're leading an effort to develop an approach to integrate these advanced control algorithms in nuclear digital twins. So that's what we're working on. The 5-year objectives, with this being the beginning of that effort and developing the integration approach, will allow us to test out and develop the right digital twin approach. And you can see, and this was a figure that was shared earlier on Monday when we kicked off this presentation. We have this kind of arrangement of the actual plants. So you see that where it's described as your reactor. So that would be the microreactor or some advanced reactor that would have actual equipment in place that was being monitored and replicated or simulated through the use of a digital twin. That digital twin would be comparing the input from the plant to what it's predicting, and then sending and communicating that information to some remote monitoring and control center. That remote monitoring control center is actively taking that information, and decisions are being made to support the plant. And then you can see the maintenance facility being tied to the monitoring and control center. and also tied to the plant. So as there's reasons or needs for activities, support activities, maintenance, or engineering support, those would be sent to as needed to the plant. So that's the envision integration of people to digital twins to the plant to the support organizations, and we're developing that overview of that approach based on a lot of the research that you're going to hear about today, and showing that and demonstrating that in that advanced control demonstration, hardware in the loop simulation type of approach. So that's where we see this headed. So this year's activities is going to capture the gaps and the needs and the research objectives that still need to be developed and demonstrated through the next couple of years to achieve this vision here that you see that can show how these digital twins can monitor and predict the needs of the plant in real time or faster than real time. So you can ensure, if you're thinking about supply chain logistics or things like that, you can predict the needs that the plant will have in advance. So the 4 bullets here go into that in a little bit of detail, talking about how anomaly detection is a big piece of what the digital twin is comparing its expected performance to something the plant is actually seeing, and identifying anomalies and communicating those to the support staff to diagnose and correct what might be a problem in the plant. These modeling and simulation tools are the basis or foundation of this kind of approach. So having very complete models and demonstrated high fidelity models is a really important part of that. So we need to make sure that we have those, and that's what we're developing now and we'll be leveraging in the future. And then we talked about the communications piece of that and the importance of that. And finally, all of this is going to be enabling and leveraging these control algorithms to enable this autonomous operation. So that's where we're at. That's ultimately what we've been working on as the vision of this space. The digital technologies is allowing for this integration of sensors, communications, the advanced AI ML applications, and integrating all of that into something that's useful for the advanced reactor community to incorporate into their general operations and maintenance and support of these plants. So that's the overview I had planned for us. I looks like I'm a little ahead of time. And I know Rick, you're up to bat there, so I'm ready to transition it over to you a little early, if you're ready.
Hi, Greg. Thanks for the introduction. So I was a little late at the start of the meeting. So
no worries.
So yeah, I think we can move on.
Let me turn it over to you, Pattrick.
Sorry.
I said, let me turn it over to you. Got a couple minutes. Like to add?
I think it's a good idea to turn it on to Rick Willem and start the next presentations. We then would avoid having to compress. I am sure that there's a lot of projects. They're all like around or about the same stage in terms of TRL, unlike what we've seen in the last few days, where we had like some more R&D related work and some more demonstration portions. And so I think today will end up being compressed, and we're probably going to race for time, I am sure, at the end of each presentation. So it's not a bad idea to start earlier. I don't think anyone would join at 8:30 specifically to start, because if they join now. So if Rick is available, I think we can start, and maybe shift some of the presentations earlier. So no pressure on filling the time, Rick. We'll just, when you're done, we'll just have some discussion. I don't see any questions for your introduction.
Pattrick,
Greg?
could you confirm that you can hear me and see my screen?
I see a screen, I see you, and I hear you fine. So just the screen needs to go on in presentation mode and you should be fine. Perfect.
Terrific. Let me, okay. I'm Rick Phillip from Argonne National Laboratory. This project.
Sorry, Rick, the screen was on, but at the moment is not, so it disappeared.
Just a moment. What do you see now?
Right now, no presentation. Oh, there it is. It's coming. Sorry, there's some lag, side time lag. So okay,
Yeah.
it looks okay now.
I'm actually on travel and not in my usual environment. You still see my screen, do you?
I do. Try to move to the next slide. Yeah, perfect. That works. Thank you.
So Rick Phillip, Argonne National Laboratory. This is a project that is officially coming to its 3-year conclusion, but there's a no cost extension. So we're going to press on with the tool we're developing. So in the title, the process constrained data, what that implies is something more than measurement data. So we've invoked the digital twin concept, a physics-based conservation type model. There's other information, but in this presentation, it's going to be basically the digital twin that augments the measured data. What we're trying to do is assign a sensor set to an advanced reactor for advanced O&M monitoring needs. And so, traditionally, sensors are out there for alarm and control. They're not really there for condition monitoring. The plants that were built in the 1970s never really got there. But for the advanced reactors, we have, high-powered computers, high-powered software, modeling capabilities. So we can now think about, installing sensor set that will give us the status of component health and even allow us to predict where the component will be in the future, so we can adjust our O&M tasks in a optimal economic fashion. So formally, you've given a list of faults to be diagnosed to a prescribed level of spatial resolution. We're trying to find the sensor set that will accomplish this at the least cost. And we can't do that actually without process knowledge. We have to have a digital twin, something more than just data. There's no algorithm out there that's purely data driven that can actually diagnose to the level of component fault versus a sensor fault. You need to bring in additional information. So with us, it's the digital twin. The digital twin additionally provides virtual sensor capabilities. So in fact, you have more process variables known to you than if it were just a plain data-driven approach. And further, if you have a conservation-based model, you can reason back from the diagnosis to the sensor set and confirm that actually the diagnosis you got was in fact correct. And we saw that in tests we did with operators 2 years ago in a full scope simulator. They were always looking to confirm, through their kind of logical thought processes, that the diagnosis that was being rendered was correct. So we have that explainability built into our algorithm. And just by way of motivating things, on the right-hand side, we have on the top a figure of a pump with some sensors, and we can resolve the fault to either the valve, the line, or the pump. But if you put in additional sensors, the red region compresses and you have greater spatial resolution. So that's the kind of thing we're trying to do, determine the sensor set that gives us the desired degree of resolution. Okay, so as I say, the diagnostic algorithm is digital twin based. We use automated reasoning to look at the difference between digital twin prediction and what the sensors are reporting. And from that, you can infer what's happened, what the fault is. So the digital twin is constructed from domain knowledge, the characteristics of the plant components. And that allows us to provide a richer understanding what the system is doing than if we simply looked at each component in standalone fashion. So we use the digital twin to model the system, the engineering system, which will consist of pumps, heat exchangers, and we're just able to get a much richer understanding of what's going on if we treated each of those components in isolation. So the sensor assignment algorithm we've developed, it actually is a wrapper around a diagnostic algorithm. And so we call this diagnostic algorithm iteratively, and we converge on the lowest cost function through this iteration. And so the problem is cast as a mixed integer problem. You know, the sensor's either there or not. So that's a 0 or 1. That's how it's done formally. And we're basically just trying to minimize the cost of you know, the sensor set given a specific set of diagnostic objectives. So over on the right-hand side, you can see how we, you know, conceptually go from a process flow diagram, that's the one in the background, to a you know, a nodalization diagram that the digital twin will consume, to a an HMI interface that the operator would look at. Okay, so we, as I say, we've been on this project for 3 years. First year was methods and algorithm development. You can see a flow chart of different pieces that fold into creating these model residuals, which we use to compare against sensors and make our diagnosis. Second year, we went to actually looking at particular components. The table there is for a feed water pump, a motor set and bearing, and based on the value of the residuals, you can locate the fault, be it a motor fault, a bearing fault, a pump fault, or a sensor that is out of calibration or faulted. In the third year, that's just the year that ended, we actually have been looking at utility data, and you'll see more of those results shortly. So the industry does have an interest in this, particularly the advanced reactor people. They know that current fleet is really expensive when it comes to O&M. So in that plot you see on the left-hand side, we've got gas turbine O&M costs compared with light water reactor. And the blue is O&M costs, and you can see that there's room for improvement in the nuclear compared to gas turbines. And so the advanced reactor people, I think, appreciate that. And so the tool we've developed will, you know, enable them to. It's a part of the toolkit that will enable them to reduce their O&M costs. So in the middle of the slide, our approach, as I say, allows for explainable condition-based monitoring. And the figure there in the middle, we have something called forward chaining, backward chaining. It's relating cause and effect. So the cause is the, you know, the fault. The effect is the sensor that you're seeing, deviation, and we're able to go back and forth through this automated reasoning. And it's sort of the same sort of thing that an operator would do, although qualitatively, not quantitatively. So we can do what the operator does, but we can even do it quantitatively. So we can come up with more specific diagnoses than the operator would be able to. And we can do it much quicker. An operator would be challenged to do this in real time. Okay, so this is actually a module that we've got over these 3 years that will plug into something greater. And so on the right-hand side, you see a series of steps, and this is pulled from Dave Grabowski's project. He'll talk a little bit later. We're doing the online monitoring diagnostics, that's step 3, but ultimately where we're trying to go is asset management and maintenance optimization. So this work is, it does have a follow-on, plugs into Dave's, and so there's some coherence there. It's not just going to die. It does have utility in terms of long-term advanced reactor goals. Okay, so the advantages of a physics-based digital twin, there's 2 of them. There are some problems that utilities recognize with data-driven. They're not problems, but limitations. On the table on the right-hand side, I've got a number of different capabilities, and I'm comparing them data-driven versus physics-based. You know, I'm not going to go through them all, but you know, you can see them one at a time. Where there's green, you're able to manage better than where you were, you know, you're data-driven, which is red. So basically, the digital twin allows you to improve your business case. And the table kind of buttresses that. So the support from the nuclear industry that we're providing, the current plants want to go beyond 80 years. They're going to have digital upgrades. The equipment is going to degrade. It's going to be more health monitoring problems. I mean, these aren't new plants, they're older plants, they're aging plants. So being able to do diagnostics online is going to be useful for these plants. They're trying to improve their economics. If you can get people off the plant floor and into the M&D center through the technique that we're using, well, that's an economic gain you're realizing. So basically, if the designer during these digital upgrades or the advanced reactor designer can understand how to design a sensor set to improve monitoring, that will allow for staff reductions and more reliable operations. So we're supporting the nuclear industry through that capability. So let me move to our results and accomplishments. So we, number one, developed a virtual sensor capability for an engineered system. So on the right-hand side, there's two parallel feed water heaters. That's an engineered system. It's not just a component, it's a number of valves and heat exchangers, all linked together. So our virtual sensor capability is based on a digital twin that we create for the engineered system. And by having these virtual sensors in combination with physical sensors, we have a richer set of measurements, for making diagnoses. We create these virtual sensors solely through the piping and instrument diagram. We transfer that information into a model. The engineering parameters in the model are obtained through data that we take in the plant. I won't go into the details of that, but we actually have done it in operating plants and it does work. Our digital twin actually is fairly advanced. It's kind of like, how you would interact with a systems code. You have a library of components, you stitch them together through the input. That's what we do. We don't have a hardwired implementation for each system. We configure the system that we're interested in through the input deck. And, we're actually working on a drag and drop capability currently. So we have these building blocks of individual components. And I say the parameters, I won't go into great detail, but essentially we don't have to provide things like heat exchanger, tube dimensions, or pump performance curves. We derive that data from the plant. Let me just back up. So on the right-hand side there, you can see the green are the actual sensors and the red are the virtual sensors that have been created by virtue of having the digital twin for that system. Okay, so we actually, moving on to the second accomplishment, we did do blind fault diagnosis for a feed water pump motor set. You can see it there on the upper right-hand side. So we had 3 blind events. That is, we didn't know what they were. The utility did. A plant load change. Actually, they kind of snuck one by us. There was no fault. And we actually did correctly. We turned back to them and said, we've analyzed this, there was no fault. But they gave it to us because data-driven techniques aren't very good at flexible operation. They just like to be at an operating point. But this was a plant load change, and we were robust for that change and came back with no fault, and that was the right answer. Second problem involved a flow straightener upstream of a pump. It broke off, it went in the impeller, it jammed. Where that arrow is pointing to on the bottom right is the residual pattern that came from the diagnostic algorithm. That pattern happens to conform to a mechanical performance degradation of the pump impeller. And then we injected a 2% bias on the flow measurement, actually on the feed water flow measurement. Again, the pattern that you see on the bottom left there is the signature of a miscalibrated or uncalibrated flow meter. So we were successful for all 3 events they gave us. Okay, so that's the diagnostic part. Now I'm going to get into the sensor optimization business. Where do you put these sensors to get your maximal information? So on the left-hand side is the input deck that configures the optimizer algorithm. It tells you about the nature of the problem, how you want to optimize. Over on the right-hand side on the top is the flow chart for how the optimizer sequences through things. The information about diagnostics is in our ProAid code. I hadn't mentioned that previously, but basically that's communicating with the genetic algorithm, and it's basically just running through, the genetic algorithm is running through all sorts of different sensor populations. For each one, ProAid is rendering what can be diagnosed and what can't, and we have a cost function that we're trying to minimize, some stated diagnostic objective, and so we finally converge to the sensor set that gives us the things that we want to diagnose. So that's how that works. Okay, then we took this problem from East Coast utility. What you see there in the figure is the P&ID for the high pressure feed water system. So we took this system, we created the input deck, we had the genetic algorithm run with calling ProAid to optimize the sensor set. And so, again, it's what is the minimum sensor set to diagnose faults? Actually, we approached this two ways. We took the existing sensor set and we looked to see what we could actually diagnose. And then we ran the code to determine what a more optimum sensor set was to diagnose the same things. So those results are shown here on the next page. So what you see on the table is a column titled installed sensor set and then the optimal sensor set. And essentially under the installed sensor set, we have what we're able to detect in terms of faults and what we're able to diagnose. And we required that this new sensor set that we're about to design provide at least that specificity of the installed sensor set. And so the outcome was that, and there isn't necessarily a unique answer to this, but with 38 sensors, we can not only determine what the installed sensor set did, but we can actually determine more. So clearly, the installed sensor set was not optimum if you're trying to do condition-based maintenance. But of course you weren't, because they were just doing alarm and control. But it was interesting to look at a 1970 vintage plant and see just how useful the sensor set would be for condition monitoring. And the conclusion is it's not optimum. You can do things to improve on condition monitoring by reallocating sensors. Okay, so anyway, this problem demonstrates the importance of sensor type and placement when you're considering condition monitoring. Okay, so conclusions. We developed a virtual sensor capability for an engineering system based on the concept of the physics-based digital twin. We diagnosed blind faults in a pump motor set using utility data. We developed our GA-based optimization algorithm. We actually have it running on a cluster, 50 nodes kind of thing. We successfully applied our sensor algorithm to a couple of utility cases, which I just showed you. We were able to get physically explainable optimal sensor sets in reasonable run times. So future work, with our no-cost extension, we're going to press on. We're going to actually integrate two approaches that now exist. We have, classic data-driven incipient detection business, the MSET, the Sure Senses, the Prisms, and then our ProAid code, which does detailed diagnosis. So, the data-driven are highly sensitive, but they're not very good at locating the fault. They'll tell you there's an anomaly, but they won't tell you what particular component, and they won't tell you the nature of the anomaly. Physics-based digital twin in our work will give you a very detailed explained diagnosis, but there is a model in there, a physics-based model. It does have approximations, and so it's less sensitive. So the two of these put together are actually what utilities are looking for. We actually at Xcel Energy, they told us, well, we don't want two different algorithms, we just want one. Well, the strength in having one where you combine these two things is you'll get the advanced anomaly detection from the data-driven, and then a little later you'll get the physics-based. So you're really getting the best of both worlds by integrating these two, and that's what we're going to do in this current year. So we'll work with our utility partner to collaborate with them on having a deployable version. They'll provide plant data sets, and we'll just make the assessment going forward this year. Okay, so I did hint at where this work will go longer term. We want to leverage it for the end goal of maintenance optimization and asset management, and that goes into Dave Grabowski's presentation that you'll hear a little later. Basically, our work in this project provides the prior probabilities that feed into the Markov process model, and you can see the string of steps there. The second from the left is the ProAid, and then downstream of that is the Markov model optimization business. So I'm almost done here. We have a number of journal papers, conference papers, patent applications, and there I am if you need to contact me. And that concludes the presentation. Thank you.
Okay, thanks, Rick. Appreciate that. We'll be transitioning now.
Rick, Craig, I have a question.
Oh, sure.
So Rick, thanks for the presentation. On your long-term goal, you mentioned on the maintenance optimization. Are you aware of some of the works that Westinghouse has done recently under industry FOA?
Everybody is doing this problem, I have to tell you.
Yeah, that's what I'm saying. I just want to make sure that you're aware of it, so that.
Yeah, no, I'm aware of it. EPRI is doing it. Framatome is doing it, but they're all doing it to different degrees. Yes, and we've been talking to Westinghouse.
Okay, just want to make sure that you're aware, so that you can leverage some of the findings.
Just to make you aware, this is going on. It's EPRI, Framatome, and so it is pretty pervasive. I guess it's an indication of how important this problem is, that it's so many people working on it.
I agree. I just wanted to emphasize that they have real data and some of the real analysis done as part of the industry FOA work they did. So you might want to kind of leverage that and build upon that.
Well, that's what. Yeah, let me talk to you offline about how we might work with Westinghouse. Yes. Yeah.
Vivek, what is the scope of the IFOA for Westinghouse? I mean, it's sometimes redundant, but sometimes good to provide, project specific.
So the project ended this last fiscal year. So the scope was to integrate some of the future work that Rick is thinking to integrate with risk models, generation risk models, the predictive data-driven approach. So it is kind of along the same line. It has completed. It has all the information on a public domain. And I can make that available to Rick. So he can leverage that research.
Yeah, Vivek, but let me just make the point. I mean, we talked to Westinghouse. They don't have what we have in ProAid. They don't have a digital twin model. And so I know, well, I don't want to critique their work, but the business of, the prior, I think you need a digital twin in there to do that correctly. So there are going to be differences between our work, and I won't go into them, here.
Yeah, Rick, there's a difference. I'm just trying to say, just so that you take advantage of what they have done. That's what I'm trying to lead you to. That's what I'm not saying that they have done what you are doing or you are trying to do what. I'm sure they don't have physics-driven model. Just an advantage, something to consider.
Right. Okay. Well, thank you for that suggestion.
Yeah, I don't see any more questions. Craig, do you see any questions?
No, that I don't.
So we can move on. Thank you.
Thanks, Rick. So what we'll be doing next then is transitioning over to the design of risk-informed autonomous operations for advanced reactors. We've got a couple different presenters for this this presentation. I believe Dr. Goulet's got the first piece of the presentation. Looks like we can see your screen. So Michael, when you're ready, you'll take it away. And I don't hear you yet, so I don't know if you're muted.
Mike, you are connected. You can just share your slide now. because we are all watching your screen.
So Craig, it looks like he's on a Mac, so he may be having trouble with his mic and camera.
Okay. Well, then maybe what we can do is, I know there were a couple presenters. One of the other presenters.
Okay,
Yeah.
this is Yong Kang speaking. I can start the presentation. Please let me know how I share my screen.
All right, we'll get that transitioned over to you.
So, do you see my screen now?
Yes.
Which screen are you? I mean, I
see the presenter view, not the presentation. There you go. You swap
yes,
it.
I will switch the presentation.
Yep, perfect.
So, do you hear me well?
I do, yes.
Okay, great. Let me start the presentation for Professor Michael Goulet because he is experiencing technical difficulty now. Our project title is Design of Risk-Informed Autonomous Operation for Advanced Reactors. So this is a very top view of the project. So we are working to reduce risks from human errors during transients, including normal operations and accident mitigations. And the goal of the project is to demonstrate artificial reasoning to support operator actions. And in order to achieve that, we are developing the elements for the prognostics and response planning, operation actions, and some automated suggestions and actions. And the baseline element to support this kind of activities is developing a simulator for testing whether our newly developed algorithm is really useful for human operators' decision-making support. And up to now, what we achieved was for the prognostics, we obtained some data. I will explain a little bit more later. And we developed a Bayesian model for performing that prognostics and automated reasoning for needed response. We developed a risk reduction scheme and system metric optimization. We will have a detailed explanation later. And for the future work, because this project is entering third year, we will extend the scope of the prognostics. Currently, we have very limited data for this prognostics, so we will extend that scope. And the other two very important future steps are the advanced reactor model and integrating the techniques we developed up to now. So this is the milestone up to now. So as you can see, we developed signal processing schemes and decision-making support and detecting the degradation of the component of the structure. And we plan to submit some more milestone reports in coming third year of the project. So we will talk about the risk assessment of the signal processing, which will be processed based on PLC and both PLC and FPGA. And the final report will cover everything. The project will integrate all the technique we developed, including the Bayesian network and Markov decision process and other prognostic information processing with the target of the SFR. So this is the distribution of technical element we are currently addressing. The first part is the safety operation. That's, most familiar part, as you know well. So we utilize the relay simulation environment connected with Raven, which was developed by Idaho National Lab for the automated simulation under certain parameter uncertainty distributions. So we used it to generate data for the accident mitigation exercise. And currently we are working on Modelica based simulation environment development. So for the example system, we successfully finished that Modelica simulation environment development. For the SFR, including its BOP balance of plant, we are currently working on that model development. And we also, based on that Modelica simulation, we were able to exercise many non-safety operational issues. You know, the real lab is focusing on safety issues, but this Modelica is more general modeling environment. So we tried a couple of things, including the fuzzy logic development and diagnostics and the Markov decision process, which will be explained a little bit more detail later. And then we, on the right hand side, you will see the prognostics data collection. So after several trials with actual utilities, EPI, they were not very successful. So after that, we have a collaboration with MIT power plant, MIT Central Utility Plant. So we were able to get some of the signal they stored, and we found that can be used as a basis of these example trials. And we developed the Bayesian belief net model in order to process that kind of signal automatically. And that Bayesian belief net model will suggest whether this component is in a good stance or is in a failure state. So that first part is that system structure and component health status diagnostics. So mainly this part was performed by the MIT, but I will present for them. So this first slide shows you the vibration signal stored at the MIT's power plant. So as you can see at the top, you see the green line there. So we can we observe the visible difference between that green vibration signal from the other signals at the bottom. So those are the normal, the components in good condition, but the green vibration signal shows us a clue that this component might not be in a good state. So those signals are from the cooling tower fan motor. So because it is electrical motor, we believe this is the good start point of the application of our. So this is the Bayesian net developed for that kind of electric motor. So you know that this F1, 2, 3, 4, 5, all those are the possible faults. Actually, the F1 means unbalanced voltage, F2 means open stator winding, all those are the faults. And then it will be observed by E1, E2, E3, E4, something like vibration or heating or noise. Yeah, though they will be observed through that observable node, and we can categorize those faults into the electrical faults or the mechanical faults. So we will be able to update the probability of electrical fault or mechanical fault based on observables. So in order to do that, we used UNB-based program toolkit. As you can see, the probability will be updated like this. This is just an example. So when we observe something specific at the E1, E2, E3, E4 observable node, then all other probabilities will be updated, and then we will have conclusion, right? So electrical failure probability drastically increased, but mechanical failure, no. Electrical failure probability seems normal, but the mechanical failure probability drastically increased, almost certain. So that's how we make a decision. We are currently considering this, converting this kind of probabilistic or expert probabilistic, expert opinion, which are captured by the probabilistic distribution, and we want to convert this framework into the prognostics probability distributions, so that we will be able to predict how many hours this component can go and what would be the value probability of this component at a certain time point in the future. So that's what we are currently working on, and we also plan to extend the data collection coverage in cooperation with the MIT Power Plant. Buddy, this is your part. So Buddy from Oak Ridge is supposed to present this part. I found
Can
her
you
name.
hear me?
Yes, we can hear you well.
Oh, okay. Interesting. So you hit unmute on the computer, but it unmutes your phone. Okay, wonderful. Hello. Who has control of the slides? Could we go to the next slide, please? Oh, okay. Thank you. Yes. Okay. So I'm Birdie from Oak Ridge National Lab. The connection issues are resolved on my end, but have me a little flustered. So for the development of the Markov decision-making method and its demonstration, we focused on an example household heating system with 2 loops. And this example system offers similar structures and components, as well as availability of the range of possible actions that are in the primary and secondary systems of advanced reactors. The control logic developed considered competing objectives of maintaining the system within safety operating limits, such as trip set points. Okay. As well as the objective of continued operation of the system, possibly even in a compromised state. So this past year, we examined a loss of flow accident initiated by a pipe break. In the right leg, it's indicated in orange in the top right figure. So a schematic of the heating system is that top right figure, and then the green boxes are components that the operator has access to. The bottom left figure is a high-level depiction of the evaluated decision tree. It has many of the decision nodes omitted, but it's basic three-layer decision tree. And the system state evolution in response to the loss of flow accident and various corrective actions available is shown on the bottom right. And those results were generated using a transform model, a Demola model. So next slide, please. So we casted the problem as a Markov decision process. It offers a general framework for formulating sequential decision problems. And these problems are decomposed into 4 components: state space, available actions, dynamics models, and a reward model. And we're often, you and I often think in terms of immediate rewards, which are associated with your current system state and an action taken. However, the MDP solution approach, the objective is to maximize the long-term reward. So the solution approach is a dynamic programming algorithm, which is a recursive approach that breaks up this longer sequential problem into simpler subproblems that look in a greedy way at the immediate reward, but it gives rise to the Bellman update equation. So For the full solution, you're not just looking at the immediate reward, but the expected reward for each state taking each action and considering the long-term possible evolution of the system, as well as your perturbations on the system. So next slide, please. So this slide is a bit of a smattering of the results, but I want to highlight that the dynamic programming approach, you obtain the full expected cost or expected reward table that is shown on the bottom left. So that was used to find the correct throttling of a water inventory backup tank in response to our system's failed loop scenario. So what we find is that this was consistent with human logic. So this is kind of the first check of the method. Can we reproduce human logic? And we had success there. So this expected reward table is pre-computed offline, and it can be stored in memory and then called during online operations. So with the MDP approach, we're shifting the human effort from the traditional burden of developing complex pseudocode in the form of event-based operating procedures. Instead, the effort is primarily focused on developing dynamics models and reward models. And these reward models are really key in developing the control logic because it has our objectives embedded in the model, and it gives us an opportunity to engage and iterate with stakeholders and operators in order to shape the control logic in a way that is consistent with our human logic. So after that, the computer effort is expended in solving the dynamic programming control logic. So I think now it's back to Hyun. Yes.
Okay, thank you, Buddy. I didn't tell my name when I started this presentation. My name is Hyun Kang. I'm from RPI. I will finish this presentation portion of the decision-making support with the dynamic Bayesian network. So the point of our research was utilizing all advanced algorithms, including artificial intelligence reasonings, in order to support the human operator decision making. The problem comes from that communicatability. So if we cannot explain where my plant is and where we want to bring my plant, if we cannot explain it to actual human operators, we will not be able to support them. And as you know well, on the left hand, do you hear me well? I got a warning that
Yeah, we can hear you.
I have network. Okay, then let me continue. So I got a system warning. Okay, so as you can see on the left-hand side, something like a decision trees has wonderful explainability, but it has very limited learning performance. If we talk about the neural networks, it has wonderful learning performance, but we cannot actually explain what physically the state means. So what we did was summarized on the right-hand side. So you can see internal structure modeling, we want to be more mathematical and graphical. So we utilized multi-level flow modeling to express the physical relationship of the components in the system. And we utilized mathematical framework to here, the dynamic Bayesian network. And then in order to decide number of beans in one system state, we utilized support vector machine, which is a kind of machine learning or AI-based approach. And then we wanted to utilize graphical illustration by using the decision trees. So as you can already catched from our presentations, we wanted to stay at very mathematical representation of the actual world so that we can find which data should be improved or what was the cause of that kind of suggestion. And if there is any error, we can trace back and fix it easily. This is how we utilize the MFM and dynamic Bayesian network for this purpose. So first, on the left-hand side, you see the PNID of the system. This PNID will be converted into MFM model. You can see at the center. That's kind of most likely automatic conversion. You don't have to have special skill to develop this MFM. So you have PNID, then you will automatically have MFM. And then that MFM model will be used as a state of the Bayesian network. We call it dynamic Bayesian network because we consider time responses. So we will have a Bayesian network at T1, and we will have same thing on the T2, T3, T4. So we can capture the dynamic behavior of the plant in that way, and everything will be mathematically treated. And this slide is for explaining the state space discretization. As you know, if we want to keep the very high level of the resolution, we should have very fine meshes. Then fine meshes will cause big issue to us because this is dynamic response calculations. So number of meshes will be multiplied whenever time goes on. So we will need to handle huge computational challenges. So in order to reduce that issue without losing much explainability and much resolution, we develop a new system space discretization methodology. So first step one is using physics-based partitioning, and second step is using machine learning-based clustering. So considering the data size, we develop a hyperplanes for that. And then last step, we will reflect component status, something like valve on, pump on, or the heater on. That information will be coded with different color. Then we will have limited number of cells only, without losing too much resolution and without losing the physical meaning of the data. And this slide is for explaining about the integration of the possible integration of the methodologies we developed up to now. So we commonly use Bayesian networks. Actually, the Markov decision process also utilized conditional probability. So mathematically, it can be expressed on the right-hand side. And what I explained, I mean, dynamic Bayesian network can be summarized on the left-hand side. So as you can see from here, we are actually doing the same thing. By using the Bayesian dynamic Bayesian network, we are calculating system risk based on state probability. That state probability was calculated based on conditional probability, series of conditional probabilities. MDP, exactly same. They calculate state value, so-called reward, right, based on state transition. That state probability was calculated based on the series of conditional probabilities too. So we're gonna integrate them into one framework in the third year. That's what we aim to do, and we will keep that explainability, and we will focus on the utilization of that information for the advanced reactor. We are currently developing the SFR model, so we will integrate them and we will demonstrate how this kind of techniques can be used to support human operators' decision making. So let me conclude our presentation here. So what we did up to now was, first was the development of Bayesian network diagnostic model by using the MIT power plant data. And we developed a two-flow example system simulation toolkit
Thank you very much. Appreciate you jumping in and taking over the presentation there. So apologize to Dr. Goulet for technical difficulties, but we appreciate the update. I don't see any questions. Again, we'll be having the panel sessions in the afternoon. So if you think of any questions on this topic, please send them through the chat or question box. We can ask them now. We're running just a little ahead of schedule, so we have a moment for questions. Otherwise, we'll transition over to Vivek. So thank you to your team.
Great. If there's no questions, then just since I have a minute, or we have a minute here, I would like to remind people of the one-page summary that was requested as part of the annual review. So there's still a few folks that haven't done so, but together with your slides, which as we have mentioned a few times, will be publicly available on the ASI website. We also want a one-page summary to be included in the FY21 program accomplishments, which is our high-level communication documents that we distribute. So everyone that hasn't done so, please do provide this one-page slides. This relates to direct research and competitive awards. So most of the R&D that we're discussing, we are not going to include the industry-related projects. Some of them we will be seeing later in the afternoon, just to be clear. But all the R&D projects should send this one-page summary. So if you haven't done so, please send it, and by the end of this week, so we can collect. Thank you.
Okay, thanks for that reminder. Hi, Vivek. Appreciate you joining us today. Vivek is going to cover his analytics at scale of sensor data for digital monitoring in nuclear plants. So thank you, Vivek.
Thanks, Craig. I hope you can see the slides in full screen mode, presentation mode, and hear me okay?
Yes.
Okay. Yeah, thanks again. As Craig mentioned, this work was under the competitive awards, started in fiscal year 2018. And it's we have a no-cost extension for this project to complete this fiscal year, but most of the work is done. The topic of the presentation is analytics at scale of sensor data for digital monitoring in nuclear power plant. So we can go to the next slide. Yeah. So the scope of this research, when it started, was to develop to advance the online monitoring and predictive maintenance strategy in the nuclear power plants. And this is more focused on the existing fleet rather than the advanced reactors. But what we find is some of the research development that we have done under this project can be transferred or can be leveraged by the advanced reactor community. So that the existing fleet can improve their performance, especially in terms of efficiency gain and economic competitiveness. So when we start with this as a scope, we had 4 major objectives. As sensor modalities was becoming an important question, we have lots of hardwired sensors. Wireless sensors was becoming a question of concern, of interest. So we started this project by doing the techno-economic analysis of wireless sensor modalities, very specifically vibration sensors. Within the year one, we have published results, and we just recently got a journal article out of it. And in the following year, second year, we were more focused on working with a nuclear power plant site, 2 sites basically from Exelon, and getting the data on their assets, and develop diagnostic and prognostic methods. Once we do that, we also looked into the visualization scheme and then the validation of the technique. So this is a very comprehensive team that includes national labs, industry, and Electric Power Research Institute. The technical point of contact for this project is Rick Willem from Argonne National Lab. So within INL, I'm leading the effort, but I'm close. The contribution comes from Nancy Lieback. Cody Walker is a postdoctoral researcher who's working on a machine learning algorithm validation of this approach. Kaushik A. Manjunatha was a postdoctoral researcher who worked on the wireless sensor modalities and the techno-economic analysis. From Oak Ridge, we have Pradeep Ramaholi. From Electric Power Research, we have Mike Taylor. And from Exelon, we have Charlotte Geiger. So I think so I have introduced the overall scheme of the approach here. So it's going from sensor all the way, that's reason for the data, to all the way to the decision making. And visualization is a very important piece of the decision making, and we should not ignore that. Whether it's you are doing localized visualization of the information or your centralized visualization of the information. So the sensor, in the first part, we have talked about all the sensor modalities, wireless vibration sensors, and its installation on the balance of the plant asset. In the second side, once you have the sensors, new sensor modality installed, we also have existing data from number of plant sites, which plants have been collecting for over years. Like it goes from technical specification, maintenance data, plant process data, and historical failure records. And all this information needs to be integrated and to understand a very good, to develop a very good diagnostic and prognostic model, and requires very in-depth data analysis. So yes, this is a purely data-driven approach, very contrary to Rick Willem's physics-informed approach. But yeah, it is a data-driven approach. And once we get this information out, we have to validate and verify the approach. We are doing that, and then visualize the information. So techno-economical wireless sensors. The wireless sensors are becoming pretty much very a go-to sensors modality in nuclear power plant because the cabling cost is high, and there are other factors associated with wired cables, wire sensors. But in the balance of the plant, wireless sensors makes more sense. But the challenge here is there is different types of wireless sensors. They communicate at different frequencies, uses different resources, and used for different purposes. So there is no one-size-fit-all solution that you can apply. So you have to develop an architecture that can accommodate the different wireless sensor modalities that a nuclear power plant would be using, and whether you're going from Wi-Fi, 5G, LoRaWAN, or Zigbee communication. It all needs to be integrated because they are all transmitting at different frequencies. So this is the architecture that we propose under this research, which uses the distributed antenna system as a backbone and consolidate this information. And we just recently had an article published in a journal on this. The second, and going to the maintenance, one of the milestones that was completed this fiscal year is on the development of diagnostic and prognostic models, and also leading to the preventive maintenance optimization strategy. So in this case, we worked very closely with the 2 Exelon plant sites. One was a pressurized water reactor, and another was a boiling water reactor. We obtained, and for both the plant sites, we used condensate feedwater system, common system across both the plant sites. We obtained information on the work order, plant process, maintenance record, and using that information, we were able to inform the development of diagnostic model. And once we were able to develop the diagnostic model, we kind of also looked at how this model can be used for forecasting in future the trends of the signals that are of interest. I'll talk more about them in the next few slides. At the same time, we are also looking at, before we transition to predictive maintenance, there's a large amount of effort done on preventive maintenance optimization, preventive maintenance. How can we optimize that? The one way of optimizing is by looking at how we can change the frequency at which these preventive maintenance optimization is done. The preventive maintenance optimization is very periodic in nature. It's labor intense and sometimes includes taking the plant offline, and which leads to loss of revenue. So in order to optimize that, so that the plants don't have to take as many turns on doing preventive maintenance, what are the candidates? So we looked at those healthy components under evaluations like condensate booster pumps, motors, and look at different kind of PM activities they do, going from vibration measurement, oil analysis, and what are the frequency of this. And then we compared that frequency with EPRI's preventive maintenance database, and what recommendation they have. And based on our analysis of diagnostic, if that particular asset has not seen a failure in the past or any degradation, and there's no need to go and do another additional maintenance on that, because if you do additional maintenance, you might risk in bringing additional false injection. So these were the few candidates that we brought, like pumps and motors, as good candidate and very specific activities as a part of preventive maintenance extension. And so that is the major motive, one of the major outcomes that was summarized in this. That's one of the milestones that we submitted this year. The second milestone that we looked at is the data visualization to support decision making. And so eventually we do all this good machine learning approach, whether it's data-driven physics or hybrid, we get good results and present the results. So the question becomes, who is going to look at that results? It is basically very user-centric, right? So the results that you generate should be usable from the visualization point of view. Just by showing trends to a stakeholder who has just 5 minutes will not make him very comfortable without detailed explanation. But for a system engineer, those trends makes more sense. So depending on the user you're trying to present, your visualization should be adapted. So that's why the usability and of your visualization is important. So the goals that we focused on this is usability, saliency, and error prevention. And usability, again, the user should be able to use that information that you extracted from all the data. And saliency is like, what is the important part that a user need to focus on it immediately. And error prevention is, we should not be miscommunicating the information. It's like right information at right time in right format and to the right user. So some of the visualization recommendation as part of the study was to highlight the consequential information. From the data, we get lots of information, but what is the critical information that a user needs to see on your screen and to make a very informed decision? We can group the consequential information. And it's like, if a vibration is changing, is there a change in the flow, or is there a change in the temperature of the bearing? It's a high consequence. But it also is another grouping is related. For example, the gross load. The gross load is affected by many other parameters. So what is a good way of showing that a gross load is changing because a particular system is changing? That's a grouping of the information of related type of information. And when you cannot develop user-centric visualization for each user in mind and have a different dashboards. So you need to have a very unified dashboards where you can navigate based on the user needs and requirements. So that navigation of information is important when you do the visualizations. And then we are all doing diagnostic and predictive analytics, so which we should be clearly say which is the actual signal that is coming from the plant and what is your model, your machine learning model is predicting. So you clearly delineate that so that the user is able to understand, okay, this is my true signal and this is the estimated or the predicted signal. And when you can tie that with other information. There are lots of tools that we surveyed and that could be used to develop this kind of visualization scheme. Okay. So the third important aspect of this year's accomplishment was the validation and verification of the models that we have been developing. We never tend to do this kind of validation verification. We are very happy with what the model is predicting. But to do validation verification, we needed an independent data set. The data set that does not comes from the existing the data that was used to model develop the model. So in that case, Electric Power Research Institute provided us with good 3 independent data sets, 2 on the PWRs and 1 on BWR. So I think the BWR came from Exelon. We kept that, and then PWR came from the Electric Power Research Institute. So the data was from main turbine system, steam generator and feed water system, and then for the BWR we had the condensate feed water system. So all this data was given to us, and the parameters that we were focusing on the main turbine was the thrust bearing temperature that we need to validate the approach. And then for the second system, steam generator, we are focusing on the flow and also the bearing temperature. And for BWR, we were bearing on the pump bearing temperature. So there's one. So these were the information that we were using to validate the approach. But one thing I have to make sure that the validation verification is not saying that here is one model that I have and it can go and do the prediction or diagnosis across all the three systems. It's more on the methodology, how you take it, how you develop going from data to all the way to the forecasting, and what steps you need to take. And given that you have different systems with different measurements, and how can you kind of generalize that approach or validation verification. Then going, so that was the thing. And the two main approach that we were using for validation verification was a long short-term memory neural network and support vector machine. And so LSTM is a very well-known recurrent machine learning neural network technique, and that maps the input and output based on some of the historical knowledge, and it creates and through memory cells. That's the important one. And support vector machine is a global optimization technique that is based on kernels that transforms the input space into a high dimensional feature space, and then identify the support vectors that are critical to decision making. And so these were the two major approaches that we used to do validation verification. And we used 1 hour ahead prediction to 1 day ahead of prediction. So this is 1 hour to 24 hours for the forecasting. Okay. So one of the part of the development of this model is a feature selection, because from the plant we have lots of data and with lots of information. So we have to understand what particular feature, whether it's temperature, pressure, flow, or the change in gross load, or is salient and to predicting to the variable that we are of interest in predicting. And so that is the important part. So how do we do the feature selection? Because that helps address one cause of dimensionality in machine learning, and two, it also provides some explainability of what is making more sense going forward in predictive models. So one of the important aspects that we used in feature selection was Shapley additive explanation approach. It's an approach where you take a base model, which could be a constant of the variable that you want to predict. Say on this figure, you can see this is a base model. This is the expected function, and you want sorry, I'm going in a wrong direction. And you start adding one by one features. The feature could be the temperature, and then how that feature moves your prediction more towards a real value. It could move you towards or against that. And it also generates a local explanation model for you, surrogate explanation model that provides explanation, what's the level of contribution, and how if you fiddle with that input a little bit in terms of changing its value, how resilient it is. So it provides that kind of explainability and shows you how that feature is contributing towards your prediction. And so that is one thing that we have used as, and it can go towards explainability part of machine learning. And random forest was used as to generate the Shapley values, and dynamic thresholding was used as part of that. And the table on this right shows that the turbine speed is our target variable that we use the variable itself, so it's obviously the most important variable. But other than that, there are a few other variables that are important to predict the future value of the turbine speed. And once we get to a point where it's 1 order of magnitude different, we drop that, which is a shell expansion here. It's an order of magnitude different from other values of importance. So we can drop that. So it will add minimal information to your prediction. And so that explains why we should not be considering the shell expansion as a feature. And also it also addresses the concept of dimensionality. The third, and that's the milestone we are working on, and we finished and submitted just this Monday. But work was done mostly in the previous fiscal year. So while we're developing the forecasting model, we use 3 approaches. One is the direct approach, forecasting approach for 1 day ahead prediction. It means that you have the data, you sample the data, and do a direct one time 24-hour prediction, and then move the data and do another 24-hour prediction. So that was computationally less expensive approach, straightforward. Then what we do, we went and did the recursive approach, where the 24-hour prediction is done in increments of 1 hour time step. And so before we get to 24 hours, we do 1 hour ahead and use that predicted value as an input and do 1 hour ahead. But this from our approach had a error accumulation issue. So at the end of the day, we'll have an accumulated error, which would lead to a much prediction with a higher variance. Then we had a direct recursive. It's kind of a hybrid of both the first approach, where we would do a 1 hour ahead prediction with model, and then optimize that model based on the predicted input, then do 1 hour ahead prediction, and again optimize that model. So basically you're generating a step of 24 models. It's computationally expensive, but at the end of the day, it kind of comes very close to direct approach. So we wanted to show that the different approach of forecasting model and the robustness of each one and the merits and demerits. Right. Again, LSTM and SVR were used to predict 4 parameters here, and the 4 parameters, I'll talk about them in the next slide with the results. With the 1 hour prediction and 24 hour prediction. And we use 10-fold cross-validation approach to achieve the root mean square error that we are reporting. And so overall, if you look at the results, it will look like SVM has outperformed LSTM. But you have to make into consideration LSTM has so many other parameters to optimize that if we do the optimization of LSTM and it might match the SVR or even better the SVR prediction. And so at this point, the result shows SVR is better than LSTM, but you have to keep into consideration that LSTM architecture needs to be optimized. Nice. So here is a quick result on 1 hour to 24 hours prediction. And so the blue curve here shows, I apologize for the lack of resolution here. The blue curve shows the actual value, and then you have SVR's a 1-step prediction, LSTM's 1-step prediction, and SVR's 24 and 24 LSTM self-prediction. So what's more important is the table on the right. So you look at we are not only reporting the mean root RMS value, root mean square value, but also the standard deviation, because we did the 10-fold cross validation. And it's very important when we do the validation verification to report the variance in the result. So on average, for 1-step ahead prediction and for 24-hour prediction, SVR seems to be better performing in terms of RMS value. And that's the 4 parameters that we did the validation verification on using these 2 approach. So and some of the external visibility of this project is we did get a publication in the wireless person communication on the wireless architecture. We had 2 conference presentation in the nuclear plant instrumentation control HMIT conference, human machine interface conference, which was in a part of the American Nuclear Society summer meeting. And then we had a news article on this topic and published. So that's some of the external contribution of this project to the scientific community. How do we, what's the technology impact? Is like, when we set out with the aim to advance the online monitoring and predictive maintenance. And I think so we are achieving that through this project by showing how wireless vibration wireless vibration is an important addition to the existing fleet. What are the economic values and what are the technical values? How do we balance the economic and technical challenges wireless vibration? It's kind of summarized in that effort. And so that enables online monitoring across different plant assets which did not have wireless vibration sensors, which was previously done through manually installed vibration sensors. So we are moving that paradigm from periodic manual vibration measurement to real online monitoring of vibration on plant asset. So the predictive, the machine learning models, which is totally data driven, has shown that you can take data from different scales, whether it's coming from work order, plant process data, historic maintenance, can integrate that information usefully and develop machine learning models. And then also the validation scheme of those models has shown to be very resilient. That's how we are advancing the state of the art. Visualization is something that people have not very specifically focused on it, and it has been part of the research. But we have to show that how you have to develop a user-centric visualization scheme for someone who's sitting in a control room to understand, or someone sitting in the remote monitoring center, that's something that Craig pointed out would be very, very useful for advanced reactors, because you're not going to have hundreds of employees or staff members working on a nuclear power plant on site for advanced reactor. That's not the vision. It's minimal staffing, more of technology driven. And so that's information visualization is important. How does it support DOEs? Yeah, within the light water reactor, we want long-term operation of the existing fleet. Right? If I have to be more bold, I can tie this to net zero effort of DOE's mission. And because the nuclear is going to be a critical part of the future of energy system. And then the maintenance strategy. Right? When we move transition to advanced reactors, we are not going to look and work on the preventive maintenance strategy. We want to look at the predictive maintenance strategy. So this kind of lays the foundation of how do we do predictive maintenance. And this has been brought about by previous speakers also. Rick pointed out towards predictive maintenance needs. Right? And many other projects are working on that. Impact of the nuclear industry, it helps the existing fleet to maintain long-term economical operations. They are 100% safe and no concern about their safety, but just to make sure the economic operation of the existing fleet is achieved. Commercialization, we would work with our collaborators at Exelon to transition this. As part of the last fine milestone, we are looking at what kind of platform that you need to be considering, what are the requirements, so that all the transition from data to visualization is on one common platform, whether it could be a cloud-based platform or a local platform or a nuclear power plant or the existing platforms they use. So we need to evaluate that and going forward. So that would be the part of the next year's one last milestone part of this project. So in summary, we have demonstrated how wireless vibration sensors are important in economic analysis, develop diagnostic prognostic model. I've used Shapley value to explain some of the important features. We are also looking at variance in inflation factors, another method that addresses the multi-collinearity issue in the plant variable. Yes, so that's a summary, and that's my contact information, and if you want to reach it out. But as a part of the future work is more on understanding how we take from data to visualization on a platform level, and that can handle this AI infrastructure. So basically, I'm looking at like AI infrastructure for next few months before we complete this project. Right, and there are a few additional journal articles in the pipeline to be submitted. Right. So with this, I'll complete my presentation. Sorry for taking 50 seconds more than allocated time. And if I have any questions or comment or concerns, let me know.
Thank you, Vivek. Actually, my agenda looks like the next presentation starts at 1:45, so I think we're running a little ahead. So we got time for a question here that's been posed, and the question is largely around the quality of data and how the data that you're getting is impacted by things like environmental conditions or erroneous sensor readings. And curious to know if you've considered that and have a comment on that type of question.
Oh, definitely. So the data does not come with issues. So there's always data with outliers, data with missing information because the sensor was out, or the data system that was collecting that sensor the information was not functioning properly. So that's a huge part of data pre-processing effort that we do as before we dive into developing the machine learning model. Yes, the data comes with issues and challenges, and data analysis is a big part, and very specifically data cleaning. We use a different statistics approach to understand that this data that we are inputting into machine learning is clean, reliable, and captures the information. And sometimes when we don't have that information, we do reach out to the plant engineers to provide more insight and why the sensor information is behaving this way. And that's sometimes they can make us aware of the operation logs, the change in operation profile the plant was making at that time. So that might not be related to any of the environmental conditions, sensor fault, but it's just related to the operation of the plant. So that kind of interaction helps us understand the behavior of the sensor. Okay. I hope it addressed the question.
I think so. I think you know, that's one of the bigger challenges with any kind of data-centric approach is quality of that data and how to manage that data. And so that's obviously part of that process. So appreciate your insight there. Yeah, so I don't see any other questions. So thanks, Vivek, for sharing your information. Again, if the audience comes up with any questions for any of the presenters, please feel free to enter those into the question box. We'll present those to the panel as well if we don't get to it during the presentation. So thanks,
Hey, Craig.
Yes.
Craig, I'm sorry. I know you're trying to fill time in. I know Dave's about to start. I did have a question for Vivek. Do we have time for that question?
Is it the question about the data?
No, well, it's related to that. So this is Rick Phillum. So I know when I talked to a particular utility, I won't identify them. This is, when we were in the process of formulating our proposal, they said we would like to see physics-based models in our algorithms. We have the MSET, well, I shouldn't name names, but we just don't get reliable output from these data-driven algorithms. They're subject to operating point, sensor failure. They're not robust with respect to change in the heat sink. I wonder, you're working with Exelon. In fact, did you get any feedback from them? I mean, they have their PRISM technique. I mean, were they advocating for physics-based models? Like, because a lot of those problems can be solved by physics-based models. I mean, I don't know how you can tell the difference between a component failure and a sensor failure if you don't have the physics in there. So I'm just curious, what did the utilities you're working with have to say about physics-based? Did they have any remarks?
Okay, so they didn't have a specific remark on any physics-based approach versus we never discussed which is better, physics or data-driven or hybrid, and so that was never mentioned. But I understand the concern that that's a very good challenge of delineating the sensor failure versus the fault, and that's where I think so the other parameters that are correlated or that provide additional information are useful to understand whether it's a sensor failure versus an actual fault. Not in this project, but in other projects, we have kind of addressed that through data-driven approach.
Yeah, of course, and tell me, Craig, when we need to move on. But the thing is, you have a limited number of sensors, and you don't necessarily have the over-deterministic sensor set, right? I mean, if one sensor is going bad, it isn't necessarily reflected in the other ones. I mean, it kind of depends on how you interpret the data. If you have a physics model, you can interpret that. The other thing about the physics models, it creates virtual sensors, so you actually have more information. I don't know if I don't think this is generally recognized, but I think it is an important point. Just we're there with data-driven algorithms right now, and there's just so much more you can do if you include process information. And I'll stop there.
Yep, I agree. Physics provides valuable information. That's good, but virtual sensors, I beg to little differ here. Does not always require to be physics driven. There is a literature on the virtual sensor that also says that a virtual sensor can also be derived from a data-driven approach, or a purely physics-based approach, or a combination of both. So to make a claim that the virtual sensor only will come from physics is a little bit, I think, so challenging for me, because physics is important. I'm not saying physics is not important, but yeah, there's lots of research that can be leveraged around virtual sensors.
This is a very good debate for later. I think it is one of the key. Well, I mean, and at the end, it will be a hybrid approach, but it is an important conversation that we should have on data-driven approaches versus physics constraints. And I know that I would like also to hear the opinion of universities, for example. Both MIT. We'll hear from you soon, but I think it would be interesting to understand also the more the less nuclear related side of the house and how these applications in other industry are being pushed forward, because obviously it seems that a purely data driven approach is actually being used elsewhere, right? So is also important to capitalize and take a look how that works in other applications. It's an interesting conversation. There's obviously reluctance in the field of nuclear, particularly then if we start discussing licensing and how can that even be used. So it's a good conversation to have. At this stage. Obviously, at the end, anything that moves towards maturation will likely have a hybrid approach, right? That's where we are. But at this stage, it is important to see the difference, and I don't think anyone should be shy in defending his own approach to things, because they're both good approaches, and it's more important to actually enhance or make it evident because that way we have a better understanding, right? And we can then move on to optimize that in a hybrid. So there has to be advances of purely data driven, right? Because everyone's using that. So there has to be something there. It's more important for me now to understand what the advantages are, what the difference are with respect to the physics approach that we are more accustomed with, so that we clearly have on the table, how then we are going to merge it in a mature, maturing this in the path forward. So I encourage everyone to bring this up again when at the end. These are good conversations to have at the end. In the last 2 days, we had the same type of fruitful discussion at the end, and it probably leads to follow up in both cases, things that we want to follow up on the optical and the acoustics. And so this, I think, will be another good outcome of the conversation. Keep that in mind when you're presenting. I would like to hear from everyone on this, and let's discuss this again at the end as a wrap up. Thanks for the contribution, Viva.
Thanks, Pattrick. Thanks everyone for the questions.
Okay, thanks. We'll be transitioning now. Dave's on, so thank you, Vivek, and welcome, Dave. Dave's going to be presenting out on the cost-benefit analysis through integrated online monitoring and diagnostic. So Dave Grabauskas is from Argonne, and you're ready. We can see your screen.
Okay, thank you. Can you hear me okay?
Yes. Thanks for joining.
Great. So I'm Dave Grabauskas. I'm the manager of the Safety and Risk Assessments Group at Argonne National Lab, and I'll be talking about our project on cost-benefit analyses through integrated online monitoring and diagnostics. And also thank Rick for earlier giving a bit of a plug to this project too, and how it's somewhat of a continuation from his work concerning ProA2, which I think you'll see as we go through this. So in terms of the project goal, there's really two pieces to this. One is, and I should say our major focus is advanced reactor economics. So on one side, we're looking at optimizing the reactor sensor network during design. So how can you have a minimum sensor set, but get the most information out of it? And then number two, once you're operating, how do you do intelligent asset management decision making by leveraging that information you're getting from the sensor set? So the participants, this is a collaboration between us at Argonne, Ohio State, and Framatome. At Ohio State, this is Professor Carol Smits and her students and researchers. And then at Framatome, our current co-PI is Pascal Bratany. So this project started in FY20, and we're currently entering the third year of our project. So a real high-level overview of the project here on the right-hand side. You can kind of break it down into those two pieces based on our objectives. One would be during the design phase of your advanced reactor. We're looking at, well, how do you optimize your sensor network design so that you have a minimum set of sensors? And this could be based on different criteria, such as the cost of the sensors, reliability, things like that, which I'll talk about in a second. But you can still ensure that you have the diagnosability of the key faults or events that you want to see. And we're doing this through a combination of ProA and another tool that I'll talk about. And then once your plan is actually built and operational with this sensor set, how do you utilize that online monitoring and diagnostic information to create what we're calling a real-time risk profile of the plant? And we're looking at risk in two aspects here. One is from the traditional safety aspect, so using a probabilistic risk assessment, but then also through an economics or generation perspective. And this is done through a generation risk assessment, which I'll also talk about in a bit more detail. And then once you have this real-time risk profile, then you can use the information from it to look at different operational options and try to optimize, do the cost-benefit analysis to determine what is your best strategy operating the plant moving forward. So a real high-level picture of the schedule. So in FY20, what we were really doing was looking at these different tools that we're integrating, the different capabilities that we're integrating, figuring out the process and the flow. You know, where do we need new capabilities? Where can we leverage what's already there, like what we're doing with ProAid, and developing the linking strategies. This year, or the year that just ended, FY21.
Hey, Dave.
Yes.
Sorry to interrupt your presentation. I think some individuals in the audience, they're only seeing basically a small slice of your slides. Do you mind exiting out of PowerPoint and then going back in? Maybe that'll correct the issue. And basically, it looks like it's zoomed in only on a portion of your slide.
Oh, okay, yeah. Give me I think I may know the reason here.
Sorry to interrupt your presentation.
No problem.
I was getting some questions in the chat.
Okay. Can you see it now, or a white screen?
It looks like a white screen to me. Craig, do you mind chiming in as well, just to get a second opinion on this?
Thanks. I'm just seeing white as well.
Yeah.
Okay, let me try.
Okay, we can see your desktop and we can see the PowerPoint application.
Okay. Let me try. Okay, how's that?
Oh, that looks good. Same, Craig, can you concur?
Yes.
All right, yep.
Oh,
So,
my apologies. Had it in a windowed view.
Okay, apologize for interrupting. Thank you.
Oh, no, thank you for catching that. Oh. So, as I was mentioning, here's a real high-level overview of the project. This past year that just ended, FY21, we've really focused on instituting those new capabilities that we've outlined, defining the linking strategies between these different tools that I'll talk about, and then also selecting a demonstration analysis, which will be the focus of FY22, where we'll be finalizing some of these methods and tools, because there's still a couple options we have, and then completing a demonstration analysis showing how this all works together. And then obviously publicizing the findings and results. So in terms of technology impact, again, what we're really focused on is economics of advanced reactor operation. So advanced reactors are the economics during design. So how can we minimize the cost of the sensors, or say systems penetrations, things like that. And then during operation, making the most out of the diagnostic information to inform the asset management strategy. We're also trying to take tools and methods that have been developed by different DOE programs. As Rick mentioned, we're utilizing ProAid, which is being developed under NEAT. Also some methodologies that have been developed under ARPA-E, and some risk assessment methods we've developed under the Advanced Reactor Technology Program to put it together into this bigger approach. And we're also working directly with Framatome, an advanced reactor vendor, looking to institute this process. So in terms of results and accomplishments, I'll kind of start at the beginning of the methodology and work my way through. So starting with the design phase and the sensor network optimization, we're using two kind of different tools here. One, we're using the integrated system failure analysis method developed by Ohio State, the ISFA method. And this is a methodology to create a sensor network design based on the capabilities that you need. So you pre-describe the different faults you want to be able to identify. And with some of physics knowledge of the system, it can help optimize your sensor network design. But what we've done as part of this project is expand the capabilities of ISFA so that there's new optimization criteria you could utilize. And you see a list here over on the right-hand side. So say the cost of the sensors, reliability of the sensors, functionality of the sensors. And you could even do potentially a multi-criteria optimization too, which anyone doing an optimization problem knows that can be a very challenging problem. So to go along with that, what we've also done with ISFA is looked at new optimization algorithms to help speed up this. So both evolutionary algorithms and greedy algorithms that would be conducive to these complex multi-criteria optimization problems. And then the way we've linked this to ProAid is, while we have ISFA doing the optimization of the sensor network design, during the design phase, we would also use ProAid as a validation to make sure that ProAid would be able to properly utilize or leverage that sensor network design during optimization. So it's an additional check on the design being developed by ISFA. So now once we get into the operational phase of the reactor, here's where we would be using ProAid to do the actual monitoring of the reactor. And as Rick mentioned earlier, ProAid combines sensor data and physics models to diagnose plant conditions. And so we're building off the accomplishments of that neat project and then looking at, well, how can we use the information coming out of ProAid? And the way we're using this is to actually update the Markov component models that are in our risk model, our PRA, our GRA. So Markov component models, we have a very simple version of one here on the right-hand side for a pipe. You have different states that the component can be in. And for each one of these states, you have a different probability that the component is in that state currently. And then you also have transition rates, so that the likelihood that the component would move from one state to the next in some future time interval. So a pipe might currently be healthy, but it can get a small leak or it could get a large leak. And there's some transition rates going between these. So what we can use the information from ProAid that's looking at the plant right now, and we can update the probability of us being in each of these states. And we can also potentially even update the transition rate. So how likely would it be that we transition to one of these new states in the future too? So we have a couple of deliverables that we published so far on how we're linking ProAid to these Markov models that we use within the risk profile. So in terms of the risk profile itself, we use these Markov component models as kind of the base of the risk model and then build up from there. I mentioned earlier, we're looking at both a safety aspect and a generation aspect within our risk profile. So in terms of safety, we're using probabilistic risk assessment, PRA, which looks at the likelihood of different event sequences and the consequence of those event sequences. Typically for advanced reactors, those are consequences in terms of offsite dose. So if there was an accident scenario, would there be an offsite dose? And if so, what would be the magnitude? So what we're using for this part of the analysis, we're using the licensing modernization project, the LMP approach. For those of you who have been up to date on advanced reactor licensing, probably are well aware of the LMP project. There's a lot of discussion right now in the NRC about the development of Part 53 and how it intersects with LMP. But one of the central pieces of LMP and what's important for this project is this frequency consequence curve over on the right-hand side, where you take the potential event sequences that can happen at your plant, the potential accidents, and you plot them on this frequency versus consequence curve. So how likely are they and what are the potential consequences of them? And in essence, you want to stay within this consequence target as part of your licensing case for your reactor. So this is really useful for us because as we look at the different potential operational plans moving forward, each one of them will affect the likelihood of different event sequences. If a pump fails, it might have some impact on these event sequences. So by using this frequency consequence curve, it gives us an allowable operating envelope or an allowable operating window that we can look at different operational plans and make sure we stay within the bounds of our licensing case in terms of safety. So that gives us a hard constraint about what our future operations could do. But then what we actually optimize on is the second piece here, this generation risk assessment. So the generation risk assessment is in a lot of ways identical to a PRA, but the consequence we're looking at is not accident sequences and offsite dose. What we're looking at are event sequences that could potentially lead to a plant shutdown or a plant derate. So a piece of equipment goes out, maybe we have to cut back power 50%, or if it's severe enough, maybe we have to scram the reactor and shut down. So it's looking at risk from that generation perspective. So what we can actually do then is the PRA gives us the envelope we're allowed to be in, but the GRA gives us something that we can optimize our different plans on. So how do they affect our future likelihood of scram? How do they affect our future likelihood of a derate? And then we can take that into account when we do our asset management decision making. So in terms of that asset management decision-making structure, as you've heard from the presentation so far, and as you can imagine, there's a lot of different variables we have to consider. There's the current state of the components, or what we believe the current state of the components are from the diagnostic information, and then what we're predicting the future state of the components will be with some probability. We have the cost to repair or replace components, and that cost might be different whether we're doing it under planned conditions or whether we have to do it on the fly because they fail at some point in the future. We have the costs of lost generation. We have the risks associated with an unplanned loss of generation versus a planned loss of generation too that we have to consider. So we've set up this kind of high level process about how we do the asset management decision making using this information we're getting. So we have our real-time risk profile of the plant. And for those who might be familiar with PRA or GRA, there's different importance measures you can derive from that, which tells you what components are the most important for your risk right now. And this can be what components are driving your risk from a safety perspective and what components are driving your risk from a generation perspective. So we actually get a prioritized list of components about what are those components that are most important to risk. And then for each component, we can say, well, what are the different things we could do? Okay, maybe this component we can shut down and repair it right now, or we can continue to run for the next 15 months and wait for the next outage. And maybe we do this for each of the top 5 or 10 components that have been prioritized this way. And then, so this might seem quite straightforward, but when you start adding in different combinations, you could repair component 1 and component 2 and not repair the rest. You can repair component 1 and component 3 and not repair the rest. The available options to you grows very quickly and very dramatically as you look at more and more components. So once we know what these different options are, then we can look at our safety risk and say, well, is this operational plan even allowed? Would we still be within our allowable operating envelope if we did this plan? If we're not, then that's a hard limit that no, we can't institute that plan, so we set that one aside. But if that is an allowable plan, then we can go to this last bullet point here and say, well, okay, what's the generation risk associated with this plan? So you can imagine if we see a pump degrading, we could shut down right now and fix it, and that would give us more confidence in the pump. Or we could say, no, we'll just continue to operate for the next year with this pump at a degraded condition, understanding that we have a higher probability that that pump could fail and we'll have to shut down at some point along the way. So we actually get a likelihood of these different events, of these different operational possibilities. And then for each one, we also assign a cost associated with it. So what's the cost of repairing things now? What's the cost and time needed to repair something in the future? And for each of these different options, then we can do the comparison and optimization on the cost benefit of each one of these. So the real difficulty here is really getting all this different information, all these different probabilities and likelihoods, and we want to distill it all down in terms of dollars, right? In terms of potential costs or the certainty of costs, and take that into account so we do our optimization correctly. Now, if you have a very simple problem, you can just do this using traditional cost-benefit optimization techniques. But as mentioned earlier, when you look at these more complex operational modes, then you really need like a reinforced learning process like the Markov decision process. Because you can think, if we're not repairing that pump now, what if that pump then fails 4 months in the future? That opens up a whole nother window of potential operational plans we have to look at. So it's kind of like a tree that branches out into more and more options as you look further and further into the future. And that growing complexity, oftentimes you need a more refined tool like a Markov decision process to look at. So those are kind of the different pieces of the analysis. Now I'll talk a little bit about the demonstration analysis that we're planning to do this year in FY22. So we wanted to have a demonstration analysis to show how these different pieces could work together in one integral approach. We wanted to use an advanced reactor, and working with Framatome, they have their steam cycle HTGR design. But there were concerns working with that design directly. There's proprietary and export control concerns, and especially working with the university, we didn't want to limit their participation. So we decided to use the General Atomics MHTGR design from the late 1980s, early 1990s, which was DOE supported. This is really nice because the design is fairly similar to the Framatome SC HTGR design, but there's tons of information in the public domain. So we have the preliminary safety information document, the pre-application safety evaluation report from the NRC. We have a PRA and licensing basis event selection. And we even have a lot of the SDDs and SSDDs, so that the system design descriptions and subsystem design descriptions, and even their initial maintenance plans and stuff too. And all this is in the public domain. So there are no worries about sharing this with students or anything like that. So we have a large amount of information to build on, and that saves us a lot of time within our project here. One thing we did look at in FY21 was trying to figure out, well, what piece of the MHTGR system did we want to look at with this demonstration analysis? Taking on the whole plant would be too much under this project within a year. So we looked at a couple different systems and we evaluated them based on the complexity, the available data we have to support it, how important is it to generation? You know, there's some systems that are really important to safety, but not might be important to a generation perspective. And then we also wanted Framatome's interest in the problem too, obviously working with them. So what we selected was actually the feed water system for the MHTGR design. And there's a couple of different reasons for that. One is that it is really highly important to both the PRA and the GRA in terms of the plant risk profile. So as you can imagine, if you lose your feed water, then you have a loss of heat sink, and that could be the initiator for a whole host of different transients in the plant. So it's important from a safety perspective that way. But obviously, it's very important to the generation side too. Not only does it feed one reactor module in the MHTGR design, it actually feeds multiple reactor modules in the MHTGR design. So there's quite a bit of complexity there in how this system operates. And there's a bit of flexibility too. There's quite a number of feed water heaters and stuff where you could lose one but still operate at a degraded capacity. So it's quite an interesting problem to look at from that perspective. And then also working with Framatome, they have tons of data on the components within these systems because there is a lot of similarity with light water reactor feed water systems. So we have a lot of good up-to-date information on the cost to repair items, what repair times would look like that we could use in our demonstration analysis, and that we don't just have to pull from the air. So to do this demonstration analysis, there is a bit of upfront work we've had to do. Number one, as you can imagine, we don't have an operating HTGR design to work with. So to demonstrate that part of the analysis, we've created a surrogate of the system in DiMola. So this will let ProAid analyze the system, look at potential faults, and we can actually use real ProAid output in our analysis, just as we would if we had an operating plant that we were looking at. And then we've had to recreate these risk models that we have information from them from the old MHTGR documents, but we had to put them into a tool that we can utilize. We're using Sapphire, which is the INL risk assessment tool. And then we could do the modifications in there to get the different risk outputs that we're looking at for our real-time risk profile. So in conclusion, again, we're looking at advanced reactor economics, both in the design and the operational phase. In FY21, we've really continued to expand the capabilities of these tools and refine how we're putting them together and talking between them, and also selected and started work on our demonstration analysis. Next year, or I guess this year now, we're really finalizing all these different methods because there's still a method or two where we have a couple different options we can choose, and we're trying to decide which one's the best execution pathway for our demonstration analysis. We'll complete this demonstration analysis, obviously do a lot of publishing along the way, and then explore the next steps, which I'll talk about here. So in terms of next steps, one of them, Rick talked about how his current NEET related to ProAid then is feeding into this one and how we're utilizing it. We actually hope to do the same with another NEET project that just got started by Roberto Ponchiaroli, who will be presenting a little bit later today. He'll be looking at utilizing ProAid as a component of an autonomous operation scheme. And as you can imagine, a lot of the things we're looking at this project in terms of looking at different operational plans and optimizing there, although in our project, we're looking at them as a suggestion to the operator, you could take that a step further and actually begin to automate operations based on some of these things too. So Roberto's project that he'll talk about later kind of takes it even beyond what we're looking at to fully or partially autonomous operation. We'll also be, depending on the outcome of the demonstration analysis, we'll also be looking to do a more complete advanced reactor system demonstration in partnership with a vendor. Because what we're really looking at then is, okay, well, what's the next avenue for industry if they want to utilize these tools and methods? What's the best approach to get this out there and available to them after completion of the demonstration analysis? So with that, I'll stop there. My information's there at the bottom if anybody has any questions. And sorry again about the hiccup there at the beginning, but.
Thanks. No, I thought it was my screen that was just not working right. So, but we were able to see what you were speaking about, so it wasn't too bad. So, very much appreciate you taking the time and sharing your results with us. Is very interesting. I don't see any specific questions at this point, so we'll just transition on to break is next. So, thank you very much, Dave.
Greg, can I ask a question?
Oh yeah, absolutely. Sorry, Dave. Didn't get off quite like you thought you would. So go ahead, Vivek.
Sorry to spoil the early break, but but good presentation. Quick question. So you're trying to tie the output of your health analysis to economic risk and economics, right? Eventually. So what would be that time piece, because your health indicator is in one kind of format of information and your risk takes a different kind of probabilities as an input. So where is that mapping happening? I didn't see that mentioned in the presentation. So can you speak to that?
Yeah, that's a really good question and something we've wrestled with a bit too, where, okay, we're getting online diagnostic information from the plant in its current state, but obviously your asset management plans take into account not only the current state, but your projected state for some time period in the future too. So where we're really making that linking from a technical perspective is within the Markov component models, because what that is allowing us to do is the diagnostic information we're getting from the plant is informing us about what we believe the current state of those components are. And in the Markov model, you have these current, the state probabilities of where your component is now. So we're updating that information based on the diagnostic information we're getting from ProAid. And we're also even exploring updating the transition rates between the components too. So, if it looks like the component is degrading now, we can also update our likelihood of it transitioning to a failed state in the future too, not only the probability of the state it's in now also. So then within the risk profile, within our risk models, within our fault trees and event trees, that is what's taking that updated information and actually projecting it out for the mission time of our risk profile. So the Markov component model is really the key there that lets us utilize that information within the event trees and fault trees of our risk analysis.
Okay, thank you. Again, I'm going to repeat myself from Rick's presentation. I would highly encourage you to look at one of the recently completed IFOA. It was done in collaboration with INL, and we do show that connection. We do show the economic, right? And especially we show how the future state prediction can be done, and you can make a decision whether to derate now or trip now or to take it completely offline to do the maintenance. So we have kind of show that optimization. So something as a point of reference to something to learn and build upon. So it's just because we are all in the scientific field, we just need to just make sure that we don't kind of recreate the same thing, but we want to do something better than what has been already done. So just a point of reference on that.
No, absolutely. And yeah, if we missed the latest publication, yes, please forward it to us. We'd definitely be interested in learning more.
And it does talk about the same thing, Markov process, the transition rates, how the transition rates are updated and based on the forecasting in the future, and how that is going fed into the economic model, because eventually it's all driven by economics, right? So you want to say safety and economics both are important. So we catch that. So there is some information there again. It's a data-driven approach, so it might provide some insights or something for you to consider.
Okay, no, great. Thank you.
Thank you. I have no more questions, Greg. Thanks.
All right, thanks. And I think, I'm not sure, Rick, did you have a comment or question?
Yeah, Craig, I can just add to that. So that you're not obviously not aware, we do have an IFOA at Argonne. it's looking at mechanistic degradation and providing that prediction component that you were alluding to. So we intend to synthesize that into what Dave is doing longer term. Yeah, so it's there's a mechanistic approach to doing degradation. We're doing it for heat exchanger. So we recognize that hole and we're working to fill it in.
Well, and that's the point of this this annual review, and get everybody together and chat and look at the results. So again, I appreciate the comments, questions, and particularly Dave, appreciate the presentation. So thank you very much. Okay, well, hopefully everybody can see my screen where I'm sharing our agenda. We just finished up the first session of the day, and we are now at the break time. So we'll, it looks like we're supposed to be breaking around 12:15 Eastern, so a few minutes early. Again, if you have any questions, please put them in the questions box interface through the webinar interface portal, and we'll get those to the panel in the afternoon session. But if you'll please plan on rejoining us at 12:30 Eastern, we'll pick up with Vivek's gonna offer some insight on his data approach for the methods and tools that are available through the NSUF data. So, all right, everybody, thanks for joining for the morning set. We'll see you in about 15 minutes.
Hey, Dave.
Hey, Rick, this is Craig Primer. You're still transmitting on
Okay.
the webinar. You want to mute?
Hey, Craig.
This is Craig.
Craig, this is Eric. I'm gonna make Vivek a presenter only because I have to run over to EIL real quick. So I won't be here for his start, but I'll make him a presenter, and then he can share his screen whenever he's ready.
Sounds good.
Okay, thank you, and I'll be back probably in about a half hour.
Okay, thanks, sir.
You're welcome, sir.
Right, Vivek, I got a couple more minutes before we get started. And so just welcome everybody back. And so just start introducing the next subject. Vivek's gonna walk us through his area of discussion on the developing methods and tools using nuclear science user facilities data. And again, that's focused on supporting the risk-informed predictive analytics. And I think that was what you covered earlier, is that effort in that space. So in just a moment, Vivek, I guess if you don't mind monitoring the clock, maybe in 1 more minute, it lets you start.
Okay, great, thanks. I hope you can see my full presentation mode and hear me okay?
Yeah, I see the screen, full screen mode, and hear you just fine.
Okay, thank you.
Okay, I think that's close enough. So as I just introduced Vivek, welcome everybody back, and turn it over to you, Vivek.
Okay, thanks again, Craig. In this presentation, what I'm going to present is basically the work we did at Idaho National Lab under Directorate Funded Research within the NEAT ASI program, and is on developing methods and tools using the nuclear science user facility data, very specifically the advanced test reactor data, to support kind of predictive analytics, and that can go in informing what could be the risk profile, and something that Dave spoke just before the break. So, and then again, this work was done at Idaho National Lab. So the scope of this work was to inform advanced reactors how the concept of operation and maintenance by design and can be included for the long-term reliable and economic operation. Because as these advanced reactors are working towards bringing the plant operational, they're working on lots of concepts ranging from sensors, controls, communication, and eventually they want to make sure that the O&M aspect of the advanced reactors is addressed. So it's an opportunity to understand and hear what the O&M would look like for advanced reactors, and how we should prepare ahead of time in terms of analytics, in terms of sensors, what kind of sensor adds more value. So that's why this concept of O&M by design was coined when we proposed this work. So then, and in order to do that, we know that the most of the advanced reactors are working towards operational advanced reactors. So we don't have real data yet. We have physics, which we can generate, but also we have something across the nuclear science user facilities that provides data at different levels, different scales, which could be leveraged to do some kind of predictive modeling and development. And that's what we are trying to do here, very specifically taking the data, the acoustic data that we collected at Advanced Test Reactor, to develop something what is called as a baseline signature that would inform how a reactor operates when there is no deviation, it's a steady state behavior, and what happens to the frequency or the acoustic signatures when there is an anomaly or there is a change of event. And if we can capture that, we can build analytics around that. And so, because to develop any predictive analytics, you need a reference value, you need a baseline information, and that's what we get from this acoustic signature. So that's what we are using, the operational signature of ATR and the develop predictive analytics. Thanks. So the TPOC on this project is Pradeep Ramaholi from Oak Ridge National Laboratory, and this work is done by myself and James A. Smith, both from Idaho National Laboratory. It was FY21 effort. So advanced test reactors, it's a legacy system, legacy reactor at Idaho National Laboratory with years and 70 years of service. So we kind of leverage this, and we do have looking at very specifically the acoustic signatures. Looking at just listening to passive acoustics, how the reactor operates, and when it operates, what kind of acoustic signatures are generated. Some of this initial work was funded under laboratory directed research, where the objective was different. The objective was to design or understand what is the quiescent frequency range where the acoustic sensors could be installed to collect salient information, because that is again very critical, because you cannot install a sensor, especially acoustic sensors, in a high vibration zone or radiation or noise zone, because it will just be the salient information would be buried in the noise. So it's understanding the quiescent frequency range was very important, and that was achieved. And once we had that system installed, especially within the ATR's nozzle trench area, it's an area where it's of limited radiation. We installed 8 acoustic piezoelectric accelerometers at 8 locations, and ranging from pressure vessels, flanges, and hydraulic shuttle irradiation system, which is commonly known as rabbit, which because these are some of the areas that we were able to access it. And these sensors were installed and have been operational for over 5 years now with limited radiation exposure, and they work still reliably. So radiation in the nozzle trench area has not impacted the performance of these installed sensors. So and then we connected this to a National Instrument data acquisition system, and what we are referring as an acoustic measurement infrastructure at Advanced Test Reactor. So now we are talking about acoustics, and we have to latch on to a very distinct acoustic signature so that we can use that as a reference, right? So we went through this ATR operation profile and realized that they have the primary coolant pumps that they operate, and that operates when the ATR is operating, and the impeller frequency is one of the consistent acoustic signature that gets transmitted to the structure and can be captured by the data acquisition system, which is at 148.3 hertz, what you're seeing. Okay? So it's a 5-vane system, and each rotates at 30 hertz. And the actual frequency should be at 150 hertz, but due to some slip, we do get at 148.3 hertz. And that became the fundamental reference signal that we track to ensure that when the pumps are operating and the ATR is operating, we capture that 148.3 and the harmonics of those nodes. So there are 4 primary coolant pumps. They are labeled as M6, 7, 8, and 9. And they're divided into 2 sets, set 1 and set 2. So when the ATR is operating in normal condition, they run 2 primary coolant pumps, 1 from each set. They never run 2 primary coolant pumps from the same set. That's a rationale that ATR has taken, and that's what they stick to. And then there's something called the power axle locator mechanism operation, where they operate the ATR above its rated capacity for a very short period of time for a very special experimental needs. And in that's the situation when they run 3 pumps. It doesn't matter how they choose the 3 pumps between the 2 sets, but they need to run 3 pumps. So there are different combinations we can get between the 2 pump operation, and that's what we have captured, because each combination of 2 pump generates a very different kind of signature, and that is an interesting finding, because you would assume that the same type of primary coolant pumps, with a little bit of age difference from pretty much same manufacturers, should generate very much same signal. But no, there is some distinction, and some frequencies are lower, some frequencies are higher, around 148.3 hertz. And especially the interaction, what we call as a beat frequency, is important to understand here. When the 2 pumps operate, and the beat frequency, the push and pull that happens between the 2 frequency or the 2 pump frequencies, is important to capture that. And that's a unique operation signature. So that's what is depicted on the schematic here as these operates. It's in the PDF format because the file size is high, so that's why you cannot see the animation. But if you do this PCP primary coolant pump 6 and 8 operation, this beat frequency changes. Yes. And 148.3 hertz became kind of the reference signal that we wanted to track, and then the second harmonic is 296.7 hertz. That became, so we choose the central line frequency around which we collect that amplitude, maximum amplitude signal. So that's the approach here. So that's the schematically represented. So when the reactor operates, these primary coolant pumps are running, and there's a raw acoustic signal that is generated, and it's very intense. We're collecting at 20,000 samples per second. So this is a huge data, huge amount of data. We take the data, identify the frequency of interest, which is 148.3 hertz for us, because that's a distinct omnipresent signature for us. And what we do is the first pass of short-term Fourier transformation. Sorry for not expanding the acronym. STFFT stands for short-term and fast Fourier transformation. And when we do the first pass, we extract the frequency is at maximum amplitudes. It's maximum amplitude. So 148 Hz band is selected, and then within that we select the maximum amplitude and also the phase at maximum amplitude. So that creates another time series of signal of max amplitudes, and that is passed through recursive short-term for fast Fourier transformation, and to generate another set of frequencies features, which is feature generation 1, feature generation 2. And eventually what we get on the right on the display is the beat frequency or the modulation frequency between the two pumps operating. It could be any combination and at different locations of across the 8 sensors. So that's why you see that the hertz is very small. It's like 0.05 or 0.03. That doesn't tell us that that's how that's not the operating frequency of the primary equivalent pump. That's the push-pull that happens and modulation that you're seeing there. So 2 pumps versus 3 pumps. The frequencies, just normal frequency domain analysis. As we did this to understand whether we captured this 148.3 hertz, and we show it across all the locations 5 here, because 3 sensors with different sensitivity. And we see that we captured 148.3 hertz very clearly across all the locations. And the noise floor level when 3 pumps are operating are a little higher, which is understandably because there's more fluid flowing through the system. The noise level is going to be higher. But only thing that was interesting is some high frequency around the 5,000 hertz, which is very high during the flange, but it went away because after some maintenance. So here is the spectrogram that we have generated from multiple data samples collected for different combinations of primary equivalent pumps operations. So this is for normal 2 pump combination. So we can get M6 can operate with M8 or M9, which we have here, and M7 can operate with M8 and M9, which we have on the left side, on the right side. Initially, you can see there is a small spiking here. It shows the reactor is coming online and reaches criticality and maintains a steady state operation. And you can see that the frequency mapping is a little different. So for M6, M8, the peak frequency is low in 0.03 hertz. But if you go to M7 and M8, normal operation, just different combination of pump, the beat frequency is at a higher, starts with a higher level, around 0.06. Right? But same thing, M6 and M9, there's a different combination. You can see some rise and dips in the spectrogram. I'll explain that why there's there. And so what does this 3 tells us is basically the M6 M8 combination. So it's very unique. It starts with a lower beat frequencies. So if you do, and you have to look to operator logs to understand which pump combination they're running. But if you have this kind of signature well built in, and you don't need to look at the operator log, you can just looking at the signature over a period of time, you can say, okay, this combination is running, this is the characteristics, and these are the things we should be monitoring. And so some of these jumps in the signatures are due to the changes in the operation. And so one of the jumps with M7 and M8 was operating is here, just for a pretty extended time of period with similar jump, and M8 and 6 was operating. And that jump is due to switching to diesel backup emergency diesel generators. Right? That changes the frequency of operation, and that is not a desired change of mode, but for some reason they have to do that. So that's why you capture that. And around this time, which is not enhanced, which will be enhanced in future slide, you will see there is a sharp change in the signal here that is related to the seal break event that happened and that led to the reactor shutdown. And through this, we were able to capture that at seal break before the ATR was able to capture it, like about 30 minutes ahead of time. So that is one of the things. So these are the operational behavior. What's interesting is when you do look at this spectrogram, it's not very evident, but if you just look at this portion, it has a kind of a bistable state. It goes up and down in a periodic fashion, which will get enhanced in the future slide. Right? And then it enters a very steady state behavior. It's a normal operation, but just because how the pump operates and how long it operates, the profile changes. Whereas on the 6 and 9 combination, you see the bistable state consistently across its operating regime. So these are a few observations that help you distinguish between the different combinations of the pump they are running and different operating mode they will go into. Here again, you see a spike, which was transitioned to backup diesel. So you can easily distinguish that. And the third one is the power accelerometer mechanism. The next one, we did collected the data on different combinations: 6, 8, and 9, 6, 7, 9, and 7, 8, and 9. Right? And each of them have a distinct signatures. What's interesting and what makes it different from the previous is you can see 2 beat frequencies here, because there are 3 pumps. There's a push and pull happening between 3 pumps now. So you should see two frequencies, and which we do. One around 0.01 hertz and one around 0.06 for this combination, and it changes as a bit for different combinations, and the intensity and the spectrum changes from the location also. So this is very useful for us to understand whether it's 2-pump combination, 3-pump combination, different beat. What's the interaction between the primary coolant pump, because they are located in a common area right next to each other. So one of the applications that we diagnosed very clearly is an internal event at ATR. It was a kind of a loosening of a cracking of a beryllium block, and eventually a loose part running. And it's an internal event, and it's very difficult to diagnose. So one of the hydraulic shuttle was close to the beryllium block, and that part started cracking. And so we did collect the data that time. We were collecting the data. It was a palm cycle, so you can see the 2 beat frequencies. But for some reason, we were not getting the signal, similar performance along the Rabbit installed accelerometer. And our first hypothesis was that the accelerometer installed in that area has gone bad or is fallen off. But until we got a call from a advanced test reactor that saying that it looks like we have an issue. Can your system sensor pick it up? And now it became evident that our sensor can pick up the internal faults. It was not just to understand the operating profile now, but also it can help us understand the internal structure. Only if it was in a real time, we could have captured that ahead of time. But it was more on an offline basis. And after the event, we could understand that this AMI infrastructure, along with the reactor data analysis, can help us understand the internals of the reactor. So that was a big finding from this research. So I apologize for the low resolution of the scheme figure here, but if you look at that event happened. Sorry, that event happened in 2016, and you can see a spike around this high frequency range, and that was an indication that, okay, Rabbit is telling us something in the frequency domain, that there is some event happening. The ATR fixed that issue, and we reran the analysis for the palm cycle a year later, and that frequency disappeared. Right? So that is, if this system is implemented and the frequency analysis is done on a real-time basis, it gives you an insight of what is happening. And every time you are able to capture that 148.3 hertz in both the locations. And as part of that maintenance action, and that was able to address the Rabbit beryllium crack, we were initially seeing a high spike around 5 hertz in the flange area. And after that maintenance action, that spike went away, and we got more clear on the 148.3 hertz frequency. So that is an internal action. So that tells us that some of the crack that was developing was also showing up a frequency at around 5,000 hertz. So we took all this information in, and that's one of the spectrogram we take, especially when they transition to backup diesel. we see that we take this entire spectrogram. We the startup, the event, 2 events we capture, and then shut down. So there are four basically transition phase during that phase. We take this information and we said, instead of doing it manually and visually comparing, okay, the speed frequency has increased. We put that into a machine learning model and said we'll do 2 types of machine learning models. One is support vector machine, which can capture the nonlinearity in the data, and also the linear discriminant model. It's a basic classification and linear classification technique, and see whether we can capture these events clearly. We didn't label them as event 1 and event 2, just an event and compared to normal. And our accuracy, we took the data and did the data processing feature extraction, and our results shows pretty consistency. I think so. I forgot to update this accuracy table. It's mistyped that. But overall, what we're seeing, the support vector machine performance is slightly better than the linear discriminant, and that's because there's some nonlinearity that support vectors kind of captured it. But the effort that you take to optimize the SVM is little more than that what you do for linear discriminant model. So with this case, I think so linear machine learning technique would work very well with small loss of accuracy, which is not a big one, and that gives you a classification model from a linear point of view, which is important because we don't want nonlinear training and computational time. So another aspect was a year later, there was an issue with ATR's neutron flux sensors, which is also known as the brush experiment, and it's seeing a high vibration. And we collected lots of data and ran lots of tests around that. And we ran from a single pump to 2 pump to 3 pump combination. And that's the timeline represented here on this center of the screen. And we go from operating different pump combinations, and you can see how when you you add 1 pump, it's at 148.3 hertz because it should lock at that frequency, and there is no. And you can see the amplitude plot here when they're operating, okay? And then when they shut it off, the amplitude goes to 0, and then all you see is a white noise. Right? So that's kind of says that, okay, you're seeing that 148.3 hertz in analysis, and we do keep doing that until we start operating the 2 pump combination. And you can see that the frequency, the amplitude, which was at low 2 unit, and starts spiking up. So then there's a 2 pump, and there's a 3 pump, then 2 pump. So that gives you a pattern of operation acoustic signature. And they start slowly withdrawing the control rods, and then the pattern starts changing. And all this is an important figure. We wanted to make sure that when we have this, and when they ran the pump cycle, it logged into the 3 frequency quickly. Okay. And we did that analysis to see that every time it's 148 hertz with slight variations around that point. So this was analysis still under work with ATR to understand what exactly happened with the ATR brush experiment and how this our data matches with their finding. And there's lots of questions and that still needs to be answered, but we are seeing that the sensors are able to behave and capture the react to the experiment and here. Yeah. So the technology impact is like we have shown that the recursive approach of short-term fast Fourier transformation can be developed, can be used to analyze acoustic signatures coming from an operating plant or in this case ATR, advanced test reactors. And you can use machine learning technique to diagnose whether it's normal operation versus an event and use that for future prognosis. So that is that. And what it advances is the concept of O&M by design and becomes kind of moves more from a concept to kind of a reality, saying that okay, there is a possibility of designing operation by maintenance content, because this approach also informs the sensor design, the quiescent frequency information, and so this is where the value of this research is. Impact to the industry, we are again focusing on predictive approach, how this can be used for maintenance or even for operations going forward, and make sure the reliability of the reactor operation is maintained or enhanced. Commercialization strategy, this was a tool developed completely at INL. So we do have copyright filed on software disclosure. It's pending DOE approval. And so once we get that, and this entire tool of acoustic data analysis using short-term recursive short-term fast Fourier transformation would be available for anyone to use it. And in this process, we were introduced to one of the events that happened at National Institute of Standards and Technology NIST last fiscal year, and we had some few conversation there on how this approach can be used at their reactor and help us understand what is the operating mode, what are potential events that can happen. So we are in discussion with them and looking forward to potential collaboration this fiscal year with NIST. So the software association can help there. We can license them in the government agreement and help them with their concerns and issues. So in summary, we cannot take it for granted that when the two pump combinations are operating, they're similar, though they come from different same manufacturers or same operating lifetime, maybe a little plus minus there. But they generate unique signatures, and especially the interaction between them are so unique that they can inform you more. And they can also inform you with a piece with aging, and that we saw some. And HER has kind of replaced most of their prime equivalent pumps or upgraded them. So it will be nice to collect those data back and say, okay, now this was on the aging PCPs, and now this is signature on the new. How is it different? How is it similar? How can this be used to inform how you should adapt your predictive approach because the signature has changed slightly because you have a new asset in the mix? Thanks. So that's the kind of the summary that we are looking to publish here. So that's basic information that we have collected in this project, and I think so. Then we are trying to reuse or optimize the use of recursive STFFT appropriately. So that's the end of my presentation. Thank you for your time.
Okay, thanks, Vivek. There are a couple of questions that Pradeep has posed that we've got a couple minutes. Maybe you can help answer, shed extra light on. So the first one is asking a bit about the bandwidth of the sensors used and how was that selected, those bandwidths?
So I am assuming he's talking about the sensitivity of the sensors. So if that's the case, we started with two type of sensitivity. And I didn't put that in the detail, but there are two types of sensitivities in the sensors. One of higher sensitivity, one of lower sensitivity. And we realized that the higher sensitivity sensor was more reactive and capturing the frequencies and information that we wanted when compared to other sensitive other information, other sensors. So that was the first round, and then once we realized that, we replaced the 3 that we had at lower sensitivity with the matching sensitivity of the remaining 5. So it was more on an experiment, trial and error basis. There was no prior calculation done to understand the sensitivity of the selected sensor.
For people that are out, yeah, just for like through that trial and error process, did you come away with any suggestions you might share if people were starting that themselves?
Generally, the sensors that are commercially available have a fixed sensitivity. So probably, yeah, I was not involved in the selection of the sensors and selectivity, but definitely I'll reach out to the team and see if there is a process they approach or their insight they learned, and I will share that with the audience here.
That sounds good, Vivek. And then the second question was a little bit more about the recursive pass on the STFFT. Do you have any more insight on that as well?
So why did we do recursive, or what was the motivation? Is that the question? So basically,
I think it was the actual, if you could explain the process a bit on the recursive pass.
So the recursive pass is like we take the raw signal and the raw signals are pretty intense. It's very difficult to store and analyze. So what we know is like we know that it's at 148.3 hertz is our main frequency. So we collect that, we decide that as a centerline frequency with a bandwidth of plus or minus 10, I think so. So 130 to 150, okay, and see within that band and go and see what's the maximum amplitude every time step and pick that. So that gives you a max amplitude times E signal. Now what we were interested in the push-pull phenomenon between the primary equivalent forms, and basically the modulation that's happening. And in order to do that modulation, we send that extracted signal again through another round of short-term fast Fourier transformation to extract that modulation. So that was the motivation. So it's a two round. It says recursive. Basically, it's a two times STFFT.
Gotcha. And so were any other algorithms considered there?
In terms of data analysis, no. We did think about breaking down the signals using wavelet transformation and empirical mode decomposition, but we didn't take that route because once we applied the recursive STFF, we got the beat signal that we wanted to, and we stopped it. But we did think about wavelet transformation of the signal and empirical mode decomposition, but never took that route.
Okay. Well, that I think addresses the questions that were asked. Thank you very much, Vivek.
Okay.
All right, we'll be transitioning now. Our next presenter, it looks like Dan's up next. Dan Cole from University of Pittsburgh, going to looks like go over your advanced online monitoring and diagnostic technologies for the nuclear plant management. So welcome, Dan. We've got you on video, and it looks like we can see your screen now.
Yep. And I suppose you can hear me as well.
Yes, sir.
Thank you, everybody, for having me. Yeah, as Craig said, this is about our advanced online monitoring project. It's really about using data, both about the plant and about the supply chain and the way products are, their availability and resource availability in order to make decisions for asset management and operation and maintenance. So this is the team. I'm the PI. Hang Ban here at Pitt is a co-PI, and Vivek is also involved in the project. We're about 2/3 of the way through, and that means that there are really 4 pieces to this, and I'll talk about these more in a minute. There's a condition monitoring piece, which is using data from the plant to be able to figure out what's going on. There's a supply chain piece. Again, that has to do with resource availability in terms of the low volume, high value assets that we use in nuclear plants. And we want to be able to bring those together and integrate them to be able to then make decisions about asset management, whether or not we need to repair or replace. And the real challenge is to be able to do multiple components over several outages. And it's that multiple outages problem that's really interesting, because when you're trying to deal with what's going on, and I have a better picture here, when you're trying to deal with what's happening over multiple outages, your decision to be able to buy a low volume, high value asset, it may not be the type of thing like you can make that decision at this outage and then replace it at the next one. It might have to happen 1 or 2 in the future. So there are, as I said before, there's the condition monitoring piece. Really, that's taking plant data and including it in some sort of component model that models the health of the product, of the part, the device, and actually can do some forecasting of health. Supplier data, and the real challenge here is that in nuclear power we have lots of one-off products, but further up the supply chain, things get more to made to stock as opposed to made to order, and the interaction of those pieces in the supply chain affects the ability to get stuff. And we now know, everybody's extremely aware of this, that supply chain is one of those hidden things where things can really upset it and affect stuff, and how it affects resource availability when it comes time to make choices. And if you're not going to get it for the next outage, but you decided that you have to replace it, there's increased costs in terms of getting it delivered early and stuff like that, which also gets to the economic modeling part. How we can take financial data about both the historical and future costs, whether or not inflation's affecting things, and combine these things into some model of the asset. And ultimately, what's interesting is things end up hiding over my, so I'm going to collapse some stuff here. Be able to, we're really interested in sort of the financial risk, where this is not really, doesn't really come down to safety risk. That's a different discussion. But we're interested in that sort of financial discussion about what the best options are in terms of minimizing costs and maybe maximizing uptime and capacity factor and things like that. The technological impact, I'll start here, is really about long-term decision making for a plant and ways that you can manage operation and maintenance. And along with that is ways that you can also go about minimizing staffing levels, so that you're not having to do the continual inspection in order to evaluate what's going on, but also make the right choices at the right points and times in terms of what needs to be repaired or replaced. So being able to do you repair, and how do you manage the critical assets that are in the plant? How do you do this over multiple outages? That's a big deal about what we want to be able to do. And all of this, both effects could affect the current fleet in terms of licensing extensions for a longer operation, but it also matters for advanced reactors, because this is an approach that could be incorporated in the way that we decide to manage and operate those advanced reactors and make decisions about what needs to happen over the long term. So there are 3 parts. I'm going to start with some condition monitoring. For this, we've had to, and I'm sure other people have talked about this, we've had to sort of generate some synthetic data to model what's going on. We've chosen to model some pumps, and specifically, we care about 2 different phenomena in particular, what we've modeled, which is cavitation and how that affects the health of the pump, and also bent shafts and things like that. That's by no means the limit of it, but those are the ones that we've been particularly focused on. So you see here on the left, there's a simple lump mass model of a pump, and we can use that vibration data along with some other models of health to be able to get predictions of the health of the pump over time. And with that, we can incorporate that data and some probabilistic analysis of how long the pump is going to last into longer, bigger term models. So using machine learning, really what we're doing here is a lot of Bayesian networks to be able to diagnose faults. We can collect information about pressure and vibration and things like that, and along with other metrics that we can measure, things like skewness and kurtosis, we can evaluate and use the Bayesian network in order to infer what the health of the pump is. And that information then is going to be used in that integrated model that we talk about later on to be able to make decisions about what needs to happen. Similarly, on the supply chain, the supply chain is a challenging thing. Supply chains are nonlinear. Your ability to stock stuff, there's limits in terms of what you can have in warehouses, and if you run out of material, you can't have negative inventory necessarily. So it's this weird nonlinear system, and it works well when the things are sort of at equilibrium. But when you go through odd situations where there's lots of demand and upstream suppliers have to increase their demand, and usually that requires them to ramp up their orders drastically, which causes further propagation upstream. You can get large swings in what different suppliers on different tiers are doing. This is compounded by the fact that in nuclear power, as I said, we have these low volume, high value assets. They're often made to order, but there's another model for the way you go about developing that sort of made to stock. And nuclear power, things really end up sort of, at higher levels of the higher tiers in the supply chain, those made to stock things then at some point become the made to order. And how those different things end up interacting, those different tiers of the supply chain, how they interact is something that has to be considered because they have different sorts of dynamics. And so in this picture we see here in the bottom left, there's a customer driven supplier. That's, the plant makes an order. That's very much a made to order sort of thing. But there's this decoupling between that and what goes on up at other levels of the supply chain in terms of made to stock. And those suppliers typically have to forecast what's going to happen. So we've modeled these sorts of things, these different supply chains with different tiers, and we can simulate different scenarios. And we use a particle filter to be able to do this. Again, this is a nonlinear system, and we're interested in sort of the probability of what's happening. So not only can we get a nice response and talk about what sort of the expected response of the system would be in a certain scenario, but we can get distributions and talk about the way those distributions behave over time. Those distributions are very useful when we get to Bayesian inference in terms of being able to estimate and predict what happens with back orders and lead time and other things like that. So, how do we create these Bayesian networks? Well, they're largely done by thinking about what goes on in a plant and the way you would do it in terms of a bill of materials. So, as you can imagine, you take a plant and you break it down into its individual components. And so maybe you're interested in a steam turbine, and then you break that down into its bill of materials, and thrust bearing is a certain thing that you care about. And then we can break that down into other individual pieces and talk about the ability for suppliers to be able to supply those individual components in a plant. And this ends up being, can be complicated. If you're trying to model an entire plant that's, all at once and the way everything interacts, that's a very big model. But you can still talk about individual components and the parts, the major components that make up those sort of macro components in the plant. So an example in the top right, you see this, thrust bearing criteria, and you can create, using the statistics that you know about the supply chain, you can create some sense of the unreliability and reliability. And the real interest is ways that we can go about mitigating strategies we can use. And so one that you can do is you can then get upstream suppliers to supply information about their ability to stock things and supply things and stuff like that. So we have this resources supplier. And with that information, having that information, you can reduce the unreliability of the delivery of that product, which is in the green box is that block there you see on the right. The drawback, of course, is that as you do this, it can cost extra money. And so there's an interplay, as you can imagine, between mitigating strategies you can have for the supply chain and the costs that it will take. We've done some investigation in these sorts of things. Again, we're pulling lots of different things together. And the real interest is reducing uncertainty, which helps us control the risk in terms of what's happening in the plant. It's not that there might be bad things that happen, but that we want to know whether or not a bad thing is going to happen or not, given the forecast for what's going to happen. So we can use the dynamics of the supply chain along with the certain goals that we have for that, and we can incorporate in these mitigating strategies in order to account for what risk events happen. And so the graph that you see on the right, this plot shows a variety of different strategies that you might undertake in a plant. And in these particular cases, there's a cost of each strategy that is the x-axis, and sort of measured on the y-axis is the unreliability in that particular part. And as you can imagine, you'd want to do something that's very close to the origin. In this case, find a strategy to help improve the existing supplier. In this particular case, ends up being something that ends up being more beneficial than other options that we looked at. Finally, we get into how do we incorporate these things? And this is work that we're currently doing right now. Again, we're interested in bringing condition monitoring and the supply chain together along with some economic model of what's going on, and use that to be able to make decisions about what to do in terms of operation and maintenance, right? And these assets that exist in the plant. And there are a variety of things that you can do. Do nothing, you can inspect, replace now, replace the next outage. And what makes it even more challenging is that operation and maintenance decisions are now, there are certain choices that can be made sort of inter-outage or intra-outage, and there are other ones that have to happen at the outage. And so being able to make those choices over longer periods of time is more challenging. And the system is complex. So there's these complex and nonlinearities in the problems, and the more components you have, the more complex the environment gets. And the problem gets really, really hard. And so there are a lot of tools in the AI world that are strong here that can handle long forecast horizons, uncertainty and partial observability of the system, and the large action and decision spaces that we're talking about here. The approach that we're looking at is the reinforcement learning, and here the idea is that there's some reward for the agent to make the right choice, and the reinforcement learning uses that, and that reward most basically ends up being the cost that it's going to be to take a certain action. But that agent then interacts with the environment that describes the way that the plant is going to be operated and the financial interests and what the assets are like and things like that. And so as the agent interacts, the agent receives rewards and penalties for each action it takes. And with that, it can converge to an optimal answer. This type of approach has been done a lot for drone swarms. It's been used in complex games like Go and even Dota 2, which is an online role-playing game. But what's interesting there is there's lots of actions that can be taken, and some AI people using OpenAI have been able to create agents that are able to win that game and perform better at it than any humans can do. So there's a lot that can be done. Some preliminary results that we have uses deep Q learning. So Q is sort of the score that you get, the cost that you're trying to optimize. And they've been proven successful for single component analysis. And you can see some training results that, over the number of episodes, we've been able to minimize or maximize the reward. And in the picture on the right, you can sort of see component health as a function of time. And in this particular instance, it got to a spot where it decided that it was more beneficial to do a partial repair in order to get it to the next outage, at which point it could do a replacement and get the health back up to near 1. I have a PhD student, Ryan Spangler, who's working on this, and he's currently trying to incorporate multiple outages and multiple components. He says it's a really complicated environment, and right now is having some challenges getting the AI to converge. But I have every confidence in him that things will work out. And so I don't know why this says needs to be updated. It doesn't need to be updated. We've evaluated a bunch of different machine learning methods for improving classification and condition monitoring. We have some dynamic supply chain models that let us evaluate and estimate what's going on in the supply chain, even using supplier information from that first tier supplier. And then we're starting to incorporate these bits of information together into an integrated model that lets us do decision making over multiple components and multiple outages. And so with that, I'm happy to take questions. And I imagine I'm ahead of schedule, but
you are a little bit, yes. And I'm looking, I don't see any questions yet. So if anybody has any questions, please feel free to submit them. In the meantime, I'm gonna comment that I think the needs update, maybe you wanted to put in your happy picture and you're smiling.
Well, I do have a slight smile in that picture, but for whatever reason, my smile looks more like this, and it doesn't really, it doesn't map well to internet sort of thing. So I end up with my yeah. Everybody, I have what I call an angry rest face, and the students all say I'm intimidating, but that's just because of the angry rest face. So
that's appreciate, and I don't see any questions. So let's just move on. And Dan, thanks for sharing your
you bet
work, and if you're available for the panel session, there may be some questions for you, but appreciate the insight into the work.
Okay.
All right, so next we'll be transitioning over to Roberto. He's out of Argonne, and Roberto, welcome, thank you. See your presentation and you, so that's a good start. So Roberto's gonna give us an update on the design and prototyping of advanced control systems for the advanced reactors operating in the future electric market. So Roberto.
Can you hear me okay?
Yes, sir.
Perfect. And you said that you can see my screen. Okay.
That's good, thank you.
Okay, awesome. All right, good afternoon, everybody. Yes, my name is Roberto Ponciroli from Argonne National Laboratory. I am the PI of this neat project, so design prototyping of advanced control system for advanced reactor operating in future electric grid. Yeah, sorry for the title. And so basically, this project is a collaboration between Argonne National Laboratory, University of Michigan, and Kairos Power. And basically, the driver, the goal of this project is the improvement of the economic competitiveness of advanced reactors. And we propose to achieve this goal, how exactly? First, by enhancing the operational flexibility. So the idea is that we came up with an integrated energy system constituted by an advanced reactor concept plus thermal energy storage technology. Then our idea is we're pushing for autonomous operation. Well, when I say autonomous operation, yes, it would be more correct if I say semi-autonomous, because the last word, of course, belongs to the operator, but you got me. And the idea, the goal to do that, we propose to, we propose a suitable architecture where control modules, diagnostics modules, and automated reasoning modules are closely interacted and they are integrated. And finally, basically the point is how we're going to improve the economic competitiveness. Well, the idea is that we're going to propose several solutions to reduce the O&M costs by optimizing the plant availability and the maintenance schedule. This project started October 2020, so FY21 was the first year, second year just started, and we're gonna keep going until September 23rd, okay? Okay, as for the schedule, yes, FY21, 22, 23, FY21, the goal was basically what we did, we focused our efforts on definition of integrated energy system reference configuration and the development of the high fidelity simulator. So the first step was the selection of the suitable configuration that will serve as a reference case, okay? So first we identified the appropriate thermal energy storage technology that can be driven by a fluoride salt-cooled high temperature reactor, so FHR. And as for the modeling, we adopted SAM, so System Analysis Module Code was developed, is currently being developed here at Argonne National Laboratory, and we put together a high fidelity simulator. So that's basically the efforts and the achievements of the first year. Second year, is going to be focused on the development of diagnostics and control methods. So first, and now that we have a high fidelity simulator, let's use it. So we simulate operational transients, charging, discharging of the thermal energy storage, load following, and all the possible power transients that are envisioned during normal operation. Then we're gonna implement the regulators foreseen by the control strategy. Most of them are PID controllers or feedback controllers. We're gonna implement finished state machine to coordinate and synchronize these controllers, and the supervisory control layer. And finally, there's going to be the selection of the diagnostics algorithms and the derivation of the digital twin that will be used by diagnostics and by control modules. Finally, during the third year, there's going to be the demonstration of the performance of the proposed architecture. So we're going to formulate the Markov decision process that will constitute the heart of the decision-making capabilities. And for this part, the achievements and the outcomes of another neat project, the one led by Dave Grabaskas, will be leveraged. So, those achievements will be very important to define this part of the project. And then finally, there's going to be, of course, all the different components of the architectures will be coupled, and the whole architecture will be validated by adopting the high fidelity simulator. So basically now, before proceeding, I would like to stress this part. So how exactly can autonomous operation can help saving on O&M costs? So why are we pushing for autonomous operation? So when I hear autonomous operation, I mean, in my mind, it comes to my mind the paradigm of the self-driving cars. In this case, I would like to stress that when we talk about autonomous operation, I mean, you're not going to save money by limiting the number of operators, by limiting the number of the people in the main control room. So the idea is that an autonomous operation, this paradigm, this concept, and then a control system architecture that implements this concept is going to help saving money by optimizing the maintenance schedule. So less time-consuming interventions, or by limiting the number of technicians on site, okay? So having a diagnostics algorithm that tells you exactly what is the component that is faulted or whose performance is degraded, or which are the sensors that need to be replaced, or what is the most suitable time to replace a component or to intervene for maintenance. So that's the kind of things that help you saving money, okay? And another thing I would like to stress here is that we're going to apply AI ML algorithms to normal operation only. So I'd like to stress that we are going to focus in this project, in this implementation of autonomous operation, we're going to focus on the normal operation, okay? So there is a clear separation between control and safety, okay? If one of the safety-related constraints are violated, okay? So if one of the variables that are monitored for safety purpose is going to exceed the safety thresholds, okay, the party is over, and that's safety stuff, and we're not going to mess with that. So we're going to stick to the normal operation envelope. So that's an important distinction I wanted to make. Now, I mean, what is the concept behind the autonomous operation? So basically the inspiration or the idea that I'm trying to implement in this architecture is started from this NUREG that was published in 2016 by the NRC. That year, the NRC organized a team of researchers to review literature in psychology, cognition, behavioral science, and apply it to human performance in nuclear power plant operation. So the idea, the point, the whole point of this publication was that the best way to produce power with fewer errors, fewer events, and improved performance is teamwork, okay? So the idea is that to operate a nuclear unit, there are different tasks, okay? Detecting and noticing, sense-making, decision-making, action, different tasks, and people performing and taking care of those tasks, okay? And the idea is that all these people gotta play together, gotta interact and operate as a team, okay? Because teams without teamwork defeat the purpose of teams. It's just a bunch of guys working together, but that's not enough. So the idea that the point that we're trying to make here in this slide is that if we want to implement this concept of autonomous operation, we need to stress this teamwork feeling, okay? So basically the control, the diagnostics, the decision-making modules, they gotta be at the same page and they gotta closely interact. So that's why the architecture we're proposing is not just, like in the old days, like a pyramids with upper layers tell the lower layers what to do, but we have control, diagnostics, and decision-making closely interacting with each other. Another thing is that, as I said before, nuclear has some peculiar features, okay? So we're gonna preserve the distinction between the plant control system and the plant protection system, okay? So it monitors safety variable, as I said before, violates the corresponding thresholds, okay, the party is over and the plant protection system take over in case in these situations. Another thing that is very important, another requirement, is a requirement for the diagnostics, because as you can imagine, in this project, we're gonna heavily rely on digital twin, because the control module is going to use a digital twin, the diagnostics is going to use a digital twin. So digital twin are going to be fundamental in this project, and of course that will be derived by adopting data-driven techniques. Okay, so as the power operates and the performance of its components change, clearly the digital twin corresponding to the system gotta be updated. Okay, and to do that, the data-driven techniques will be used. But think about it: if you cannot trust your data, well, that's a problem. I mean, let's assume that one of the sensors or multiple sensors are biased or they're faulty in some way. Okay, basically the data you're using to derive your digital twin cannot be trusted. They are not accurate. So your digital twin will not be accurate, and then your control actions will not be effective. Okay, so there are a series of failure modes, maybe a series of consequences that I don't want to even think about it. So the point is that diagnostics algorithm, a capability of diagnostics algorithm is discriminating between component level faults and sensor level faults, and that's fundamental for to ensure good performance for this kind of systems. Another thing is that, as I said before, one of the goals of this project is to extend the flexible operation capabilities of advanced reactors. Okay, so basically we are trying to push the boundaries of normal operation. Okay, so we're trying to operate this system as flexibly as it could. Okay, so load following, charging, discharging, and the point is that we need to stay, as I said before, we need to stay within the bounds of normal operation envelope. So the point is that if you wanted to achieve these goals, these bounds gotta be closely monitored, okay? And these bounds gets updated in time, because as I said, the performance of the component change in time. So the bounds of the normal operation envelope and the degraded regions, they are changing in time. They are evolved as the reactor is operated, okay? And so we need to closely monitor these bounds during the plant operation. Now, when I talk about normal operation envelope, I'm not talking about an abstract concept, because yes, traditionally it's just something to visualize where is safe to operate the reactor and when you don't want to operate the reactor, right? But the point is that for this particular application, it gotta be more than an abstract concept. So, as I said before, it evolves in time. So this envelope gets larger, shrinks in time. So it gotta be monitored. And to do that, you need that superior diagnostics capabilities. Okay, so you can track the performance of the components, and you need a dedicated control algorithm that allows you to evaluate this envelope. To this aim, we identified the reference governor, which is a DOM scheme that allows enforcing state constraints. And this algorithm allows you to evaluate the normal operation envelope. So basically, in a nutshell, this is the idea. You have a bunch of controllers, okay? They are trying to control and to govern the evolution of your system, okay? And you have a set of constraints on flow rate, temperature, pressure, and these constraints gotta be respected during operational transients, okay? And the reference governor basically is, as I said, is a DOM scheme that enforces the respect of this constraint by adjusting the set point signal. Okay, so basically the operator is providing the set point signal, and the reference governor adjusts these signals to ensure the respect of these constraints. And as a result, as you can see at the bottom, the reference governor allows evaluate an n-dimensional polytope that evolves in time. And basically, this n-dimensional polytope is the normal operation envelope. Okay, so you define your set of constraints that define the normal operation, and this algorithm allows you to quantitatively evaluate this envelope and to ensure that the system moves within the bounds of this envelope. Okay, so that's why we selected this this algorithm, and why this is the heart of the supervisory control scheme. And that's shown at the bottom. Okay, this is not related to the current project; it's from a previous project. But the idea is that this feasible region, this area within you can move, is something that evolves and shrinks or gets bigger in time. Okay, and that's one of the most important pieces of the architecture. Now, as I said before, most of the work, most of the efforts of the first year was focused on the definition of the integrated energy system reference configuration. And as I said, pebble bed fluoride salt cooled high temperature reactor was selected. Okay, and it was coupled with a thermal energy storage, and in particular, in this particular application, molten salt energy storage was selected. Okay, so our national laboratory developed a generic model in SEM for an FHR. It's called GFHR, to foster commercial developments of FHRs. Okay, so the idea is that we took that particular model for the primary circuit, so the nuclear island. Okay, and we interfaced that primary circuit with an intermediate circuit with thermal energy storage. And when I say thermal energy storage, basically I'm talking about two tanks of large size, okay, a high temperature tank and a low temperature tank that allows to store energy through, heat basically during low demand period, and allows releasing this energy, and so producing an additional power contribution during peak demand periods. Okay, so basically we have these two tanks that are always interacting on each other during charging discharging transients. In particular, as for the GFHR design specifications, those are based on the University of California, Berkeley Mark I design. Okay, and of course, all this project is being performed with the collaboration and the support of Kairos Power. As for the primary circuit, in this slide, you can see a detailed view of the core. So as I said, it's a pebble bed core. And you can see a schematic view of the thermal hydraulic circuit. Okay, and you can see at the right the list of components. Okay, so the core, the pipes, there is an expansion tank that is fundamental to limit the pressure transient and the density transient during power variations, and interface with the intermediate circuit. So as for the core, as I said, the SEM code was used. The reactor, the core, basically is a 320 thermal megawatt core power. And as for the neutronics, point-wise kinetics equation was used. And dedicated thermal hydraulics closure models were implemented for packet bed geometry. Okay. As for the intermediate circuit, well, as I said, we got the two tanks, so suitable valves and pumps for charging and discharging transients. And in SEM, we implemented the thermophysical properties of the selected solar salt. So basically, we leveraged a technology that is currently implemented in concentrating solar power plants. Dedicated PID controllers governing the pumps were implemented in SEM model. Okay, and it's very important in this model the addition of the expansion tank. A dedicated expansion tank is foreseen to address coolant expansion contraction during transients. Okay, and finally, as you can see there, there is the SEM, that dashed blue line represented the SEM boundary condition. So in the simulator, we didn't explicitly model the energy conversion cycle. So to mimic the presence of the steam generator, a dedicated boundary condition, so basically thermal flux imposed, is adopted. Okay, so to mimic, turbine trigger the power variations, we impose time-dependent thermal boundary conditions. Okay, and from a dynamic standpoint, that's all you need basically. Another aspect, another tasks that we perform during the first year was the design of the TS circuit. So basically, as we said, the primary service of the nuclear island was the GFHI model, and we slightly modified that model. But the point is that we focused mainly on the intermediate circuit, and we had to size the tanks. Okay, the tanks containing the molten salt. So basically, the procedure we adopted was this one. So we took a representative normalized daily demand profile data from the California ISO grid. Okay, we selected because of the large penetration of renewables. So basically, in this picture, you can see the duck curve. Okay, so you have up and down. You have moments of you have periods of low demand, periods of high demand. Okay, and those periods corresponds basically, from our perspective, to charging mode and to discharging mode. Okay, so basically, starting from how long does the discharge the high demand period last? How long is the low demand period? So starting from this one, starting from the requirements and the performance that we want, basically we derive the size of the tanks. Okay, so basically we performed, as you can see in the table, a sort of sensitivity analysis. So saying, okay, during the high demand periods, I need to provide 50 megawatts for 30 minutes. That corresponds to a certain size of your tank. And so basically, according to your requirements, the performance you want to achieve, you have different volumes. So we perform this kind of sensitivity, and finally we defined the optimal size. Okay, or better, I mean, it was not really an optimization, but we find out a compromise between the size of the tanks and the performance that we wanted to achieve. Another thing is that during the first year, we defined the control strategy. So when I say control strategy, basically the idea is that we have a certain number of actuators. Okay, so there is a list of input variables we can manipulate to govern the system response. Okay, and we have a lot of variables that ideally we would like to control. Okay, or whose evolution needs to be controlled. So we have candidate input variables and candidate variables that we want to control. So what is the most favorable pairings? Okay, what is the optimal pairing? So how are we going to control the guys we want to control? So that's basically what we mean by control strategy. So we defined these pairings, okay, and we implemented suitable PID controllers corresponding to these pairings. And in addition, we defined a preliminary set of constrained variables. Okay, so basically variables that need to be constrained during power transients, and basically, you know, that corresponds to the normal operation envelope. So starting from these constraints, okay, so first we define a set of variables to be constraints. We define the corresponding upper and lower bounds that gotta be respected during normal operation, and starting from that, the reference governor will define an n-dimensional polytope that corresponds to the normal operation envelope. Okay. To define the PNID of the integrated energy system, so the set of sensors, the variable that can be actually measured and monitored, we relied on the experience of University of Michigan and Kairos Power. At the end, I'm close, I'm almost done, just a couple of slides. You know, as I said, during the first year, we completed the development of the high fidelity simulator in SEM, and we started simulating some of the most interesting operational transients. So in this case, for example, is the TS discharging. So the idea is we have the high temperature tank completely full, okay? So it's full of hot salt, okay? And what happens that we are in some of the above mentioned high demand scenario, okay? So we need an additional power contribution from the intermediate circuit, okay? So the reactor is going 100%, but I need more power, okay? So salt is flowing from the high temperature tank to the low temperature tank through the steam generator, and an additional power output is produced, okay? So we have PID controllers that are regulating the head provided by the pumps, the discharging and the charging pumps, okay? And as you can see in the picture, you can see this is not a large variation, but it's still meaningful, okay? And you can see how the temperature changes throughout the circuit, okay? So you see in particular the IHX outlet temperature and the IHX inlet temperature. And you can see how the level of the high temperature tank and the low temperature tank changes, okay? From this perspective, the role of the expansion tank is crucial to address the coolant expansion and contraction during transients. Okay. Another transient that we simulated, another power transient, is the load following transient. So basically, let's assume that something is happening at the SG level. Okay, so the turbine is demanding less power. Okay, so we are reducing the feed water flow rate on the SG side. Okay, and so let's evaluate how the thermal perturbation propagates throughout the intermediate circuit first and the primary circuits later. Okay, so basically we simulated the load variation by altering the imposed thermal boundary condition. Okay, and in this picture, okay, on the bottom you can see the SG feed water flow rate variation. So it's a 10% variation, and in the plots on the right you can see the corresponding thermal perturbation. So basically you have that because of the reduced heat disposal capabilities, basically the system is getting hotter, okay? So the core inlet temperature is increasing, okay? And as a result, because of the negative reactivity effects, the reactor power is dropping, and so does the core outlet temperature, okay? So this kind of transient is very important to evaluate the characteristic time constants of the system, okay? So starting from this simulation, we're going to derive the characteristic time constants of the system, okay? So how long does it take the thermal propagation to propagate throughout the whole system? And that is going to be fundamental to evaluate the most suitable strategy to meet the demand. So basically, so far, we simulated the load following, right, and the charging discharging, okay? When we simulate the charging discharging transients, basically the reactor is supposed to go 100%, but that's not always the case, okay? Because sometimes you can have at the same time load following and charging discharging at the same time with the thermal energy storage that smooth the transients, okay? So basically it's helping meeting the demand without asking the reactor to change the power like a roller coaster, okay? So basically, this kind of transit is fundamental to characterize the dynamics of the system and to find the best policy to operate the reactor. As for the future plans, these future plans are short-term plans, okay? So now we're focusing our attention on the implementation of the system identification scheme to derive the digital twin for control algorithm, okay? Because as I said, the reference governor is going to need a digital twin. At the moment, the reference governor has not been implemented yet, but it will. And a digital twin that allows you to closely approximate the system dynamics is crucial, okay? Then we're going to implement the finished state machine to synchronize the control actions during complex operational transients, okay? Because so far, the PID controllers are manually coordinated, but the more we go into complex power transients, the more we're going to need synchronization. And so finished state machine to coordinate all these actuators are fundamental. And finally, we started a literature review about the savings in terms of O&M costs ensured by autonomous control architecture. So as I said before, how does exactly the autonomous operation can help with saving on O&M costs? So we started breaking down the O&M costs into different items, and let's see how autonomous operation allows addressing each one of these items. So thanks a lot for the attention. So if you need any questions, I'm here. Thanks.
It looks like there is a new question. I was trying to open that. Give me one more second, sorry. Yeah, sorry, Roberto. I thought there was a question for you, and I was trying to open it, and it doesn't. It looks like that was an older question. So again, thanks for the information with us, and it looks like I was mistaken on that question. So we'll transition now. So thanks, Roberto.
My pleasure. Thanks a lot.
You bet. All right, so now we'll move on to Pingbo Tang's presentation. As Pingbo's on, we'll transition over to you.
Yes.
Yep. Perfect. All right, we can see your.
Can you see my screen?
Yes, sir.
Hello.
All right, while you're getting set up, I'll just introduce you real quick and with the audience that you and it looks like George Gibson are perhaps going to be sharing information on the context-aware safety information.
Can everybody see my screen?
Yep. Can you hear us?
Is
All
it
right,
okay?
when you're ready.
For the presentation. Hello.
Yep. Yeah, Pingbo. Sorry, I keep talking right over you, so I apologize for that. But feel free to start your presentation.
Let me see. Hello.
Yes, we can hear you. If we can see your screen, great. And we can.
Yeah. Let me use my my screen to present. So the screen is okay, right?
Yes, it is.
Great. Okay. Hello, everyone. Thank you for listening to my presentation. This project is the PI is from Arizona State University, Professor George Ed Gibson. I'm the technical PI for the research development. Co-PI from Ohio State University, as well as collaborators from Idaho National Lab, Professor Dr. Boring and Mr. Miles from Duke Energy. The research is about context-aware safety information display for nuclear field workers. The scenario is when we have a nuclear power plant, there is two parts of the operation. The first operation, people look at the control room, but the other portion is the nuclear plant field. Information has to flow from the field to the control room through sensors or through other approach, such as human observation. Once we have the information from the field, we have the control signal from the control room back to the field to make sure that everything is okay. Now, once we have some sensor data, some information sensor data cannot capture, or some information data has a malfunctioning problem, then we got to have the operator communicate with the field operator. The control room operator, usually they have a well-defined procedure for the field worker to follow what kind of information they should collecting and what kind of a part of the job site they should pay more attention to when they are finishing their task. Then the field worker will have an operator run. That's in the literature we found from the literature. They collect information, the component status, temporary modification, have some temporary modification in the field. Then they communicate back to the control room and to say, this is what I found from the site. Please continue your operation. Then the control decision made by the operator is going to finalize the control process. In some cases, there is the word is not perfect. For example, the information from the control room might not be exactly reflecting the real-time situation. I would not say that's the problem of the operator. That would be the nature of this very dynamic control process. And the people might not realize that something has been changed in the issue when they issue information list to the field worker. On the other hand, the field worker might have some chances to recognize the incorrect part of the job site, the workspace, or they find the wrong object, correct the wrong information, because there are so many similar objects in a small packed space. Then, in order to make this whole control process more reliable, another approach is to use the control history. For example, the nuclear power plant has a digital control system. In the future, the sensors could be connected everywhere, and we could look at what happened at every location of the facility and of all the loops of flow loops of the nuclear power plant, and to see what people has been doing and how the control algorithm has been doing to manipulate valves and change different parameters of the control system to make sure that the nuclear power plant is working efficiently and safely. Then once we have that information generated from the control history, the control history provide people a memory of operation and tell them in this kind of situation, what are the most useful information and what are the most critical object we need to looking for. Then the field worker will carry out the information with a more reliable real-time situation awareness. And to understand, we need to walk through the space and to find out the right place and locating where they are and make sure they go to the right spot in the nuclear power plant. They are going to find out the critical objects, the critical sensors. They need to pay more attention based on the real-time sensor data. Then, based on the trends captured by the sensor data, its a simulation model could predict the flow trends of the nuclear power plant to make sure that what they are doing right now is going to projecting to some good outcome in the future. Now, what we are trying to do here is that since we need a real-time situation awareness, we are trying to have some kind of like a real-time data collection from the field, including sensor data, also including video from the job site. If we have a video from the job site, such as the camera, the worker carry a small camera on their suit, then we could match in the information from the digital system versus the object detected from the video. Then the computer vision algorithm will find out which object are related, are corresponding to the object in the video. Then using the augmented reality glasses to display the information to the worker to give them real-time information about the important object, important sensor to pay attention for their task in that scenario. From a more technical point of view, the framework of this context-aware safety information display system, we have the input as the layout of the workstation, nuclear workstation, the real-time environmental video, and of course, we have a sensor data from the physical mode reflecting the physical condition of the nuclear power plant. Another sensor information we didn't put in the original scope of work. We realized that that's important because human operator, they have a lot of experience and they can notice a lot of those abnormal behaviors of the facility very, very early, such as a small noise or something which is not modeled in the system, but human kind of know is not normal. Then we try to also collect in the operator's eye motion data and to as part of the operation process. Then those three sensor, video, human behavior information can be put into reasoning model and to produce a list of information to help the field worker to find out where they are, what are the critical objects, and what they should do, operation guidance, and what is the prediction if we do this, and what's going to happen. Then any risky or dangerous information, dangerous object they should avoid, and to make sure that they are doing the work follow the instruction, compliance checking. Now, once we have this whole process set up like this, then we need to make sure that in this whole process we have a control loop, and that control loop has a simulation part. The simulation part means we need to understand what's the process and what is the expected process. And the other part is the situation awareness. That's the real-time part. We need to have the information from the real-time sensor readings, from the real-time video collected from the job site. For both the simulation and the situation awareness, we have a three-step type of execution, the work in the job site. For example, we need to understand what's the state of the nuclear power plant, so which is perception. Then the next one, it's going to be, we observe the most critical part of those state, which is collected by sensors. Then once we have all those information, then we need to taking actions. And the goal is to say, we know the simulation and the real-time situation awareness, they match. Then we can provide the field worker instructions about what is the most the safest and the most efficient way to carry out their work. Then the computer vision algorithm work together with the context awareness safety information display. It's going to be a powerful way to help the worker to make that communication loop between operator and the field worker much more efficient, or maybe potentially in the future, we can have most of them as a field worker, only the central control room will be more decentralized. Then to enable that, we have a very important part of the data is from the job site video. And using the job site video is important because we need to collect information, the visual, the site condition information to help us to understand where we are, which is positioning. And for this part of the research, the Ohio State University researchers has developed an algorithm which combines the video data from the camera, inertial measurement unit data, which measures the acceleration, rotation around along XYZ axis and around XYZ axis. And use these two part of the data, the combination of these two data analysis process is going to use a floor plan to help us to locate the worker on the floor plan. Then once we know the current position of the worker, then we also know the current orientation of the worker. The orientation of the worker is also important because we want to have the augmented reality glass provide the real-time visualization to align what the worker are supposed to see based on which direction they are facing. Now, then the next step is once we know where they are, then to carry out the work, it must be a destination of the task execution. So that's the navigation part. For navigation part, we need the video data. We also need the hazardous location information identified by the algorithm to say which part of the site it's not safe for the worker to touch, or even they should not even get close to that area. The work order information tell people about what are supposed to be done in the workspace, in the field. Then finally, the worker get the information. They are going to follow a path generated by the system to safely transfer their destination. They also get a real-time video information from their mobile camera, and the object detection network trained by a lot of those sample data. I'm going to show you how we train them later on to recognize which object is supposed to be the object identified by the algorithm as a safety critical, and also identified by the algorithm as a critical sensor to highlight those to the worker so that they will know, okay, this sensor data I should pay attention, and this is the object I should touch, and this is the object I should not touch. Now, the whole process, let me recall, it's find out the location, to have a safe path navigation, and identify the critical object in the real-time video. Now, how we generate the operation, how we use the operation history of a nuclear power plant to find out what is the things they should do or they should not do. We are trying to learn possible control action sequences from the operation history. We can say it's like a digital records or say computer logs in the control system. We can use those to determine what is the most likely control action safer next based on what they have done. Then, for example, when we learn and look at the sequential process about a time series of sensor data and a sequence of actions people has been doing when certain sensor data show certain patterns, then we can show that, oh, some sensor reach a set point, people need to take action. When a combination of several sensors form certain patterns, people take another action. Then we want to build a model to predict when the operator should perform what type of control action, including which sensor data is most important for them to pay attention before they execute that control action. The development efforts for prove the concept of a historical operation history, historical data of a nuclear power plant operation could help us to identify safer and critical objects to highlight in the video. We are using the RANCO system developed by Idaho National Lab and the University of Idaho called RANCO to simulate the operation. It's a simplified version of a real world operation. But we can capture the operation logs with all the sensor data, time series of sensor data. For example, the time series of temperature, flow rate at the different locations of simulated nuclear power plant. It's a physics-based model to help us to collect the operation data. And we test a few processes. I'm going to use one example. It's called reactor startup to show the concept. The reactor startup, we have 10 students, including some of those students who have some experiences of startup reactor to find out how they normally follow the instruction to start the reactor. And so this process involved multiple steps, and this flow chart on the screen shows that flow chart, and some of those steps has loops. For example, A3, it's a step to control the rod, and people are going to have multiple times of touch that control and until they achieve a satisfactory level. Now, and the last one, like a load control and rod control, is another example of the control loop. And the other ones are more sequential type of operations, such as a steam generator and feed water actions. Then the general procedure for the algorithm to analyze the operation history is to use one of the approaches using Markovian approach. And the first order Markovian chain could take in the history and to find out what are the control actions has been done, and to look into those history and to predict what are the most of the people follow when they achieve to this point. What is the most highest percentage of people go to another station? So the other station will be the next control action. Then this very, very simple approach help us to generating a good understanding about for those 10 people, and what is the percentage of those people trying to do different things. For example, at step 4, we can see 17% of the people, they go to choose the beam rod control target RX, and 83% of those people, they choose to touch the steam generator. And from here, we can find out what is the most frequent path from the beginning to the end people follow to finish the startup procedure of a reactor. Then we want to take a look at exactly what if the frequency matters, then is the major population or the majority of people doing the right thing. We assume that's correct, then we are going to have the computer algorithm try to learn from those and to find out if most of the people is doing this, then the outliers might be something interesting. I agree with many of you, maybe you have more experience than me in this type of research, is the majority of people might not be make the right decision. And sometimes a small portion of people choose the optimal decision. And we are trying to use a reinforcement learning approach to distinguish which strategy we identified from the control history is going to leading to most of the reward. Reward means we have a safer, more efficient operation. Now, once we have the historical data and we have a Markovian chain, and we use the Markovian chain to do a prediction to say, oh, based on those historical data from those controllers or operators, are we able to predict for their next control action? So this prediction actually has a little bit limitation. We can pretty successfully predict the transition from one state. For example, I'm touching this control, I'm using this valve. Now I'm transferring to another valve, and then the system always has like a one step lagging. And we realize that the system try to maintain the original state, but only after they notice that there is a significant change to another focus, they are going to follow you and change to a different one. So of course, this is not satisfactory, and we are considering maybe to achieve more like a real-time response about this is supposed to be the right control action, and we should learn from the control history. And it's not just one step ahead or one step behind. What we are trying to do is that we look at the sensor data at the same time people are taking the action, and to see for that time point, what are the readings of those sensors? Could we training the computer model to say, because we have these observations, that's why this person doing this. But we think that baseline model has a problem, because people usually notice a few things beforehand and then taking actions. But the question becomes, how big is that window? We are exploring what are the process patterns within that window and how big that window should be to help us to achieve more reliable prediction of the next control action, and what is the right timing for people to do the right thing. Then, so once we have this idea, then we want to learn from the history and try to understand, should they wait based on the planned parameter right now, or should they taking actions? What we find so far is that we have 5 logs from our control experiment. Then we do data normalization, feature selection, and train a machine learning model. And once we find out this model has different features really matters. And actually, one sensor called delta T, we only pick that sensor. It actually achieved pretty high testing accuracy and validation accuracy. And we're still exploring what is the best combination and in what scenario the sensor, which sensor is the most important sensor people should pay attention to make the right decision. From now, we can say only delta T seems like to be the most critical one. Another problem we noticed so far is that the imbalanced data cause problems. Imbalanced data, for example, people, most of the time, they're not doing anything. So most of these data samples, it's like people are not doing anything. So that kind of imbalance cause problems for the machine learning algorithm. Machine learning algorithm tends to only change when it just learns the very, very strong signal from a lot of samples. So we are trying to do subsampling or in-sampling, different kinds of ways to deal with this imbalance problem and to make sure that the prediction will be more reliable. This is still ongoing work. For the computer vision part of the research, we have been looking at the positioning algorithm, path planning algorithm, and for the positioning algorithm, we try to localize the worker based on the inertial measurement unit data, acceleration data, and the camera video data. Then for the planning part, we consider the safety constraint introduced by the job site condition or based on the output of the reasoning algorithm to find out which area the worker should avoid. We collect data from 2 places One, it's both places are has a very similar environment as a nuclear power plant. Actually, 3 places. The third place is a Duke Energy's training facility. So this place I show on the screen, it's a mechanical room on Carnegie Mellon University campus. And we find out that the algorithm we tested could generating the path from the original location, the worker located, to the destination location. And it's able to adjust the path based on the information we introduced, added into the model, such as this area is dangerous, should avoid, and it's going to produce a different path. And we use a 3D laser scanning and video navigation data set to further improve this this algorithm and to make it a real-time adjustment for safety reason. Then we labeled 1,500 frames from the video, and for those objects which is related to the control of critical loops. For example, in this case, we are collecting data from the mechanical room, and which is controlling the water loop, and we label the valves, meters, and the electronic chemical tanks, control valves, electronic cabinet to teach the computer those are the objects we should pay attention, and the object should be able to pick up those objects automatically. Very interesting observation is, if we train the data from a mechanical room, could we apply the model trained from this room to a slightly different room, which is the nuclear facility, which has a similar object but is a different room? We can see that on our mechanical room, it achieves very high accuracy, but we know that it's going to be very we cannot achieve this accuracy for a room which is slightly different from the room we trained our model. And we did the testing by using our model trained on a water facility, which is also industrial control room, applied it to the nuclear power plant training facility owned by Duke Energy. And it actually can pick up a lot of those control valves pretty much correctly and reliably. The conclusion for this whole research is we are trying to have a historical data analysis methodology to help us to learn from the sensor history and the human action history to understand the operation process, to predict what is the safer and the critical sensor data people should pay attention when they are operating a nuclear power plant. And we also find out that the computer vision algorithm can support the real-time visualization of those critical objects and the critical sensors from the real-time video carried by a mobile video camera. And the future work, we want to improve the context-aware reasoning algorithm to make sure the performance analysis, process analysis more reliable, and predict the control actions with higher accuracy in different scenarios. And we talk about the eye motion data, but we haven't really integrated the behavior of a human observation into this model yet. And we want to know that maybe an experienced worker know where to pay attention, and the computer can learn from there. Then computer vision algorithm, we want to testing and improve the model, and also improve the dynamic safety path planning part of the work, because right now it's more like a static test. Thank you. Hello. Hi, Greg.
Right, I was looking through questions. I don't see any new questions, so thank you very much for your presentation.
Thank you. Thank you.
Yep. Running just a little ahead of time still, so double check to make sure. Kyle, are you online?
I am here. Can you hear me?
Yes. All right. Well, thank you, Pingbo. We're going to transition now then to Kyle Reed. Kyle's going to share their work on the Rad-Hard electronics and data communication. Give you a second to bring your presentation.
Yeah. Go to the right screen. here. Let's see. Oh. Let's see. Do you see my screen?
Yes.
Oh, wrong button. All right. You still see my screen?
Yep. See you. Yep, and hear you. So we're ready to go. Thanks.
Awesome. Let me see if I can clean up my screen here so I can actually see my presentation too. Let's see, how do I hide this? Hide. Oh, do you still see my screen?
It's gone back into edit mode. There's presentation mode.
Awesome. See if I can hide this. Well, maybe. Okay. All right, just start whenever.
Yes, sir. Thank you.
Thank you. So my name is Kyle Reed. I'm a researcher here at Oak Ridge National Lab, and I've been focusing on radiation hardened instrumentation, sensors, and electronics, mainly the electronics to run sensors and to be able to move the electronics closer to the sensors to eliminate kind of any EMI, increase the signal to noise ratio, increase signal integrity and fidelity to ensure better and more safe controls and communications for reactor environments. The project goal and overview of what we've been working on is the survey of the state-of-the-art electronics that we performed last FY, so FY20, which then moved into taking some of our previous work and seeing what is the actual radiation limits of the devices, because we had only previously tested them up to 1 megarad, but the technical survey suggested that it could potentially go further than that for the electronics that we were using. We also wanted to start looking at other types of devices into more in greater detail, so specifically wide bandgap devices. The participants of this project are Dr. Nance Erickson, who's the PI. Of course, there's myself and Dr. Diane Ezel, who is the work package manager here at Oak Ridge National Lab, and Dr. Chuck Britton. Kind of the summary of accomplishments going back to FY20 is we performed this and reported the state-of-the-art electronics and up to date what their failure mechanisms were, what kind of changes they had under different irradiations, what the limitations of them would be, to try to identify what's the best technology to move forward with for the different applications in reactors or casks or anywhere in the terrestrial nuclear environment. Whereas in FY21, our accomplishments were to successfully irradiate a circuit to beyond 100 megarad silicon and establish some error corrections that were due to radiation drifts of the sensor frequencies. We also put another report together which talked about the limitations and where wide bandgap transistors, which are emerging technology right now, much less mature than traditional silicon-based transistors are, which these devices, wide bandgap devices, have a great temperature tolerance, and now they're being investigated into what their radiation limits are and what the effects of radiation on those devices are. The kind of technological impact of this research is identifying and establishing the next directions of electronics for reactor environments, which can be placed closer to sensors, have mitigations for radiation induced errors and effects that are apparent on circuits, and really just to push us further into being able to electrify and have sensors in reactor environments for better and safer control. And of course, we're looking at how this will be commercialized, because if we can now start to push these sensors and electronics further into the radiation and temperature environments of the reactors, there's so much opportunity to commercialize this technologies. Kind of get started here on the research side of things. Space is the most prominent market for radiation hardened devices, mainly for low Earth orbit satellites, some extreme environment for like Venus exploration, as we see from NASA a lot. If you're keeping up with a lot of the things that Elon Musk does, one of the things that he's right now working on is Starlink, which is putting low Earth orbit satellites to increase communication across the globe. So these markets are really what drives the research for radiation hardened electronics. But the radiation environment space is vastly different than for the nuclear reactors. Space, for one, there's no neutrons, and the total ionizing dose over the duration of the electronics are going to be very low, but they'll have sporadic, very high dose rates, whereas terrestrial environments we're going to be more focused on high dose rates, high total ionizing dose, and the neutrons. The neutrons will, of course, have effects on the electronics through the displacements of the atoms in the electronic lattice structure, which is mainly associated with minority carried or removal, some transconductance gain decreases, and kind of things along those natures. Ionizing radiation, of course, through electron knockoffs, you create charge traps in the oxide regions of transistors, or really any dielectric starts to become more conductive because you're moving the electrons from the valence band to the conduction band, creating the free electrons and free holes that were once bounded. So now the dielectrics can become more conductive. Charges are starting to flow where you didn't intend for them to be flowing, and you're going to be starting to build up charges within those regions. So basically any sort of charge sensitive device like a capacitor, transistor, diode are going to be the most sensitive devices to radiation, with these kind of semiconductor active devices being definitely the major point of failure for electronics. So this is a table here of kind of what the state of the art is for the different kind of topologies of transistors and diodes, what their dose limitations are for total ionizing dose and for neutrons. And kind of from this, we've postulated I've been researching and testing JFETs, because JFETs, as you can see from the table, are going to be on the high end of what you can get to from the total ionizing dose standpoint, but they're going to be roughly the same for the neutron damage levels until you start moving to the wide band gap, like the silicon carbide JFETs, as shown in the table. And so from that survey we did last year, we've put together this roadmap of these are kind of the pathways that are typically followed for radiation hardened electronics in their systems. So you can either take the space rated commercially available approach, where you leverage what's on the market for space rated systems, knowing that they're not tested for neutrons. They'll have limited gamma hardness because they're really only trying to be the last 1 megarad, maybe in some extreme cases 10 megarad, but to be considered radiation hardened, you have to just exceed 1 megarad. Another approach would be to kind of take a component wise approach to putting together a radiation hardened system based on just discrete components of JFETs, and rather than forming a ASIC or a integrated circuit, you're now doing that kind of just on the bare bones components. So you're going to have a large circuit, but it's going to have a high chance of reaching the high gamma hardness, but it'll still be relatively weak to neutrons. The other approach, which is going to be more costly in time and money, is to actually design integrated circuits from the ground up of now incorporating radiation hardened by design techniques, using the latest and greatest of the semiconductor materials, and designing these from the ground up to reach the best level of neutron hardness and gamma hardness. And now, kind of for the research, this has been leveraged off of a previous neat project that we had, which was led out of Virginia Tech by Lei Zhao. We also participated with the University of North Texas on this project, and this was to build a system to monitor temperature and pressure inside of a spent fuel storage cask. But this approach can be applied more generally to any sort of other applications in the nuclear environment, except for the fact that casks are relatively low neutron emissions comparatively to the ionizing radiation. And for this, we had a device that would sit inside the cask and transmit outside of the cask through piezoelectric transducers. And so our circuit would be to take a temperature pressure sensor, modulate that into a frequency, and then modulate that to be centered around the resonance frequency of the piezoelectric transducer to transmit outside of the cask. From this, we decided that the frequency encoding is going to be probably the best in terms of signal to noise ratio comparative to an amplitude encoding. There's lots of noise that you can get on amplitude signals, but you can get a very stable oscillator that has a very low signal to noise ratio. One such is a RC phase oscillator, which if you can imagine a RTD or some sort of resistive temperature device, thermistor, or something like that, you can now use those as the feedback element in this circuit to change the frequency as the resistance changes. So in that case, R1, R2, and R3 would be replaced with an RTT of a similar temperature coefficient, so that the resistance changes with that function of temperature, and then the frequency would change with the changing of the resistance as shown in the equation below, where that frequency is driven by 1 over 2 pi, the resistance and capacitance times square root of 6. And over in the plot on the right, we can see that from the circuit that we built and tested, that the actual changing of that resistance follows pretty closely to this theoretically derived frequency. And we do see that our magnitude increases. This is actually because the capacitor, which is the source capacitance shown as CS in the schematic on the left, acts as a high pass filter for the circuit. And so the gain is going to be a function of what value of that capacitor is. For the, can you still see my screen? I'm getting a notification that you can't.
Yeah, I still see your screen.
Okay.
I also concur, I can see your screen.
Okay, thank you. Don't know what this notification is. So, and you see the Gilbert mixer, right?
Okay, so, I'm looking at the blowout of the micro.
Okay. So we have a Gilbert mixer here, which is what we use for the mixing element. The Gilbert mixer is very stable, has a very high signal to noise ratio, low harmonic contents for those. And so kind of one of the drawbacks of using JFET technology for a Gilbert mixer is that JFETs are not very well matched for their current voltage parameters and transconductance gains. And so to be able to have a good mixer, which will suppress the carrier and suppress any of the baseband signals, these JFETs have to be matched, and we had to match those by hand. And for this, we took a measurement of them, and we found that the carrier leakage is about 20 decibels, which isn't the best. Some of that is again from the mismatch of the JFET. Some of it will be from the mismatch of other internal components like the drain resistors shown at the top, RDL or RDDL and RDDR. which leads us into leakage. The full circuit schematic, please let me know if the screen isn't following along. So the full circuit schematic, we show that we have this local oscillator, which is a Colespitz oscillator over on the top left. We see that we have the a temperature sensor down, which is the RC phase oscillator on the left. We have another sensor, which would be a pressure sensor down kind of in the bottom center. For the pressure sensor, rather than using the resistive feedback elements as sensors, it would be using the capacitive feedback elements as sensors. These are both fed in and added together just through a passive adding circuit into the Gilbert mixer, which is shown there in the center of the screen. The Gilbert mixer is then amplified to drive a piezoelectric transducer, where the amplifier that is shown in the right in the purple box, and the PZT is shown in the red box to the right.
Yeah, I don't see any of those colored descriptions that you're describing, so we might not got stuck on one of your frames.
Okay, let's see if I can.
Yeah, the heading I'm seeing on your slide, Kyle, is RC sensor oscillator. That's what I saw last.
Okay, let's see. So what do you see now? Do you still see that?
You're in edit mode now, and it's the main intro slide.
Okay. Now do you see the schematic?
JFET systematic?
Yeah.
Or schematic, sorry. Okay, yeah.
Yes. Awesome, thank you. So I can go back real quick just to show off the Gilbert mixer, so you can see what I'm talking about there. Again, it's right here in the center of this slide in the green box. The local oscillators in the blue box to the left, and the temperature and pressure sensor there at the bottom, the PZT driver and PZT over there on the right. Now for the modulation and signal theory, this is kind of the basic theory of how this system is operating. Is we have the local oscillator, which is a sinusoid frequency, and we have the sensor, which is also another sinusoidal frequency. So when these two signals get multiplied together in frequency domain, they become the impulses at the sums and differences of the frequencies. That is the positive, or the frequency of the LO plus the frequency of the RC oscillator, or the frequency of the LO minus the frequency of the RC oscillator. From this, we can actually take advantage of some sampling theory and oversample rather than try to demodulate, which gives us a very straightforward approach to decode where the signal is, which is now taking half the value of the upper sideband impulse and the lower sideband impulse, which gives us the estimate of the RC. And of course, as we integrate more sensors into this using frequency orthogonality, this equation expands really simply as a summation of all of the sums and differences of the sensors to the local oscillator frequency, which is due to the linearity of the Fourier transform and all this goodness. And so down the bottom left, we can actually see in frequency space what the sensor signal looks like, and we have the sensor fundamental, sensor harmonics there, because it's not a perfect sinusoid, but it's fairly close. And on the right, we see that after mixing, we have the upper and lower sidebands of the fundamental. We have the upper sideband of the sensor harmonics and the lower sideband of the sensor harmonics, and some local oscillator leakage there.
Well, we may be having some freezing or technical difficulties here, Kyle. I don't know if you can hear us or not, but your video is frozen and we can't hear you. So we'll give Kyle a minute to rejoin us and I saw one question come through, which I'll ask at the end of the presentations, but if anyone has any other questions, they might want to write them in. We'll get those once Kyle rejoins us. Hi, Kyle. All right, we can see you moving again.
We can see you now, Kyle. Oh, looks like his audio disconnected for a moment.
Yeah.
Can you hear me?
We can hear you now.
Okay. Can you see my screen?
It looks like it's still in, it's not in presentation mode.
Yes, okay. Where did I lose you? Was it on this slide?
It was on the
Basically,
transition into the slide, yes.
Okay. So for this, we redesigned our circuit board from the one that we used in the previous NEAT project to fit inside of a Cobalt 60 source there at Westinghouse in Pittsburgh. We didn't get a uniform dose across the board, and so when I speak of that we tested the board to 100 megarad, that is actually the lower edge of the board, which as you can see from the circuit, that would be the lowest total ionizing dose as seen by the circuit itself. So most of the board received more than this, which is good. And we actually tested one board to 200 megarad at this lower edge. And so in the center of the board, for both of those cases, in the 100 megarad test, the center of the board received 170 megarad, and then the 200 megarad test, it received about 340 megarad. We captured data at 10-minute increments from an oscilloscope and recorded the RC oscillator signals, the Kopitz oscillator signals, and the output of the Gilbert mixer. Kind of a picture of our experiment setup is there's the actual PCB on the left without all the parts stuffed before we irradiated. We did have all the parts stuffed when we did irradiate. We see that a picture of the JFET and the dummy source is a nice close-up of the nice close fit to be able to irradiate these. And on the right, we see the JFET PCB actually inside of the actual Cobalt 60 source during irradiation, which below you can see a test of the PCB when it's inside of the dummy source. And for the good part, the results, there's a lot to go through here, is we start to see this frequency drift on the sensing oscillator and the local oscillator, which is due to a drift in the capacitance value. The capacitance changes exponentially with dose and dose rate. And so from the equation, we see that previously shown that these sensors will also drift in frequency exponentially from the change of capacitance. So that explains that. We do see that it starts to plateau off, which is good. But for 200 megarad, everything survives. We see that for our demodulation algorithm that we're running, that we estimate to be within 5 hertz of the actual RC sensing oscillator. So that estimation is correct. And the magnitudes of the signals, except for the initial source insertion of the radiation, is pretty flat for most of it. And up in the top right, we can see that if we apply one of our early techniques for frequency calibration or error correction, that we drop from a about 16, almost 17% error on the RC sensing frequency to about a 2.5% error on that that frequency. Overall, the test, the voltage, of course, since we were using a DC power supply, stayed constant. We did decrease our current magnitude slightly during the test. But overall, the circuit performed well through the 200 megarad. So even with these frequency drifts, we note that the circuit performed and operated correctly, that we can also compensate and correct the frequency drifts due to the change in capacitance and the sensor, and well, don't technically need to in the local oscillator based on this approach. And so all those circuit works up to 100 megarad, even up to 200 megarad. We're continuing to investigate various techniques into the frequency correction. We recently submitted a journal paper to ANS overviewing the results of the irradiation. We plan to submit another paper to ANS here soon over the error correction mechanism, annealing effects, and other temperature effects on the circuit. And I'm using this research for my PhD topic, and I am about to actually start writing my dissertation. We have a few invention disclosures going in over some of these error correction topologies and other discoveries we've made in this research. And we have also written a technical memo for the wide bandgap semiconductors and what their state of the art is in the electronics at the moment. And then some fun stuff for future works is Dr. Nance Erickson is the PI on one of the most recent NEAT awards for studying GaN-based, which is a wide bandgap material, transistors, and to create more complex circuits using OSU's GaN process there. So we can actually start moving into the digital world better and seeing what kind of techniques we can come up with there for sensor encoding and transmission. Also, Dr. Callie Goetz has been awarded a direct funded project for radiation hardened front end digitizer, which we have dubbed FRIEND. In this case, they're looking at radiation hardened techniques to digitize a signal right at the sensor and transmit over an optical fiber to a different location that would be less radiation intensive. So with that, I can open the floor to questions.
Okay, Kyle, thanks for that. There is one question, and it's asking about the use of vacuum electronics. Wondering if you've considered that or have an opinion on where your application versus vacuum electronics would be appropriate.
Yeah, so vacuum electronics are actually probably the most radiation resistant of any of the devices that are out there. They do have drawbacks with some size and other aging mechanisms for them. Not that normal transistors don't age either. There also are higher voltage concerns and space requirements. I think the latest and greatest for the vacuum technology is kind of the micro vacuum tube, which is making them a lot smaller. And I don't think they require as much voltage to run, because the traditional vacuum tubes require several hundred volts, which can lead to some unpleasantness when designing for if you're not careful. But I think it also, if I remember correctly, as these devices are getting smaller, they're starting to become affected by their radiation. I guess mainly due to the proximity of I'm trying to remember from the vacuum tubes what the full structure is. One of the nodes on the vacuum tubes, you start actually building up trapped charges there, so they do start to become less radiation resistant as they're getting smaller. If that answers your question.
I thought it did, and I know there's different considerations and applications, so appreciate your on that. So thanks, Kyle, for your presentation. Again, we'll be having a panel session this afternoon, so if anybody thinks of follow-up questions or ideas to discuss in that session, we can circle back around to this topic. So thanks, Kyle, for an update. And I'll open it up now to Pattrick. Coming up to the break time for lunch, but we've got a few minutes before the scheduled time. So if Pattrick's available, turn it over to you before we break for lunch.
Yeah, thank you. I don't have anything to add. I think the questions have all been fulfilled. So I think we should just add 10 minutes to the lunch break, which means that we're reconvening, which have been short in this in this meeting in general in this week. So we'll reconvene at 3:20 as planned. And Greg, if you can leave, yeah, perfect. That would make it obvious to everyone.
Mm-hmm.
I was also going to announce, but I'll just anticipate it now, that we may not have one of the planned presentations. That's from AlphaCore. So I will check during the break and come back before we restart. We may therefore compress, have that next presentation first, with the possible ending the meeting half hour earlier. But for now, I'll continue to check with AlphaCore, and I'll provide more updates when we restart. And so we'll get back here at 3:20 or 5 minutes earlier.
Okay, thanks, Pattrick.
Thank you. Good afternoon, Greg. I don't know if you're intending to talk. Do you hear me?
Oh, hello.
Okay. Yeah. I just want to make sure you were not trying to talk to us. We still have 5 minutes before the presentation starts. In theory, we're starting at 20. But
Okay.
yeah.
Is there a place I don't see where to share my screen?
Oh, so you will let me do that. You will receive a request essentially.
Okay.
If you accept the request, then you should be the one sharing the screen. Yeah, that works.
Can you see my slide? You see my slides?
Yes, I do.
Okay. Okay. I wasn't sure. I've got two screens. I wasn't sure which one came up. So.
Yeah. Oh, that looks fine. If you want to try advancing, just in case, but it should be okay. Yeah, that's perfect. You can go back to the front screen if you want. So we'll wait 5 more minutes, so in case people that were catching up.
Sure.
We'll start sharp at 3:20 your time.
Sounds good. Thank you.
Hey, Greg. It's Craig Primer. Guess I'll kick off this session if you're ready.
Greg.
Sure,
Craig,
go ahead.
Just a quick announcement here because I need to contradict myself. So we will have the presentation from Alpha Core. So just before I mentioned that we may have a hole in the program, this is not the case. So the agenda will continue as planned. And Greg, you can start anytime. Thank you.
Perfect. Okay, thanks, Patrick. All right, welcome, Greg. We got your presentation showing and I could hear you, so I think we're all set. So welcome everybody back from the lunch or afternoon break and get started off in the last session, starting off with Greg from AMS, giving us an update on fault detection and digital instrument and control systems using integrated electromagnetic compatibility. So Greg, if you'd like to start, appreciate you joining us.
Thank you. Yeah, so this is a project we've been doing. We're in a phase 2 project. I'm the principal investigator. I'll go ahead and just get into my slides here. So just a little background on AMS. We're in I&C maintenance. We've been doing that for about 50 years. I want to say about 20 years ago, we kind of got into some EMC and wireless testing and cable testing. And we also done some work on software reliability testing for digital systems. And so this project kind of integrates those two areas of automated functional testing or software reliability testing of a digital system and the EMC wireless testing, EMC compatibility testing. So let me go on into what we're doing with this project. So the goals of this R&D really are to take the hardware and software that we have from these two different areas and automate that and integrate it into a combined system so that the testing can be done more readily, more efficiently, and it can uncover faults that are in the system that you may not be exercising in a traditional EMC test. And I'll talk about that more in a minute. We're currently in the third year of our and final year of our funding. I'm the principal investigator, and I'm the chief technical officer of AMS, and the internal project manager is Dan McCarter, and he's been with AMS for, I think, 10 years or more. Okay, so what is electromagnetic compatibility testing? So essentially, when we test a device or equipment under test, we want to make sure that it's not emitting any emissions that are going to impact the environment where it's going to be installed. So if it's broadcasting at some frequency, is that going to interfere with other equipment in the plant where it's going? And likewise, is this equipment susceptible to frequencies that are already in the plant that may make it not function properly? So one's susceptibility testing and one's emissions testing, and the electromagnetic compatibility covers both of those aspects. So functional testing is really just exercising a digital system by exercising its inputs and monitoring its output to confirm that it's operating as it's supposed to. Is it functioning correctly? In most digital systems, it's not possible to fully exercise all combinations of all inputs. So typically what's done, there's some testing done around boundary conditions. So like when you're going to cross a threshold or some event's going to happen, so you test all the control functions and the events where those are supposed to happen, all the operating states. And then you also do some random testing where you do some random test cases of some amount to kind of cover the whole operating space of the input range. So that's typically what's done for functional testing. And the idea is to make sure, is the system still performing correctly? So this testing is not functionally testing to make sure it just works normally. This is it working normally while you're exposing it to electromagnetic interference that might impact it to see if that's going to make it not perform correctly at levels that are allowable within the plants. So what are the features of the combined system that we're trying to develop? So we wanted to automate the EMC testing as much as possible, and that involves all kinds of signal generators, spectrum analyzers, field probes, amplifiers, etc. We want to automate the functional testing to make it easy to generate those test cases and model the system so that when you can run the inputs and outputs, you'll make sure that it's operating correctly. And then integrate those in a way where, as you're doing the test, it can log any faults that happen with the functional test at what frequencies there was some interference that caused a problem, for example. And I'll go into more examples of that as I go. So what's the advantage of combining EMC and functional testing? Well, you can make the system operate through a variety of its operational states. Traditional EMC testing, in most cases, they just have the system turned on in some state and they expose it to the EMC fields to see if it has an issue, but they're not typically running it through all of its operations. So the idea is let's run it through all its operational states while you're doing that electromagnetic compatibility testing to see if we expose a fault that you wouldn't normally catch. The example below just shows there was a relay we were testing, and at a certain point in the testing, because we were monitoring this by exercising its functional states as we were doing this test, it actually encountered a problem at the 175 megahertz to 200 megahertz where it actually didn't perform in the response that it was supposed to perform in. It actually was slower. And an example on the right relates to when they had it in a certain state where they thought it would be the highest current level, which would correlate typically to the highest electromagnetic fields that it's emitting. We found out that when we ran it through its operational states, one of the states that they don't normally test it in actually had a higher current output. So it actually had higher fields and higher emissions. So that was actually the state that it needed to be tested in, as opposed to what they thought originally it should be tested in traditionally. So that's just two examples of what's the benefit of doing this testing. At the end of our phase 1 project, we were able to test a digital controller and identify a susceptibility at 16, 16.5, and 17 megahertz. This was just a fairly simple system that we were testing, and we did define this problem. So had we not done the automated functional test, that would not have shown up under the electromagnetic compatibility test. So even at the end of our phase 1, we were already seeing some benefit to this process. So in the year 1 of the phase 2 project, we actually were able to demonstrate the automated functional testing on a commercial system. So there was a manufacturer, an OEM, that had a component of a digital safety system that was FPGA based. It had over 800 data channels. And so we had to expand our automated functional tester to be able to accommodate this test facility. And that was done early in this first phase. So that's just a piece of the combined system we're building. But we were able to enhance the automated functional test in the first part of this phase 2 to cover these other these large amount of test cases, large amount of inputs and outputs, and how to handle all the timing for that. Also in year 1 of this project, we did a lot of automation of the EMC test software. So a lot of the tests traditionally are done one at a time, and they use different pieces of equipment, different spectrum analyzers and signal generators based on the particular frequencies that standard test requires to be performed for that portion of the testing. And so under this part of this project, we added some automation to those things to allow it to connect with the automated functional test, so that when we integrate that, which we're doing at this time, they're able to actually communicate with each other and log information. So when stuff's happening at the same time, it can be tracked. So we've done a lot of steps to do that. And the ones in blue there, the RS-103 and the three other standards there in blue, those are tests that were done in year 1 of this. The other ones that are in white were worked on in another project to also help automate the system, but those weren't done in this phase of the project. But all that's being integrated together into this combined system. So there's a lot of individual EMC testing that's performed for digital systems that now it's going to be able to be automated with the automated functional tests. So we're making good progress in that area. Another thing we added in year 2 of this project is we added some machine vision to the system. So we have some cameras inside our EMC chamber, and we can put those cameras. This is just an example where we installed it on to watch a gauge and to watch a meter, just to evaluate the functionality of machine vision. And so in a lot of cases when this testing is being performed, they have a camera watching that, but somebody's got to sit there and monitor that. And in a lot of cases, it's just recorded to a video file, and then somebody has to go through the video file and just, if they hadn't, make sure nothing changed states when the system was operating. And so we're trying to automate that whole process to detect in real time as things change state from an image. And then that's correlated also with automated functional tests. So again, to see that there's some problem occurring in the system that's being tested. In another application of that, we have a screen that had a test pattern on it, and we exposed it to some faults with some electrostatic discharge testing. And the one on the left, you can see there's kind of a ghosting where there's a little bit of the lower image a little bit higher up, and we circled it in red. And on the right side, it was a very subtle change in that black square in the top right, where there's a little bit of a ghosting down of that line. It kind of like replicated a little bit lower down. It would be, and that only happened in one frame. And this video is recorded at 20 frames per second. So in this 50 millisecond window, there was only one little frame where that little ghosting glitch occurred. And some things like that, these little subtle impacts to a system on a human-machine interface would be hard for a human to detect. But by automating this process with a machine vision application, we can find susceptibilities in the system. Now, this error is small, and it may not be a problem for a human when the system is actually operating, because if it does that occasionally, it probably wouldn't be a big issue. However, it shouldn't do that at all. So it revealed there's a susceptibility at that point in time when that test was going on. So that's something that needs to be looked at, because it could degrade over time. So little things like that really can show the advantages of doing a machine vision application. That's just another portion of the automation we're doing with electromagnetic compatibility testing during this year 2 of this phase 2 project. Now, so I've talked about some of the pieces. So what we're trying to do is trying to integrate all of those pieces together in a combined system. So we have the EMC test equipment portion and EMC software, which we've automated, and that's in that little top red dotted box. We have the software reliability tester, which we're using as portion of the automated functional test, in the bottom box, which is equipment and software. And then we also have the machine vision that I talked about. We have also some measurement test equipment logging from DMMs and scopes and other equipment. So all that information data is being collected while EMC tests are being performed. And then we've built this architecture to communicate all that information back to this test executive, which monitors the automated functional test and the electromagnetic compatibility testing. Sorry, just can't say it today. And it's monitoring that all the time. So if something doesn't happen at the right time, it monitors that fault. And what does that look like? Well, this is one of our example screens that we've got where we were injecting some faults into the system. So one of the things we're monitoring for is what time did that fault occur. So if the automated functional test detected that some part of the system did not operate as intended, so the time when that fault occurred is logged. And then it also tracks the frequency from whatever EMC testing is being performed at that time is also logged. So that allows us to identify that there was a susceptibility at that moment. And then if that's not conclusive, we could go back and retarget more tests around that frequency to basically isolate what happened at that time to help uncover if there's a fault in the system, if it needs to have more shielding, does it need to be redesigned, does it need to have something to help harden it against EMC, or is there actually a fault in the system itself with the way it's operating? Maybe you could uncover designed in faults also, or it could be some kind of manufacturing defect in the equipment. So there's a lot of good information can come if you can find these instances. And this just shows an example of how all that is put together. Let's see here. So just to summarize, the project goal again was to develop a simultaneous system that performs EMC and automated functional testing on digital devices for nuclear plants. Our accomplishments: we combined testing to identify susceptibilities in a device, digital INC device. We've developed several EMC and AFT systems to automate the testing analysis, and we've demonstrated an AFT software component on a component of a digital safety system. And we're working on implementing the architecture now that we've developed for the entire system for all the components and pieces. And once that's completed, then we have to validate all of that application, and that's what we're doing currently, and that will be finished in the coming months. Related publications and information, we had some other reports we published on another project related to the software reliability testing portion that we did, which is unrelated to the EMC. It's just for the part of the automated functional testing piece. So that was under another project, and that's in that report DOE 1703R0. We have our final report of our phase 1 that shows what we did in the first phase of this project. And then we've had some papers we've presented at ANS and at the MPIC HMIT meeting last year and this year on 2 of the aspects that I talked about today in a little bit more detail are in those 2 papers. I think that's all I have. Do I have any questions?
I'm looking at that right now. It doesn't look, no, there's no questions at this point for you, Greg. Appreciate the presentation, and looks like we'll go ahead and transition on to the next presentation.
I have a question, Craig, as we transition.
Oh, sure.
So yesterday we saw a presentation on another SBIR project from your company. Just to clarify here, the added piece to this project that you're discussing here, it's the functional testing, but the hardware itself for the EMC is the same. Is that correct?
Yes, a lot of the hardware for those specific tests, like a certain radiation susceptibility test, that's the hardware for the test itself is the same. Yes.
Okay. So, and a lot the functional testing, I assume, will be specific to the plant. So, in your case, I know your company is very much focused on operating plants. So that's how you are basically allowed to define processes to the level, because you basically have a very experienced, I mean, you know perfectly the plant, right? You're there all the time, you know, and so that's how you can dwell into things like processes, which I assume for different applications that would then be very much design specific. Is that correct?
Yes, some of the automated functional testing, you have to have information from the OEM on how some of those work to be able to model it properly. So yes, you have to have sometimes a non-disclosure with the OEM to get that information to help model it correctly. Yes.
Correct. An OEM must exist. So for advanced reactor, for example, okay. So I just want to make sure I understood properly. So thank you.
Yeah, good question.
So we can proceed now, Craig, anytime.
Okay, perfect. Thank you.
We can or we cannot, actually. I'm following, try to understand it. AlphaCore has actually joined the webinar.
All right.
We had received the email. We had an email exchange, but I haven't seen them. Oh, there you go. Perfect.
This is a good, yeah.
Thank you.
All right, so welcome. We much debate on whether we'd have this presentation, but it looks like we will. So thanks for joining us. So we've got.
Hi, can you hear me?
Absolutely, and we can see your presentation as well.
Okay.
I don't know if you want to go to full screen or not, but we can see the first slide that says project overview.
Okay, just a second.
Perfect.
Good. So
you want to introduce yourself and kick it off? We'll turn it over to you. Appreciate it.
Okay. Thank you for the opportunity to present our work. My name is Esko Mikola. I'm the CEO of AlphaCore. I'm also have a technical background in CMOS image sensor design and radiation effects and hardening. So we changed the presenter to me from the PIS and Salsin, since we're mostly talking about our chip design and the radiation hardness for the year 1. So the name of our SBIR Phase 2 program is Video Camera for Harsh Environments in Nuclear Energy Applications. And here is a little overview about the project. So the objective is to design a high frame rate video camera that is also extremely hard to very high levels of radiation. That type of camera does not currently exist. And in terms of nuclear energy research, We are communicating with researchers from INL, especially with Kevin Terrill. We want to thank Kevin for helping us in this program. So one specific test, for example, that this camera enables is in the nuclear heated transient testing, test called reactivity initiated accident simulation with video observation of transient water boiling. Additional goal is that we strongly want to commercialize this, and there is a limited market for very high speed rad-hard camera, but a larger market for nuclear facility inspection, very high radiation hardness, low cost CMOS camera. So we have a partner who is going to commercialize this. And then we have also hardened this for space radiation. It's a slightly different circuit techniques needed there, but we thought that it's worth it. So now we are basically also, our customers can be from the booming space market. And we, like I said, we have a subcontractor in this for a small subcontract who's a large nuclear industry camera and robotics manufacturer, and they are helping us to understand how the state of the art cameras work in this industry. The next slide is number 3. So the first motivation is the frame rate. If you look at these, what we would call ultra rad-hard cameras that are suitable for these type of environments, a very popular camera is Diacon D40, and it's an analog camera, so we have the pixel quantity is basically effective pixel quantity as is the frame rate, but that's shown on the right. So roughly 700 by 500 pixels at 30 frames per second. That's definitely, those specs are very much lacking for this research that are needed. So we are developing 2 image sensors in this program because there's a big trade-off between how fast the camera be and how rad-hard it can be. So we are able to make a very, very rad-hard camera up to 1 gigarad in CMOS that provides almost a megapixel at 120 frames per second. That's the Alpha Core sensor B here. And we also have this feature that when you take a smaller areas from there, you get much accelerated frame rate. So still for pretty good resolution 256 by 256, where you can see something in the image. With this extremely rad-hard camera, we get about 1.4 kilo frames per second. This feature is not typically in rad-hard cameras. And then we are designing another camera as well that uses less hardening techniques, and that enables much higher frame rate, and that is for a full VGA starting point 1.5 kilo frames per second and going all the way to 7,500 frames per second at 256 by 256. That's the first motivation. Second one is that if you look at from the point of view, what could the already available high frame rate cameras do? And so we got some and we started testing them for total ionizing dose. And here is a typical result on the left. The left is the normal snapshot, and on the right, just after 3 kilorads. Whereas in nuclear energy reactors, we are talking about hundreds of megarads. And problems started showing up already at 900 rads. So we need orders of magnitude better radiation hardness. And Then on the okay, this is named C here is. This is how we test our image sensor. So here is an existing image sensor we are testing that was not hardened for such a high radiation hardness, but the result is, for example, leakage is the worst thing that happens there in these CMOS sensors, and we have no leakage up to the level that we tested, 125 kilorads. That is very good for space. Then next slide. Okay, the last motivation is that the typical cameras currently used for in this industry are based on quite old technologies like cathode ray tube type of devices, which is, for example, Vidicon. I think most of the cameras used in the inspections are based on this kind of 1950s technology. Whereas nowadays there are billions of cameras done in a CMOS technology, which is very manufacturable and low cost. And there's recently some. It has been thought that the CMOS technology is not good for these kind of radiation environments, but there's some recent results from Europe that show it actually is. And we are using those exact design techniques to make this available here in the United States. Low cost CMOS based programmable frame rate camera. Then the impact of this technology is, I'm just summarizing these things that I said already, is that it's a 50 times higher frame rate than what's currently available for these ultra-rad hard cameras. And we have implemented this very good programmability versus frame rate. So you can take slightly smaller areas and then you get very good acceleration in your frame rate. So this will be very handy for different types of research experiments. And so this camera basically enables new types of tests and research in the nuclear reactor research. Then we are also, this is gonna, since we are doing two different image sensors that I'm just gonna show soon, the gigarad one definitely is gonna improve the state of the art of the nuclear facility inspection applications, because it has higher radiation hardness, higher performance, much better manufacturability, and then much lower cost as well. And then as I said, we also included the needed hardening techniques for space environments. So this, and there are not that many image sensors available for the space market. This will be one of the very few, and currently has the highest radiation hardness of those, the ones that we see. The accomplishments, first out of 3 is that we have made progress on all of these building blocks needed. These cameras are very complex technologies on many different levels. So we are designing the image sensor, the CMOS chip basically from scratch, because our previous sensors don't have these kind of hardening techniques implemented. Then this will be inside the enclosure that goes to the harsh environment. We will get that from our subcontractor. One big thing in that image sensor is that it has to have this rad-hard interface that is able to push all the data through a rad-hard cable. And that's another thing that is new. People have not had a need to push a lot of data through these cables before because the frame rates have been so low. So then the data interface is there, and on the other side of the cable is then the camera control system, what is typically based on 1, 2, or 4 FPGAs, depending on the data rate, and then the whole board with maybe 20 to 30 different electronic components will be designed. We are designing it, and then the last thing you need is all the firmware. That basically the VHDL code that controls this hardware, and then the software, for example, the GUI that lets you look at the images. So we've made good progress in all these areas. Here are some accomplishments in the image sensor design. So like I said, there's that trade-off between the speed and the hardness. So that, and since INL really wanted to have the high speed, we decided to go from 2 directions. So we go for the speed, and we comfortably can get up to 1 megarad. I mean, this all needs to be tested. This is now based on simulation. And then we go from the extreme radiation hardness coming from hardening techniques, and we are looking at gigarad there, but slower camera. So we are designing both of these image sensors in this program. And for the image sensor B, we also have 2 different versions. The analog signal that is actually more straightforward for radiation hardness, and then one where we have a very, very rad-hard ADC, a novel design there that we are testing that has digital outputs. And here you see a little bit on these images, like the A is, for example, a photograph of one of our megapixel sensors. Not these ones that I'm talking about here that we are building, because they are not at this state of readiness yet, but similar sensor that we've done and tested previously. So B is the layout image, and then you see there's this yellow corner is now expanded in figure C, and you can see how small features there are. Just in that corner, there's 30,000 gates control block for this whole thing that needs to be designed. And these ADCs, we have several 100 ADCs here. And then on the D, you see that every ADC is about a few thousand transistors, and it's pitch matched, long and skinny thing needed. And then not only that, but you have the programmable gain amplifier, you have the serializer that has the clock generating PLL, phase lock loop. These are all relatively complex circuit blocks with thousands of transistors needed. And in this case, we are hardening them all with different types of layout techniques and circuit techniques that are typically done. So then next slide. The accomplishments that we've done in the first year of phase 2 is that we have come up with these architectures for these image sensors. So on the left, we saw one. We are actually doing a tape out that we are going to use lots of silicon area to test everything possible. So for these 2 image sensors, we have done one that has the optimized pixel that we think is the best, and it's a full camera that the customer could use. And then another one, a copy and paste, inside which we are trying many different versions of a pixel. Different. We have one that we think is the clear winner, but we are trying like 6 other designs as well. Testing them for radiation inside an image sensor is a very nice way to do it, because now you are in this kind of sensor, you have tens of thousands or hundreds of thousands of pixels, so you get a very good statistics for the radiation hardness. On the right, you see how this design process for image sensor go is. You start designing from basic block like the pixel. You run their circuit schematic simulations in Cadence, and then you simulate that. Here is a noise simulation is shown, and then when that's accepted, then you do the layout. Then you extract all the parasitics from this layout, which is a long list of thousands of parameters, and you run the same simulation and see if it matches. Then when that matches, then you start integrating these designs and layouts into bigger and bigger entities. And in this kind of complex image sensor, you have maybe up to 10 levels that you build from the very simple ones to more and more complex ones until you get to the top level. These kind of image sensors have tens of millions or hundreds of millions of transistors in them. So it typically takes thousands of man hours to design one of these sensors. Here is the project schedule and the milestones with these blue flags. This program started. We got the contract at the end of August of 2020, and then we have been putting together these image sensor architectures and simulating them. And then also the full system architecture, because this is not just the image sensor, but five different major building blocks. So we have got those architectures finalized, and then peripheral circuit designs ready. And the latest thing we achieved, the pixel designs are now all done and all laid out. And we are just now basically replacing in our simulations with the layouts. That's what we are currently doing, and the full tape out is scheduled for March this spring. Then there will be the camera control board design with firmware that is basically also the camera, you would call that the camera system. That's scheduled to be ready in May. Then the chips come back 78 days after, that's what the foundry told us, after the tape out. So we will integrate the full camera and start evaluating it. And then there's still time for radiation test before our final report is due in early September. Last slide, summary. So these were basically the benefits from technology. I also already told this, 50 times higher frame rate and good programmability also on the frame rate that is very flexible, design for all experiments. Enables new nuclear reactor research experiments. Then we have a partner to commercialize this in the nuclear facility inspection and monitoring market sector. This should improve and lower the cost of the current solutions. And then we are also targeting the space market sector. And so we told about the progress on all these 5 areas, and especially on the image sensor at this point. Tape out is scheduled for March. and then full camera integrated and evaluated by September of 2022. Any questions?
I'm going through. I don't see any specific questions for you. Appreciate it as.
Just one question, maybe probably the clarification, but I assume all of this is room temperature, right? I mean, the detector itself operates at room temperature.
Yeah, this stays, you know, functional up to 50 Celsius. It has been our goal. Then this enclosure is something that you could do like liquid cooling type of, that keeps the temperature steady, if you want to use it that way. There's not going to be any reliability problem or anything like that if you go even much higher temperatures, 100 Celsius, but the image quality is going to be worse. You are still going to see some image at that kind of, but maybe our partner, for example, has done in some cases this kind of liquid cooling inside the inside that enclosure, but it's not a very practical solution in every single case.
Thank you.
Yes.
Okay. I don't see any other questions at this time, so thank you very much for that. And we'll be transitioning now to the next presenter, and that's going to be Tom Grunwald. So we'll transition off. Thank you very much for joining us.
Unmute. Okay, can you hear me?
I can, yes.
Okay, super. 1 minute.
All right. And just to introduce the subject, we've got an update on the machine learning enhancement of the BWR neutron flux measurement and calibration.
Okay, I'm trying. Okay, there we go. We're on full screen. Let me get rid of some of the control panel stuff here. Okay, I'm Tom Grunwald. I'm the principal investigator on a FOA award that was primarily geared toward preventive maintenance.
Trying to share your screen. So I don't
they don't
see
see my screen. Okay, hold
Not
on.
yet.
Let's see here. Sorry about that. Okay. Okay. Can you see my screen yet? No?
No, not yet.
That's unfortunate. Let's see here. It wants me to restart GoToMeeting. Let me.
I think we went earlier with Mac. It might be a little.
Yeah, I have a Mac and. Okay, let me try again here. Okay, so it says you can record. Okay, I think I'm. Okay. Okay, all right. Let me go here. Can you see it yet? No?
Not yet. Not yet.
This is unfortunate.
Wants you to restart the system and then if that permission will kick in.
Craig,
Okay, I need to, sorry, I'm gonna have to get off.
Hey, Craig, does John Nister have the ability to share?
Yeah, so the question is, you can either send it, or if there's somebody else on your team that can share, we could,
Can you share?
that's easier.
Yeah, we have another person here who might be able to share.
Okay, who's that? We'll make him a presenter.
Okay, it's
Jonathan.
Ankit Patel.
Just a listener.
I can share my screen, but I don't have the slides, Tom.
You don't have what?
I don't have your slides, the current version.
Oh, shoot. Well, I'll tell you, it's the same version you have, except I've got them in a slightly different order.
Okay.
I'm sorry?
Is it okay? Let me pull it up.
Hold on, Jonathan. I'll send you the deck real quick as it is now.
And Jonathan, can you try and share your screen? Because we're not seeing anything from you. Okay, there we go. We can see your screen. Awesome.
Okay.
Jonathan, you want me to put it in Teams, or do you want me to email it to you?
Teams is fine.
Okay. Sorry about this, guys. Security, I guess, has its price.
Not a problem. This is the final presentation, so we don't have the luxury to swap another one. So we're just gonna wait until this is is worked out.
Okay.
Sure, that's the right.
Oh, you're right.
Today.
Okay, I know what to do.
Just going to do it. Send a copy. Manage attachment.
Okay.
Yeah, there it is.
Do you want me to share the version that I have?
Yeah, why don't you share the version you have, because I can't even get email to work now. Yeah, just share the version you have and we'll talk around that.
You want to try it again? Just go to share. Just go and upload.
You guys see this?
Okay. Yeah, hold on. Let me get to, okay, I can see it, Jonathan. Okay, folks, thank you for your patience. It's an interesting world we live in with all the hackers. So good news is we have security. The bad news, we have security. So Jonathan, why don't you go to the next slide? I won't dwell on this slide too long. This is just a quick view of the schedule. We're about a year and almost a quarter into the schedule. We've got 3 more quarters to go. The award started July 20th, 2020. The early phases were largely consumed with picking the correct project, doing economic analysis, getting the data collected and organized. And lately, in the last quarter and a half, we've been doing a lot of model development, which we'll certainly talk about right now. Why don't we go to the next slide? This is a quick look at the overview of the project. On the upper left, you get a view for the header from our technical narrative. You can see our partners there. We're partners with Exelon, Argonne, NPPD, and Exelon Generation. On the upper right, you can see the technical contributors, although we've got a number of folks working on this project. Myself, the PI, Jonathan is our chief scientist, and Jordan Heim is our neutronics team leader who works with the material we're going to talk about today, which is largely centered around LPRMs and tip trace. And we're located near Purdue University, and so we have the good fortune to have access to plenty of great interns. There have been 2 who've worked on this project, but since gone on to graduate and finish their PhDs. And then we have a new intern, Gihan Mendes, who is working with us right now on many aspects of this program. The primary, if you boil down the primary objectives, it's to facilitate condition-based maintenance, generate and develop virtual sensors, virtual calibration. As we saw this morning, there's a lot of emphasis on digital twins. These are not digital twins, but they are certainly related in a fundamental sense. The other really important aspect of this was to generate remaining useful life models for key and critical components that were major expense categories in the maintenance of a reactor. And the maintenance costs are approximately 30% of total operating costs. So to try to chip away at this aspect of operational costs was really important. And then finally, something that's really important to make all of this usable for the utility partners that we have is data management and visualization, giving folks a way to manage the data they have. Much of the data that we received for the LPRM project was actually in spreadsheets. So if I go to the left side, the lower left side of the slide, what you see there is sort of a standard O&M maintenance planning process. It starts with the ability to surveil the component using online data and historical data. And then, of course, diagnostics are developed. And then hopefully with those diagnostics and the data, you can generate some prognostication for remaining useful life, and then mitigation strategies, et cetera. And that really is independent of whether you're using machine learning or any other technique to facilitate that process. The main real issue here is to have adequate data and be able to predict anomalies at the earliest possible stage. And sort of on the lower right, it's a quick vision of the lifetime of a component. On the bottom left, you see that there's some kind of sensor reading that is a health indicator, and at some point it shows an anomaly, and that anomaly then progresses into one of many trajectories that eventually ends in some type of failure mode. And the idea then is to be able to predict that failure as far in the future as you can. And so that's, again, the overview of what we're trying to do with this particular project. Why don't we go to the next slide then? So as I talked about before, the essence of this project is to apply various techniques in artificial intelligence and machine learning to the understanding and prediction of various components in the nuclear power plant. And so on the left, you see what we called an AI-enabled framework. The top left box, which says functional considerations, in many ways is the most important, because that's where we talk with the utilities and we find out what exactly is the issue, what are their priorities, what level of accuracy, for instance, do they need, what's the economic justification, because of course you don't want to work on problems that are maybe interesting but don't really have a big economic impact. And then the next stage, once everybody understands what needs to be done, is again a really important part of the process, which is data acquisition. In this project, we were lucky to have plenty of LPRM data, but even so, there's some key components to actually ending up with data that can drive a model. The two top buttons on the right, data cleaning and handling missing values, in some sense, those are fairly straightforward because we have general rules and algorithms for what the data should look like. We can identify outliers. We can certainly identify missing values. The next two items, handling imbalance cases and data normalization, are perhaps often overlooked and but really important when you're doing a machine learning network. There's sort of a fundamental rule that says the distribution of data that you're using to train should resemble closely the distribution of the expected data that you're trying to predict, or the expected system that you're trying to predict. And we've run into cases where those things didn't really match, when all the training data, for instance, had low target values, but the future values were very high, and that makes it difficult. But there are a couple of techniques that we've used that really help this problem. One is just data augmentation. You can find new training examples and seed the existing training with that. And then the other one is something called transfer learning, where you can use a network that was trained on another particular example as a starting point, and therefore you need less data and it carries the memory of that other distribution that you might want. Then we go down to feature discovery, another really difficult and really important part of this whole process, because many times you're given many more features than you really can support in a model. And I think in this case, we have tens of thousands of features, but we're only going to use maybe a handful of those. And so there's a number of what are called unsupervised learning techniques that you can do feature reduction quite successfully. There are things like k-means, which is basically a method for finding data that is related to other data in a close fashion. PCA and things called autoencoders, which are a great data reduction technique that really helps. Now, people talked in the morning too about model explainability, and some of these techniques, however, do get in the way of model explainability. There are techniques, I think Vivek talked about SHAP, and we use SHAP extensively to explain our models and try to understand what's really driving those models. So I'll go over to the middle diagram now. What you see there figuratively on the the first black and white box, define objective. So that really tells us, what level of accuracy, what are we trying to predict, et cetera. Of course, we take the data, we do the pre-processing, and as part of that, you can see a little Pearson's correlation diagram there. That's sort of a icon for all the unsupervised learning types things that we have to do that gives us the right set of data and gives us data groupings so that the model works on a minimum feature set possible. So once you have all your data cleaned and normalized, et cetera, you always break it up into training and test data. Then you train the model, and then we score it. We have a fairly intricate way of validating the models, and then once the model is evaluated, it can be used on future data to make predictions. And so that, in a kind of a very high level nutshell, is how the process works. On the upper right, you see our outputs. We want robust metrics for the system and its component health. We'll also output virtual sensors and, importantly, remaining useful life for various components based on present measured data. And the benefits, as we strive for, are significant cost savings. In the maintenance arena, hopefully we can reduce unplanned downtime, unnecessary maintenance. And again, you reduce unnecessary maintenance by understanding when items are going to need maintenance so that that can be accommodated within planned outages. And then you can also extend maintenance if you have a good read on the health of the particular component. And then, of course, you can increase your visibility by more reliable frequent health readings if you have a good model. So the bottom of the slide here shows the two general subgroups that we're working on. We're working on the feed water heater system, some problems there. We're modeling the feed water heater level control. We actually went to one of the sites in the late summer, and we were able to take readings at the site while it was in shutdown, or while it was shutting down, and then it's pretty soon coming back up, and we'll take again readings and be able to do kind of a before and after look at the feed water heater system. We're looking at EHC tuning. That system controls the pressure in the reactor, and then we're also looking at something related to the feed water heater system, which is flow accelerated corrosion in some of the pipes. But what we'll talk about today is the other aspect of this particular project, which is LPRMs. Those are the local power range monitors. We're going to, we'll talk more about this soon, but we're going to reduce, hopefully, the need to bypass LPRMs, and we'll talk about why they get bypassed in a moment. Then we'll need a more accurate LPRM lifetime estimation. The model that's in use now to diagnose or to determine the LPRM lifetime was developed in 1995, and it's fairly inaccurate. And then we'll get to the point where we're able to have virtual LPRMs when LPRMs are bypassed or being calibrated. Closely related to the LPRMs are the TIPS. Those are the traversing in-core probes, which basically are used to calibrate the LPRMs about every 45 days to 3 months, depending on local practices. And the issue that we'll be looking at most closely is trace alignment and power adaptation. Next slide. This is a good view of how the LPRMs are laid out within the reactor. You can see on the reactor face purple fiduciary of purple dots, and each of those is a location of an LPRM string. LPRMs come in strings of 4, and they're installed with that. There's a string of 4. They span the entire length of the fuel assembly. They live inside the green circle on the extreme right. That is the instrument tube that contains the LPRMs, the associated wiring, and then there's a tube there that is used for the tip trace. The tip trace goes down that tube and then comes back out, and it does calibrated readings that we'll talk about pretty soon. Then you can see that the instrument tube lives at the intersection of 4 fuel bundles there. So that's that kind of gives you the layout of the LPRM. The one of the reasons that this project has a good level of economic benefit is that if one LPRM goes bad, all 4 have to be replaced. And so then again, the tips are put in periodically, and they have to produce every 1 inch an integrated power trace. So in other words, they have to have an accurate measurement at every inch so that the alignment can be properly determined. Next slide. So in terms of a project overview, the problem statement, as I've sort of alluded to, is, first of all, LPRMs are really critical. They're monitoring the thermal neutron flux in the reactor. So reliability and accuracy are really, really important because they are used directly to assess thermal limits and monitor the core. So some of the problems, again, as I've alluded to, infrequent calibration. And so you might have inaccurate readings, which cause real consternation about whether the thermal limits are being reached or not. Lack of visibility when LPRMs go offline or are bypassed. LPRMs can alarm either low or high. Typically, if they alarm at all, they're taken offline, but the alarm low condition is actually happens in normal operation when the axial power shape changes and the flux is very low near certain LPRMs. That's an issue because the operators still want to know what's going on, even in the low flux areas. And then finally, there's a lot of premature replacement because there's not a good lifetime model. On the right there, you see one of the tools that we've built, which is just a visualization tool so that the utility folks don't have to, the engineers don't have to use spreadsheets. They can actually point to a place on the reactor face and get the output of a particular LPRM, either over time or instantaneously. Next. This is the second part of the problem, which is the tip alignment. And the problem statement here is the auto alignment feature occasionally shifts the local flux profile by more than a full node, and it results in higher thermal limits being exceeded, the muffle pod. And this, again, is a real issue because, of course, if you think you're going to exceed thermal limits, you may derate or take other action that you don't have to. I'll turn your attention to the picture on the extreme right. You can see a blue curve and you see green arrows. The green arrows point to the LPRMs. The blue curve is the result of the tip trace going down through the instrument tube. And the issue here, or the problem that's trying to be solved, is when the tip goes down through that tube, there's not a very accurate sense of what the starting point is. And so in order to align the tip, we look for shadows caused by the spacers in the tube. And you can see a little bit of that in here. There's some wiggles and humps. And the idea there is that once you understand, and of course the positions of the spacers are well known, once you can correlate the curve of the flux curve with the spacers, then you have a proper alignment and everything will work out. If you don't have good alignment, among other things, your LPRM calibrations are going to be off, which is a big issue, and then your axial power distribution is going to be incorrect. So the idea here is that we will build a classifier or some other type of machine learning model that will act as a calibration tool for the tip trace. Next. So one of the areas that we wanted to cover too was the technology impact, and one of our missions is knowing that to provide enough clean baseline energy as fossil fuels are taken offline, there's going to be a persistent reliance on nuclear power, especially the existing fleet, until the next gen of reactors is put in place. And so, the particular project we're doing here, which is the feed water control and the LPRM sensor, is part of a larger campaign of industry-focused AI to keep the existing fleet competitive. It's no secret that subsidies to other types of energy have really hurt the economic viability of our reactor fleet. And so this is an effort to try to do as much as possible to lower not only the operational cost, but the fuel cost. And so in this diagram, as I pointed out in the lower left two icons, you can see the LPRM virtual sensor and the feed water heater control. Those are two projects that we're doing now. A related project that we've done in the past, where we've used some of the techniques on the present project, is the SRV chattering problem. The safety relief valves in certain reactors exhibit chattering, which tends to eventually disrupt the discharge portion of it, and then the reactor has to shut down because a critical safety component is gone. And so machine learning models were used to be able to associate that with other issues in the reactor plant, and then also be able to predict when it was going to happen. The upper left and just to the right of that are two models based on machine learning that are used on the lower right, which is the reload planning process. So again, in terms of trying to save money and run more economically, you can reload with fewer fresh fuel bundles. And in order to know whether that's going to work or not, you need two pieces of information. If you reduce the number of fresh fuel bundles, are you going to cause yourself an MCO problem? Because if the MCO gets too high, especially up in the red area, two things happen. One, you get hydrochloric acid created by the water molecules leaching chlorine, and the water also carries cobalt-60, making cleanup that much more difficult and increasing exposures. So that's the idea of keeping the MCO down in the green area. So these models were the first actual predictive models that the utilities had, so that they could make decisions that might influence MCO and be confident that they weren't going to exceed any limits. And then in the upper left is the eigenvalue model for BWRs, and that again is used to determine how much energy is going to be coming out of a given fuel load, and both of those two applications are used in the fuel reload planning process. And then finally, in the upper right, over the last several years, close to $80 million has been saved by just a small fraction of the BWR fleet. And those savings have come in several in several varieties. Some of them have been on reload costs using K-effective or using the MCO models. Some of them have been in power generation, being able to understand if there was a high MCO event, could you model different ways to get through without shutting down? And then finally, on the last 3 years, you can see the effect of some of the OA&M work that is being done presently with this particular project. Next. So now we'll turn to results and accomplishments and the LPRM modeling. On the left, we see the data coverage. As you can see, there's a lot of data, 15 years of it, from 2 operating stations. The type of data, it does vary by unit, but it's LPRM readings, power and replacement history, end of life determination worksheets, incident reports, PPC points and mappings and diagrams. As far as the incident reports go, we've taken volumes of those and basically written natural language processing programs to identify the most frequent faults. Then, and most of the material in this upper box has been on spreadsheets that we've converted into a proper database. On the right, you can see there's a lot more data. There's blade depletion data, dome pressure, core flow, etc. And we use some of this data in modeling, but that data is all electronic. On the right, you can see the representative data. You can quickly see that in the past, a lot of the data is gone, and what happens there is the data is collected very frequently, but to save space on the storage facilities, it's deleted, although it was still very usable. So when we looked at taking the data and breaking it into training, validation, and test, we used the older data as well as some newer data to get enough volume, and then the validation and test we used in the years 2018 to 2020. So when you see our predictions, we're predicting those particular LPRM values based on all the other data that's in here. Next. This is a quick view of the modeling techniques we use. We derived 3 different models. The first model was called a surrogate LPRM model, and that's based on all of the other LPRMs. There are about 172 LPRMs in a large BWR. And so there's a certain self-consistency of measurements in various LPRMs relative to their neighbors that exist that the neural net can derive. And so we have 2 models. One is just one LPRM string predicting another, and then the other is using all the LPRM strings to predict other LPRM strings. Those 2 models are on the bottom right. They're relatively simple models. Then we derived what we call the cycle parameter model. We didn't use any of the values in other LPRMs. We used nodal power, rod variables, core flow, core power, and thermal power. And the output was a single LPRM reading. That was the most accurate model that we were able to derive. You can see the model up on the upper right. It's a modified convolutional neural network. You can see up on top, there's certain scalar features that go in there. There's 3-dimensional features. We use something called axial attention. It's a technique that's used in some CNNs to direct the neural net to pay attention. In image recognition, it directs the neural net to pay attention to the most important pixels. In this case, we used it in a similar fashion, except in this case, it's going to pay attention to the most important nodal power data and the like, based on its particular location within the reactor. And then on the lower, the last particular model that we developed is what we call a panacea correction model. the core simulator that's used puts out an LPRM value, a physics-based calculation, and then we found out that that value wasn't particularly accurate, although it's used now pretty extensively. And so we developed a neural net that would correct that value. Next. So this is then a quick overview of the output and the accuracy. We've been able to get a 4 times improvement in accuracy. On the left is a reference. You see the panacea value. And then going to the right, you see our LPRM surrogate. That's the accuracy for that. Then the nodal power only model, nodal power plus scalars, nodal power plus rod, and then finally all of the variables except other LPRMs and panacea. And then on the right, the panacea correction model, which is just a neural net, which gives a corrected version of the LPRM reading. Next. So this is
supposed to wrap up this.
Yeah, I'll wrap up after this slide.
Thank you. Thank you.
This is, yeah, why don't we go to that model? Yeah, this is just a visualization of the results. Go to the next one, actually. So you can see that the neural net does a great job of accurately predicting the actual measured values. And understand, though, this is a zoomed in model. Next. And why don't you go right to the second last slide, Jonathan? Yeah, there we go. From a commercialization point of view, there's a tool being developed that will give at a glance everything you needed to know about your LPRMs. Again, the slides will be given to everybody. You can look through this, and then why don't you go to the last slide since we're running out of time. So summary of accomplishments, machine learning models that allow virtual calibration as well as virtual measurements. We have a visualization tool that will automate a lot of the cumbersome work. And then we're in the initial stages of the remaining useful life model. And we have a machine learning model under development for the tip calibration issues. And so most of this work for fiscal year 22 will be continued development of the LPRM models, the tip trace, and as we said before, we'll also be modeling the feed water heater subsystems, and then we'll be testing and validating those models with partnering utilities. So with that, I'll end the talk and open up to questions.
All right, thank you very much. I was looking, don't see any specific questions for you yet. We are jumping into the panel session now. So guess since Dan's jumping on, I'll turn it over to Dan and Patrick if you have any questions for the panel. I wrote down a couple of things too, so we'll just see how we're doing on time.
I may ask a question related to the last talk, Tom. I may have missed, what sensor were you planning to use for corrosion monitoring?
Oh, we're using some of the tests that are run, at the plant for that, in some of the data that they take associated with the corrosion.
Yeah, this is John Nistor. I'll just emphasize, yeah, so they'll do infrequent periodic in situ testing, and then, that's like kind of a semi-supervised learning, way to tether, and then we're looking at process and data from the plant, in the finer grain timestamp to augment in between.
But you don't know if the data are taken basically by visual inspection or by...
No, they do a lot of like, what are the integrity tests they do? They use a lot of like microwave and ultrasonic stuff.
Well, ultrasound for thickness. So they're looking at the thickness essentially.
Yeah, there's qualified data on an infrequent but periodic basis.
Patrick, can I ask a question on the same topic? This is Vivek. So on the flow accelerated corrosion, are you familiar with the CheckWorks software that EPRI has developed, which they use as an industry standard?
No,
Sorry, go ahead.
No, we haven't used that yet, but we'll certainly look into that.
Vivek, this is Rick. So CheckWorks is a flow accelerated corrosion program. What has it got to do with the presentation we just listened to?
So it's on the flow accelerated corrosion. So EPRI has this CheckWorks as a modeling tool. Whenever they take the UT data, they do go and put that as an input into CheckWorks, and they come out with an estimate of model thickness of wall.
Yeah, Vivek, actually, now that I think of it, the utility is using CheckWorks, and
yes,
they're
it's
asking.
an industry standard.
I'm sorry.
It's an industry standard. It's widely used by all the nuclear power plants.
They're using it, but they found some limitations, and they'd like kind of, in a sense, a second opinion about what they're learning from CheckWorks.
Yeah, agree on that part. Yeah, but I just wanted to make sure that you're aware of the CheckWorks and the industry standards they use across all the utilities in nuclear power plant here.
Yeah. Yeah, when we first started interacting with them, which wasn't that long ago, that particular part of the project just started in August. They had just put their package together for CheckWorks, and were going to send us a similar package so that we could have access to the same data.
Okay.
All right, thanks, Vivek. Encourage anyone else with any questions or comments to join in. Don't know, Patrick, if that was your one question or if you had another.
No, I had no more questions. Thanks.
Okay, and I don't see any other. Yeah, I don't see any other questions from the audience yet. So, Dan, did you have any questions?
Yeah, I had just a question out of curiosity, Tom. I was just curious, have you ever stress test your compensation algorithms and see how many channels you can turn off and it still give a viable result?
Yeah, that was actually in one of the slides I skipped over. Yeah, there are 3 models, and so the reactor, I'll call it the reactor variable model using nodal power, et cetera. That's really not sensitive to what's turned off. But we also did it with the so-called surrogate model, and we found out that it's very, very resilient depending on which ones are bypassed. If we didn't really show it, but there's an astounding symmetry diagonally across the reactor where symmetric LPRMs read almost identically. And if you happen to take, one of those offline and its symmetric partner you're trying to read, then it gets worse. It doesn't completely degrade, but it does get worse. But if you keep most of the symmetric LPRMs in place, you still get really good readings.
Okay. Yeah, I was just curious about this method being used to optimize the number of sensors necessary to give an accurate result of what's going on in the core. I know that that's been mentioned in some of the talks throughout the sessions the last couple of days, is determining how sparsely populated a sensor array can be, but still give accurate results.
Yeah, we could probably do some of those experiments pretty readily with the models that we have now.
Okay. All right. Let's see.
Patrick, I know just looking at time and what's left, I don't see any other questions. So would you like to take it over and close this out?
Yeah, I don't know if we want to go back to any of the comments that were raised on this issue of data, purely data-driven type optimization versus physics model constraints. I think this is something that we're going to continue to discuss for as part of the program implementation. So unless there's any specific question, I would probably, I just wanted to mention because we have discussed that before.
Yeah, I think, and I was taking some notes on that as well, and I think that's one of the, and I think you made the point as we were in the middle of the conversations about probably some hybrid solution that's going to blend in both. I think that's what we need to consider, and based on these conversations and continue these conversations, develop when one would be better than the other and where they'd be better served with some hybrid and things like that. The other areas that I think we need to continue to discuss with the research teams is how to expand these models, these different types of Markov decision processes, or any of the different ones that described to us, from the use in supply chain or analytics on generation and things like that into controls, and how they might support some of the autonomous control objectives as well. So looking into a little deeper dive into how we can transition these models and the successes from all this good work into something specific to that is another area I would like to follow up with everybody on. I know we're running out of time, but those are some of the key things I heard that were really positive results that I think would line up very nicely with what we're considering in this area, or digital technology. So appreciate everybody's support in that, and I'll turn it over to you, Pattrick.
So I think I will turn it then to Dan for closing, if there's no more question. I agree, those were the 2 points we have, the 2 threads that we should continue, Craig. So I'd like to thank myself, everyone, for now, and then we'll do that formally after that has participated. And thanks, Craig, for moderating the session today.
Well, thank you very much, everyone, for attending this year's annual review of the Advanced Sensors and Instrumentation Program. So you made it through 4 days consecutive. I know that this was a little bit different format from last year, where we did consecutive weeks, 1 day per week. So of course, I would appreciate your feedback on this format, whether if you have experience last year versus this year, what was the better strategy and layout of the presentations. But of course, appreciate all the presenters and the audience for participating, facilitating good conversations, great questions. This is really one of the main outcomes that I highlighted in the original slides that I presented on the first day, was that we want to engage with the industry, engage with the various project PIs, so that everyone's aware of what's going on in the ASI program and can coordinate scopes or collaborate and develop connections and networking. So I guess final comments was, feel free to reach out to Pattrick or myself. Our emails are listed in the slides that will be sent out. But if you have any questions or feedback, of course, and then feel free to visit the NEAT ASI website. That's also included in the original PowerPoint presentation, as well as look forward to the upcoming standalone ASI website that should hopefully be published here shortly in the next couple weeks or a couple months. And then again, thank you for your participation, and I hope everyone has a nice weekend if you have tomorrow off. So thank you very much.